Number one, how many protons, electrons, and neutrons are found in the ion shown below? An ion is a particle that has an unequal number of protons and electrons. In this particular ion, we have a charge of plus 3, which means that there are 3 more protons than electrons. An atom is electrically neutral. In an atom, you have an equal number of protons and electrons. Now, looking at the numbers on the left side, the smaller of the two numbers is the atomic number, and the larger of the two numbers is the mass number. Now, the atomic number is always equal to the number of protons. So, because the atomic number is 13, we therefore have 13 protons. So, we can eliminate answer choice C and D because they don't have 13 protons. To find the number of neutrons, the number of neutrons is equal to the mass number minus the atomic number. So in this case, it's going to be 27 minus 13. So therefore, we have 14 neutrons. So that really doesn't distinguish answer choice A from answer choice B. So now the last thing we need to look at is the number of electrons. Here's an equation that can help you to find it. The number of electrons is equal to the atomic number, I'm going to write AN for that, minus the charge. So in this case, the atomic number is 13 minus the charge of plus 3. So 13 minus 3 is equal to 10, and so therefore there are 10 electrons. Now it makes sense. If we were to add up the charges, we have 13 protons and 10 electrons. Now the charge of a proton is positive and the charge of an electron is negative. So positive 13 plus negative 10, that gives you a net charge of plus 3. So an ion with a positive charge has more protons than electrons. In this case, aluminum has 3 more protons than an electron in its ionic form. Number 2, what is the correct name for the compound N2O5? Now for each of these problems, feel free to pause the video and try these examples yourself and then unpause it to see if you have the right answer. Now, before I give you the answer for this compound, we need to talk about the naming rules for 2 different types of compounds. And that is for molecular compounds and for ionic compounds. N2O5 is a molecular compound. It's composed of nonmetals. Whenever you have a compound with a nonmetal with another nonmetal, it's a molecular or a covalent compound. Electrons are being shared. Now let's say if we have aluminum chloride, AlCl3. This would be an ionic compound because it's between a metal and a nonmetal. Now for N2O5, we would use prefixes like mono, di, tri, tetra. Mono's for 1, di is for 2, tri is for 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, deca is 10. So for N2O5, it's dinitrogen, di for 2, pentoxide, penta for 5. So the correct answer is D for this particular problem. Now for aluminum chloride, AlCl3, we won't say aluminum trichloride. That won't be correct for AlCl3. You would simply name it aluminum chloride. So what you need to know for these type of problems is that whenever you're dealing with naming, if you need to name an ionic compound, you should not use prefixes like mono, di, tri, tetra. Rather, you just name it aluminum chloride. If it's a molecular compound where you have a nonmetal combined with another nonmetal, then you should use the prefix like mono, di, tri, tetra. So let's go over a few problems relating to this. So how would you name the compound SF6? So the first thing you need to do is you need to classify it. Is it ionic or is it molecular? So sulfur, is it a metal or a nonmetal? Sulfur is on the right side of the periodic table. The upper right side are composed of nonmetals. So sulfur is a nonmetal. Fluorine is also in the upper right corner of the periodic table, so it's a nonmetal too. Two nonmetals means that you have a molecular compound. So in this case, we do use prefixes such as mono, di, tri, tetra. Now to name it, we won't say monosulfur. For the first element, you don't use the word mono. So you could just simply say sulfur. And then for the second element, you do need to use the prefix. So for 6 represents hexa, so it's going to be sulfur, hexa, fluoride. So now let's say if you want to name this compound, MgF2. So magnesium is in the left side of the periodic table, so it's a metal. And fluorine is on the right side, so that's a nonmetal. A metal and a nonmetal is an ionic compound. So we won't use the prefixes mono, di, or tri, or tetra. So we won't say this compound is magnesium difluoride. That won't be correct. Rather, the correct name is, it's called magnesium. The first element, you just write its name, and the second element, you would add the end in IDE. So magnesium fluoride. Make sure you know your polyatomic ions, by the way, because if it's polyatomic, it could have the end in ite or ate. So make sure you review that. Number 3, calculate the percent composition of aluminum in aluminum sulfite. So the equation that you need for this problem is this. The percentage or percent composition of some element E is the mass of element E divided by the total mass times 100%. Because it's a ratio, if you use mass or molar mass, it doesn't matter, you're going to get the same answer. So we're going to use molar mass in this case. So the mass of aluminum, we want to find the percent composition for aluminum. So the mass of aluminum has to go on top. We have 2 aluminum atoms. So right now I'm just going to write 2Al divided by the total mass. So that's the sum of all the elements. So that includes the 2 aluminum atoms. We have 3 sulfur atoms, S times 3. And we also have 9 oxygen atoms. So notice that there's 3 oxygens here times the 3 on the outside. And then we're going to multiply it by 100%. So let's plug in the numbers. Aluminum, it's like 26.98 in the periodic table, but we're just going to make it a whole number. We're going to say it's 27. And then sulfur, we can round it to 32. And for oxygen, it's about 16. So times 100%. Now you can type this in all at once in your calculator, but for those of you who like to do it step by step, I'll take it one step at a time. So 2 times 27, that's about 54. If we add up all the numbers on the bottom, 9 times 16 plus 3 times 32 plus 2 times 27, you should get a total of 294. So 54 divided by 294 is about 0.18367, and then multiply that by 100%. You should get a percentage of 18.37%. So the closest answer is answer choice A. Now granted, if we were to use exact numbers like 32.06 or oh 07 for sulfur and 26.98, this would probably actually be 18.3, because right now our answer rounds to 18.4. But on a multiple choice test, as long as you get very close to the right answer, you should be fine. But that's how you calculate the percent composition of any element. Just take the mass of that element divided by the total mass of all the atoms in the compound, and then multiply that by 100%, and you should get the answer. Number 4, nitrogen gas reacts with hydrogen gas to form ammonia. Calculate the mass of ammonia, which is NH3, produced if 15 grams of nitrogen gas reacts with excess hydrogen gas. So the first thing we need to do is that we need to write a balanced chemical equation. Nitrogen gas is diatomic, so you can't write it as N. It's N2. And hydrogen gas is also diatomic. So make sure you know your diatomic elements. N2, H2, O2, F2, Cl2, Br2, I2. All of those elements are diatomic. And then it produces ammonia, which is NH3. Go ahead and take a minute to balance this chemical equation. To balance it, we need to put a 2 in front of NH3. So the nitrogen atoms are balanced. We have 2 nitrogen atoms on both sides. Notice that we have 6 hydrogens on the right side. 2 times 3 is 6. So we need to put a 3 in front of H2. So now it's balanced. Now this is a limiting reaction problem. We have the grams of nitrogen gas, and we really don't need the grams of hydrogen because it's excess. It's the excess reagent. The limiting reactant is the one that runs out first. So this is a gram to gram conversion. We need to convert from the grams of N2 to the grams of NH3. We want to find the mass of ammonia. And the best way to do this is to use stoichiometry. So let's start with what we're given, 15 grams of nitrogen gas. So now let's convert grams to moles. Whenever you want to convert grams to moles, you need to use the molar mass found in the periodic table. Nitrogen has an atomic mass of 14, so 2 nitrogen atoms would be about 28. So what this means is that 1 mole of nitrogen gas has a mass of 28.02 grams of N2. Nitrogen is about 14.01 if you want to be more precise. Notice that the units grams of N2 cancel. So right now we have moles. Our next step is to use the molar ratio. We need to convert from moles of N2 into moles of NH3. And to do that, whenever you want to change a substance, you need to use the coefficients in a balance equation. So what these numbers tell you is that if 1 mole of N2 reacts, 2 moles of NH3 are produced. So because we have moles of N2 on top, we need to put that on the bottom. So for every 1 mole of nitrogen gas that reacts, 2 moles of ammonia are produced in this reaction. It's a 1-to-2 ratio. So now the units moles of N2, they cancel. And then our last step is to convert moles of NH3 into grams of NH3. So we need to use the periodic table once more. So hydrogen's about 1.01 on the periodic table. So 1.01 times 3 plus 14.01. NH3 has a mass of 17.04 grams per 1 mole. So the molar mass is always grams per 1 mole. So the units moles of NH3, they cancel. So now we can answer the question. So we need to type this in our calculator. 15 divided by 28.02 multiplied by 2 and multiplied by 17.04. So you should get an answer of 18.24 grams of NH3. And so that's how you can do a gram to gram conversion. Those 4 steps will be the same. You take the grams of, let's say, reactant A, convert it to moles, and then once you have moles, convert moles of reactant A to like moles of reactant or moles of product B. And once you have moles, you convert that to grams. So these 4 steps will be the same anytime you need to do a gram to gram conversion. So A is the correct answer for this particular problem. Number 5, 15 grams of sodium hydroxide is dissolved in enough water to produce a 250 milliliter solution. Calculate the molarity of the solution. Now we're going to solve this problem 2 ways, using dimensional analysis or conversions and using an equation for those of you who prefer to use formulas and equations. So let's start with dimensional analysis. Now what we need to know is that molarity is defined as the moles of solute divided by the liters of solution. So when you're using dimensional analysis, you need moles on top, liters on the bottom. So let's start with 15 grams of sodium hydroxide. Actually, first, we need to write the formula of sodium hydroxide. Sodium is in group 1 of the periodic table, so as an ion, it has a +1 charge. Hydroxide is OH with a -1 charge. Because these two, they have the same charge, the magnitude of the charges are the same, even though the sign is opposite. Whenever you have two ions with the same charge, you can simply pair them together. So the formula of sodium hydroxide is simply NaOH. Now keep in mind, let's say if it was like magnesium hydroxide. Magnesium would have a +2 charge because it's in group 2 of the periodic table, and hydroxide has a -1 charge. So if the magnitude of the charges are different, you need to use this crisscross method, and then the formula would be MgOH2. Because if you mess up in the formula, the whole problem is gone. That's it, you won't get it right. So make sure you write the correct formula before you proceed. So let's begin. We have 15 grams of NaOH. And the first thing we're going to do is convert it to moles. So we need to find the molar mass of sodium hydroxide. So we need to add up Na plus O plus H. In the periodic table, Na has an atomic mass of about 23. And for oxygen, it's about 16. And hydrogen is about 1. So if we add 23 plus 16 plus 1, the molar mass of NaOH is about 40, or 40 grams per mole. So because grams is on the top left, we need to put it on the bottom right. So we're going to put 40 grams of NaOH on the bottom, and 1 mole of NaOH on top. So notice that the units grams of NaOH cancel. So now we have moles. Now, since we want to find molarity, we want to keep moles on top. We don't want to cancel it. So the last thing we need to do is divide by the liters. Now, we have the volume in milliliters. If you want to convert milliliters to liters, a quick way to do it is to divide by 1,000. So 250 milliliters, if you divide it by 1,000, is equal to 0.25 liters. You can divide it by 1,000, or you can move the decimal 3 units actually to the left. So if you move it 3 units to the left, you get 0.25 liters. So we're just going to divide it by 0.25 liters, and then this is going to give us our answer. So notice that we have moles on top, liters on the bottom, thus we have the molarity. So 15 divided by 40, and then take that result divided by 0.25, and your answer should be 1.5. So we have a 1.5 molar solution. Now, I'm going to calculate the same answer using formulas and equations. So the first equation that you need to know is that mass is equal to the moles times the molar mass. So whenever you need to find mass, molar mass, or moles, you can use this equation. So we know what the mass is. The mass of sodium hydroxide is 15. We need to find the moles. Here's why. The second equation that we're going to use is this one. Molarity is equal to the moles divided by the volume in liters. So in the first equation, we need to solve for moles. Once we get moles, we can plug it into the second equation. So 15 grams is equal to the number of moles, which in chemistry, moles is represented by the letter N. Think of PV equal nRT. So I'm just going to use N for moles, times the molar mass, which we already know that to be 40. So to solve for N, you got to divide both sides by 40. So N is 15 divided by 40. So the number of moles is equal to 0.375. So now that you have moles, we could divide it by the volume in liters. So the molarity is 0.375 moles divided by the liters, which is 0.25 liters. We've already converted the 250 milliliters into 0.25 liters. So you would have to do that here as well. And then you get the same answer, 1.5 m. So if you prefer to use equations, make sure you add these two equations to your formula sheet. For Gen Chem, as we go through an equation for every problem that we solve, make sure you write that down in your notes. So if you're taking like a final exam, or if you're studying for like the AP chemistry exam, make sure you write these equations down so they'll help you to like quickly review for your Gen Chem final. Number 6. How many milliliters of water must be added to 200 milliliters of a 0.75 molar solution of sodium hydroxide to dilute the concentration to 0.25 m? So this is a dilution problem. And anytime you see a problem where it's like molarity, volume, you can use the equation M1V1 is equal to M2V2. So the original solution has a molarity of 0.75, so that's going to be M1. And the volume of that solution is 200 milliliters. Now the new solution, the diluted one, we want it to have a concentration of 0.25. So V2 is going to be the volume of that solution. So let's solve for V2. To do that, we need to divide both sides by 0.25. So these units, those values, they cancel. Now 0.25 goes into 0.75 3 times. So if you divide 0.75 by 0.25, you should get 3. And then 3 times 200 is 600. So the entire left side is equal to 600. So that's V2. But now you have to be careful because the question asks how much milliliters of water should be added. If they were asking for the final volume, 600 would be the answer. But if they're asking how much water should be added, you need to take the difference between 600 and 200. So you got to add 400. So now let's make sense of this problem. So we know answer choice C is the correct answer. But here's the original solution. And then this is going to be like the diluted solution. So this is the old, and this is the new one. So originally the volume was about 200. And the concentration was 0.75. Anytime you add water to a solution, the concentration is going to decrease. Whenever you increase the volume by adding water, the molarity is going to go down. So we know the final volume is going to be 600. That's what we got from the equation. If we triple the volume, if you increase the volume by a factor of 3, the concentration should drop by a factor of 3. So notice that 200 times 3 is 600, but 0.75 divided by 3 is 0.25. So if you triple the volume, the concentration should decrease by a factor of 3. So now the question wanted to know how much water should we add to the original solution so that we can make this new solution with a concentration of 0.25. We realized that we need 600 milliliters of water. We have 200 already in the solution. So to go from 200 to 600, we simply need to add 400 milliliters of water. And so that's why that's the answer. So be careful with the wording of the question. If they wanted the final volume of the solution, it's 600. If they want to know how much water should be added, it's 600 minus 200, which is 400. Number 7. What is the correct oxidation state of chromium in sodium dichromate? So for this particular problem, we need to write an equation. So we have 2 sodium atoms plus 2 chromium atoms plus 7 oxygen atoms. I'm going to put the O in parentheses so it's not, you don't confuse it with 70. And this should all equal to a net charge of 0. If there was a net charge, we would place it here. But since there's no net charge in this compound, we're going to make it equal to 0. Now, sodium is found in group 1 of the periodic table, so sodium usually has a +1 charge. For chromium, we need to solve it, so let's call it X. And oxygen usually has a -2 charge. So 2 times 1 is 2, and 7 times -2 is -14. So we can add like terms. 2 plus -14, that is -12. And then if we add 12 to both sides, those numbers cancel, so we get 2x is equal to 12. And then we need to divide both sides by 2. And so x is equal to 12 divided by 2 is +6. So that's the oxidation state of chromium. It's +6. So let's go over some examples relating to this. So let's say if you want to find the oxidation state of sulfur in sulfur dioxide. You would write an equation, S plus 2 oxygen atoms equals to a net charge of 0. And oxygen, which is in group 6, usually has a charge of -2. So this is S minus 4 equals 0. If you add 4 to both sides, sulfur has an oxidation state of +4. Now what about phosphor in the phosphate ion, PO4 3-? What is the oxidation state? Now because we have a net charge, instead of setting the whole thing equal to 0, we're going to set it equal to -3, the net charge. And typically when oxygen is bonded to an element other than fluorine, it usually has an oxidation state of -2, unless it's in its pure elemental form, which in this case will be 0. Any element in its pure elemental form always has an oxidation state of 0. So 4 times -2 is -8, and if you add 8 to both sides, -3 plus 8, that's going to give you 5. So the oxidation state of phosphorus is 5. So here's some general rules. If you have a pure element like H2, N2, O2, the oxidation state is going to be 0. Now, fluorine in a compound is always -1. Oxygen is usually -2, except when bonded to fluorine, or if it's in the form of peroxide or a superoxide. If you hear the word peroxide, oxygen has an oxidation state of -1, but 99% of the time it's going to be -2. So if it's oxide, it's -2, but if you hear the word peroxide, it's -1. Now hydrogen has an oxidation state of +1 when bonded to a nonmetal, but when hydrogen is bonded to a metal, it has an oxidation state of -1. So here are some examples. Calculate the oxidation state for sulfur in this compound, H2SO4. So we have 2 hydrogen atoms, a sulfur, and actually let's change it. Let's make it a little bit more interesting. Let's say find the oxidation state of sulfur in HSO4-. Try that one. So we have 1 hydrogen atom, a sulfur atom, and 4 oxygen atoms, and the net charge is -1. Now hydrogen, which is bonded to a nonmetal, has an oxidation state of 1. We're solving for sulfur, so we're going to call it X, and oxygen is usually -2. So we have 1 plus X minus 8, which is equal to -1. 1 minus 8 is -7. So if we add 7 to both sides, -1 plus 7, X is +6. So that's the oxidation state of sulfur. Go ahead and calculate the oxidation state of hydrogen in calcium hydride. So if we were to write an equation, we would have to set the net charge to 0. Now calcium is in group 2 of the periodic table, so it has a +2 charge. And so we're solving for hydrogen in this case. So since hydrogen is bonded to a metal, it's not going to be +1. If we move this 2 to the other side, if we subtract both sides by 2, we're going to get -2 on the other side. And if we divide both sides by 2, you can see that hydrogen has an oxidation state of -1 when it's bonded to a metal. When it's bonded to a nonmetal, like an acid, it's +1. And the last unusual case is hydrogen peroxide. This is the one case where oxygen is not 0 or -2. If you write an equation 2H plus 2O, and if you set it equal to 0, you need to plug in +1 for hydrogen because it's bonded to a nonmetal. So if we subtract 2 from both sides, we get 2 oxygen atoms, has a net charge of -2. And if we divide both sides by 2, you can see that oxygen has an oxidation state of -1 if it's in the form peroxide. But in the form oxide, it's -2. The only time oxygen has a positive oxidation state is when it's bonded to fluorine. If you solve for oxygen in this case, we're going to call it X. Fluorine always has a charge of -1 if it's not in its elemental form. So we have X minus 2 is equal to 0, and if we add 2 to both sides, this is the one case where oxygen has a positive oxidation state. So it has a positive 2 oxidation state in this particular example. So that's just a quick review of how to find the oxidation state of elements in compounds. Number 8. 38.6 milliliters of a 0.249 molar solution of sodium hydroxide was required to completely titrate 44.7 milliliters of a sulfuric acid solution. Determine the unknown concentration of the sulfuric acid solution. So notice that we have a molarity, a volume, and we're looking for another molarity given a different volume. So you can use M1V1 equals M2V2 for this particular equation. However, it's different from the last example that we did. In the last example, it was a dilution problem which contained only one substance, and that was sodium hydroxide. Or it might have been something else. But whatever the substance was, it only contained one substance. Now, for this particular example, we have two different substances. We have NaOH and sulfuric acid, H2SO4. So it's a little different, but you can still use the equation. So on the left side of the equation, we're going to use sodium hydroxide, and for the right side, it's going to be, we're going to apply the information that relates to H2SO4. So M1V1 is equal to M2V2. However, you have to take into account the molar ratio that's found in the balanced reaction of NaOH and H2SO4. But it turns out that we don't actually have to write the reaction to get the right answer. And notice that sodium hydroxide only has one hydroxide ion in it. So therefore, put a 1 in front of M1V1. And notice that H2SO4 has 2 protons, 2 hydrogens in it. So put a 2 in front of M2V2. If you do that, you're going to incorporate the molar ratio of this reaction, and you're going to get the right answer. Now, we're going to solve this problem two ways, using the equation and using dimensional analysis. So let's start with the equation first. So molarity 1, for this to work, we have to use the molarity for NaOH, which is 0.249. And the volume is 38.6 milliliters. The volume could be in milliliters or liters, but they simply have to match. If V1 is in milliliters, V2 has to be in milliliters. If V1 is in liters, V2 has to be in liters. Now we're looking for the second molarity. That's the unknown concentration of sulfuric acid. V2 is 44.7 milliliters. So now, to solve for M2, you need to multiply by 0.249 times, if you multiply 0.249 times 38.6, you should get 9.6114, and then divide it by 2 times 44.7. 2 times 44.7, that's like 89.4. And if you take 9.6114 divided by 89.4, you should get the answer. So the molarity of H2SO4 is 0.1075, or if you round it, 0.108. Now let's see if we can get the same exact answer. used in dimensional analysis. So we're looking for the concentration of H2SO4. So you don't want to start with the volume of H2SO4. Rather, start with the molarity of the other substance, sodium hydroxide. If you start with sulfuric acid, you're just going to make your life harder. So if you're solving for the concentration of sulfuric acid, start with either the volume or the molarity of the other substance. Now, to use dimensional analysis, we have to write a balanced reaction. So sodium hydroxide reacts with H2SO4, and it's going to produce, this is an acid-base neutralization reaction. And if you make a list of the ions that you have, Na has a +1 charge, hydroxide has a -1 charge. So in sulfuric acid, we have the H+ ion, and we also have sulfate, which has a -2. Whenever you pair up H+ and OH-, you're going to get H2O. And if we pair up Na+ with SO4 2-, I'm going to write it over here. So here's Na+, and here's SO4 2-. So we got to use that crisscross thing. So it's going to be Na2 SO4 1, but you don't have to write the 1. So now we have our equation. So now we just got to balance it. So notice that we have 2 sodium atoms on the right side, so we need a 2 in front of NaOH. And if you have 2 hydroxide ions, 2 hydrogen ions, you need 2 water molecules. Now it's balanced. So now let's start with the molarity of sodium hydroxide. When you're dealing with dimensional analysis, you don't want to write 0.249 capital M NaOH. Rather, you want to break down molarity into its 2 units. Molarity is moles over liters. So we're going to write it as 0.249 moles of NaOH per 1 liter. Because that's what molarity is. It's the moles per 1 liter of solution. Now we're going to multiply by the volume that corresponds to NaOH. And that's 38.6 milliliters. But because we have liters here, we need to convert it into liters. So to convert 38.6 milliliters into liters, you can divide it by 1,000 or move the decimal 3 units to the left, in which case it's going to be 0.0386 liters. So the units liters cancel. So we have moles of NaOH. Now we want to change from NaOH to H2SO4. Whenever you want to change from one substance to another, you need to use the molar ratio of the balanced reaction, which is a 2-to-1 ratio. So what this means is that for every 2 moles of NaOH that reacts, 1 mole of H2SO4 reacts with it. So because we have NaOH on the top, in the top left, we need it in the bottom right, so that these 2 units will cancel. Now we're looking for molarity. Whenever you're looking for molarity, and if you wish to do dimensional analysis to find it, you need to have moles on top and liters on the bottom. We want to find the molarity of H2SO4, so we already have moles on top, which means we don't want to cancel it on the bottom. Rather, we want to put liters on the bottom. Now 44.7 milliliters, if we convert that to liters, if you divide it by 1,000, you should get 0.0447 liters. And we'll put a 1 on top. So we have moles on top, liters on the bottom. That's going to give us molarity. So now let's type in what we have. So 0.249 times 0.0386 divided by 2, enter, get that result, and then divide it again by 0.0447. And then you should get answer choice A, which is 0.1075. So now you know how to solve this problem both ways, using the equation if you think that's easier, or if you prefer dimensional analysis. Number 9. A 250 milliliter sample of argon gas has a pressure of 1.25 atm at a temperature of 300 Kelvin. Calculate the new pressure if the temperature is increased to 500 Kelvin and if the volume is decreased to 100 milliliters. So, look at the units that you have, and that can help you to determine what equation you need. So we have a volume, a pressure, and a temperature. And we're looking for a second pressure, we have a second temperature, and a second volume. So what equation has a P, a V, and a T in it? And another P, another V, and another T in it? It's probably this one. P1 V1 over T1 is equal to P2 V2 over T2, the combined gas law. So let's plug in what we have. P1, that's the first pressure, that's going to be 1.25 atm. The first volume is 250 milliliters, and the first temperature is 300 Kelvin. In this equation, volume could be milliliters or liters, but the units have to match. If V1 is in milliliters, V2 has to be in milliliters. Pressure could be in atm, it could be in torr, it could be in millimeters of mercury, but it has to match as well. So if P1 is in torr, P2 has to be in torr as well. However, the temperature has to be in Kelvin. It cannot be in Celsius. If you put it in Celsius, you will get it wrong. So don't do that. P2, the second pressure, we're looking for that. The second volume, that's going to be 100 milliliters, and the second temperature is 500 Kelvin. So what we're going to do is cross multiply. So if we multiply the 1.25, the 250, and the 500, we should get a big number, 15625. That does not look like a 2. 156250. And then if you cross multiply for the other side, P2 times 100 times 300. 300 times 100, that's basically 30,000. You just do 3 times 1 and you add the 4 zeros. And then times P2. So now we have to divide both sides by 30,000. So the second pressure has a value of 5.21 atm. And that's the end. That's it. That's all you got to do for this particular problem. So D is the correct answer choice. Number 10. Calculate the density of oxygen gas at STP. STP stands for standard temperature and pressure. At STP, the temperature is 0 degrees Celsius or 273 Kelvin, and the pressure is 1 atm. But also, something else that you need to know at STP is that 1 mole of a gas, it could be any gas, occupies a volume of 22.4 liters. With that knowledge, we can get the answer. Oxygen is diatomic, it's O2, and it has a molar mass of 16 times 2, which is 32 grams per mole. Look at the units. Notice that the units for our answer is like grams per liter. So with these two numbers, we can get the answer. So start with 32 grams of oxygen gas per 1 mole. That's the molar mass. That's what we have here. And then convert moles into liters. So notice that using this mole to liter ratio, we can say that 1 mole of oxygen gas occupies a volume of 22.4 liters. So the units moles cancel, and we have our desired units, which is grams on top, liters on the bottom. So to find the density of a gas at STP, all you need to do is take the molar mass and divide it by 22.4. So 32 divided by 22.4 is about 1.43. And so that's the density of oxygen gas at STP. Now there's another equation that you could use. Density is equal to the pressure times the molar mass divided by RT. Let's say if it wasn't at STP. But let's solve this problem. At STP, the pressure is 1 atm. If it's different, then just plug in a different pressure. The molar mass is 32 grams per mole. That's for oxygen. And then R is the gas constant. So we're going to use 0.08206, That particular gas constant has the units liters times ATM over moles times Kelvin. There's another gas constant which is like 8.3145, but that has a different units. It has joules, moles, and Kelvin. If your pressure is in ATM, you want to use this one. Notice that the units ATM cancels and moles cancel as well. The last thing we need to plug in is the temperature. At STP, the temperature is 273 Kelvin. So the units Kelvin cross out as well. So the only unit that we have now that's left over is it's grams over liters. And so that's going to give us the density. So if you type this in the calculator, 1 times 32 divided by 0.08206, and then take that result divided by 273, you should get 1.43 grams per liter. By the way, be careful with the way you type this in. If you're not getting the answer, when you divide by both numbers in the bottom, put this in one big parentheses. Because sometimes if you, let's say if you were to write it like this in your calculator, 1 times 32 divided by 0.08206 times 273. Your calculator is going to divide by this number and then multiply by 273. So that's a common mistake that students make. So make sure you put this in parentheses, and you should get the right answer. Number 11. Calculate the partial pressure of ammonia if 24 grams of nitrogen gas reacts with excess hydrogen gas at 298 Kelvin inside a 2.5 liter container. So notice that we have three different substances: ammonia, nitrogen gas, and hydrogen gas. So we need to write an equation. Nitrogen gas is N2, hydrogen gas is H2, and ammonia is NH3. So to balance it, let's put a 2 in front of NH3 and a 3 in front of H2. Now, our goal is to find the partial pressure of NH3. We have the temperature and the volume. What we need is the moles of NH3, but we have the grams of a different substance, N2. So we need to convert grams of nitrogen gas into moles of NH3. So let's start with 24 grams of N2 over 1. So to convert from grams to moles, you need to use the molar mass found on a periodic table. The molar mass of nitrogen is about 14.01. So for 2 nitrogen atoms, it's going to be about 28.02 grams per 1 mole of nitrogen gas. Now, our next step is to use the molar ratio. The molar ratio between N2 and NH3 is a 1:2 ratio. So for every 1 mole of N2 that reacts, 2 moles of NH3 are produced. So notice that the units grams of N2 cancel, as well as the units moles of N2 cancel. So we have our desired units moles of NH3. So now we need to take the calculator. So 24 divided by 28.02 times 2. You should get 1.713 moles of NH3. So now that we have the moles of NH3, we can now find the partial pressure of NH3. So we have moles, temperature, volume. To find pressure, we need to use the ideal gas law, PV equals nRT. So the volume has to be in liters. It's 2.5. N is going to be 1.713. R is the gas constant, 0.08206. Whenever you use this gas constant, your volume has to be in liters. It can't be in milliliters. And your pressure has to be in ATM. It can't be in torr or millimeters of mercury. And the temperature has to be in Kelvin. So to get the answer, here's what you need to type in your calculator. It's 1.713 times 0.08206 times 298. Take that result and then divide it by 2.5. So the answer that I have is 16.76 ATM, which rounds to about 16.8. So answer choice C is the correct answer. Number 12. 4.722 grams of an unknown gas is collected over water inside a 2.75 liter container at 298 Kelvin. The total pressure inside the container is 749 torr, and the vapor pressure of water is 23.76 torr. Determine the identity of the unknown gas. Anytime you're trying to find the identity of the unknown gas, what you need to do is calculate the molar mass. And then you want to find the molar mass of every answer choice. So for hydrogen, the molar mass is 2. For CO2, the molar mass is 12 plus 16 plus 16, that's 44. For N2, it's 28. And for xenon, I think it's like 130 something. I have to look at my periodic table. And I don't have that with me, but it's somewhere, it's very high. So if I get a number that's 100 something, it's probably going to be xenon. But the goal is that we need to find the molar mass, and we can identify the compound. Now, to find the molar mass, we need to take the grams, which we already have, which is 4.722, and then divide it by the moles. To find the moles, we can use PV equal nRT, but we have to be careful because there's a lot of vapor in this problem. We don't only have one gas. There's 2 vapors that we have. We have the unknown gas, which I'll call partial pressure of the gas, plus the partial pressure of water. Anytime you have a collected over water problem, you have to consider the partial pressure of water. And this is going to equal the total pressure. The total pressure, we know it to be 749 torr. We need to find the partial pressure of the gas, and the vapor pressure of water is 23.76. So let's subtract 749 by 23.76. So the partial pressure of the gas is 725.24 torr. In order to use the ideal gas law, PV equal nRT, we need to convert that to ATM. So divide it by 760 to convert it to ATM. So this is equal to 0.9542 ATM. So now we can use the formula PV is equal to nRT. So let's plug in the partial pressure of the unknown gas, which we know it to be 0.9542. The volume, we have a 2.75 liter container. Our goal is to find N. Once we find the moles, we can find the molar mass. R is going to be the same, 0.08206, and the temperature is 298 Kelvin. Now to get the answer, this is what you need to do to get the moles. Multiply 0.9542 by 2.75, and you should get 2.62. Then divide that by 0.08206, and then you should get 31.977, and then take that result divided by 298 Kelvin, and then you'll get the moles. So N is equal to 0.1073 moles. Now, to find the molar mass, which I'll write as capital M, that's not molarity, by the way. Molar mass is going to be the grams divided by the moles. It has the units grams per mole. So let's take the mass, which is, we have 4.722 grams of the unknown gas, and let's divide it by the moles, 0.1073. So 4.722 divided by 0.1073, we get a molar mass of 44.0, which means that the unknown gas is carbon dioxide because it has a molar mass of 44. And that's what you need to do anytime you need to identify the identity of an unknown gas. Find the molar mass, take the grams divided by the moles, and that's it. Number 13, which of the following statements is not correct? So this is like a true or false problem. So A, the average kinetic energy of a sample of gas is dependent on temperature. That is a true statement. Kinetic energy is equal to or proportional to 3 over 2 RT. That's for a sample of gas. So as the temperature goes up, the average kinetic energy of a sample of gas will also go up. They're proportional. Now looking at D, the average velocity of gas particles is dependent on temperature. Is that true or false? It turns out that's another true statement. The root mean square velocity of a gas is equal to the square root of 3RT divided by the molar mass, where the molar mass is in units not in grams per mole, but in kilograms per mole. And R for both of these equations is not 0.08206, but it's 8.3145 joules per mole per Kelvin. So as you can see, as temperature goes up, the root mean velocity will go up, which means that the particles will be moving faster at a higher temperature. So A and D are true statements, so we're down between B and C. Now looking at C, heavier gas particles exert a greater pressure on the walls inside of the container. Do you think that's true or false? It turns out that statement is false. We're going to consider 2 reasons for that. Let's kind of jump into physics. Now, you might be thinking, well, pressure is force divided by area. So the larger the force, the greater the pressure, right? And that is true. But you have to realize that heavier gas particles, they move slower. And even if you increase your mass but decrease your speed, it turns out that the pressure will be the same. If you go into physics, and if you look at the impulse momentum theorem, the force multiplied by the contact time equals mass times the change in velocity. So, assuming that the contact time is the same for like a heavy gas particle and a light gas particle, if we increase the mass and decrease the velocity, there's going to be no effect. The impulse, the force multiplied by the contact time, is going to be the same. So you won't have a greater force if the contact time is the same. So therefore, heavier gas particles do not exert a greater pressure. Now another way you can see this is to use the equation PV equal nRT. Let's consider 2 samples of gases. Let's say we have hydrogen gas, which is a very light gas, and let's use a heavy gas like chlorine. Now let's say that they're at the same temperature, let's say 300 Kelvin, and we have the same quantity of gas, 1 mole. So 1 mole of chlorine gas, 1 mole of H2 gas. And let's say the volume of the container is the same. Let's say we have a 2-liter container. Will the pressure be the same or different if we have a lighter gas versus a heavy gas? Now looking at this equation, PV equal nRT, we have the same volume, which is 2 liters, same number of moles, which is 1. R is going to be the same, it's a constant, and the same temperature. So if the volume, if the volume, temperature, and moles are the same, based on the ideal gas law, P has to be the same as well, regardless if one gas is light or the other gas is heavy. Because molar mass is not part of this equation, the pressure is going to be the same for the light gas and the heavy gas. So therefore, heavier gas particles do not exert a greater pressure. So C is the false statement. Therefore, we're looking for the statement that is not correct, so C is the answer. Now, B is a true statement. The pressure inside a container is dependent on the total number of moles of gas. As we can see, moles is part of the equation. If we increase the moles of the gas, keeping everything the same, the pressure is going to increase. So B is the true statement. So the answer for this one is C. C is the false statement. Number 14, which of the following conditions will allow a real gas to behave more like an ideal gas? Is it high temperature, low temperature, high pressure, low pressure? What would you say? Now, let's start with a liquid. If we have a liquid, what's going to happen if we decrease the temperature? If we put it in a low temperature environment, like a freezer, what's going to happen? Eventually, the liquid will become a solid. And so low temperatures do not favor the formation of gases. But what's going to happen if we heat the liquid? Let's say if you were to boil water. Water is going to vaporize into steam, and so it's going to turn into a gas. As you can see, high temperatures favor the formation of a gas, so therefore a real gas will behave like an ideal gas at high temperature. So we can eliminate answer choice C and D. Now in the liquid, the molecules are relatively close, but not that close. In a gas, the particles are very far apart from each other. And in a solid, the molecules are very close together. So let's say if we have a container with gas. Now, let's say if we increase the pressure by decreasing the volume of the container. What's going to happen? So if we compress the container or compress the gas, will the gas turn into a liquid or will it become more gas-like? What would you say? As you can see, because the gas particles are more compressed, they look more like a liquid. So high pressure doesn't favor the formation of a gas. If you increase the pressure, it's going to go this way. High pressure favors the formation of a liquid. If you compress the gas, it eventually converts to a liquid. Low pressure favors the formation of a gas. So a real gas will behave more like an ideal gas at high temperatures and low pressures. The answer is A. So let's review. Let's say if you have a solid. If you add heat to it, it's going to go from a solid to a liquid, and if you add more heat, it's going to go to a gas. So therefore, high temperatures favor the formation of gases. So real gas behaves as an ideal gas at high temperatures. Now, if we were to increase the pressure, increasing the pressure will compress a gas into a liquid. And if you add more pressure, it can go down to a solid. So high pressure favors the formation of solids, but low pressure favors the formation of gases. If you decrease the pressure, the solid will eventually become a gas. Another way you can see this is by looking at the phase diagram, which usually looks something like this. So this is the solid, this is the liquid, this is the gas. And on the y-axis we have pressure, on the x-axis we have temperature. So let's say if we start from here. If we increase the temperature, we're going to go from a solid to a liquid, and eventually from a liquid to a gas. So high temperatures favor the formation of gases. You can see the gases down the right side. Now, let's say if we started from this point here. Let's extend this line further. Let's say if we're to increase the pressure, that means we have to go up the y-axis. So if we increase the pressure, the gas will eventually become a liquid, and then the liquid will eventually become a solid. So high pressures favor the formation of solids. High temperatures favor the formation of gases. So if you want to get a good gas, or if you want a gas to behave like an ideal gas, you need a high temperature and a low pressure. Number 15. How much energy is required to heat 75 grams of water from 25 degrees Celsius to 74 degrees Celsius? And the specific heat capacity of water is 4.184 joules per gram per Celsius. So you need to know the right equation to use, and it's Q equals MCAT, or MC delta T. Q represents the heat energy, M is the mass in grams, C is the specific heat capacity, and delta T is the change in temperature, final temperature minus the initial temperature. So let's plug in the numbers that we have. So the mass is 75 grams, the heat capacity is 4.184, and the temperature difference, final minus initial, 74 minus 25. So 74 minus 25, that's 49. And then we're going to multiply that by 4.184 and 75. And you should get 15,376. Now, what are the units for this number? Is it in joules or kilojoules? Now, Q is in joules because the specific heat capacity is in joules. If you look at the units, the mass is in grams. The specific heat capacity is joules per gram per Celsius. And the temperature is in Celsius. The temperature can also be in Kelvin, by the way, for this particular equation. The units Celsius will cancel, and grams will cancel, and so Q is in joules. But notice that the answer is in kilojoules. So to convert joules into kilojoules, divide by 1,000. So you should get 15.4 kilojoules. So answer choice D is the correct answer. Number 16. How much heat energy is required to melt 25 grams of ice? The heat of fusion for ice is 6.01 kilojoules per mole. Now, the equation for this type of problem, whenever you have a phase change, there's two types. It can be moles times the enthalpy of fusion, if it's in kilojoules per mole, or it could be mass times the enthalpy of fusion, if the units are like joules per gram or something. So it really depends on the unit. What we can do in this problem is we can simply convert grams to moles and moles to kilojoules. And I think that's the best way to solve it. So let's start with 25 grams of ice. And let's convert it into moles. Now, water has a molar mass of approximately 18. Hydrogen is 1, there's 2 of them, so that's 2, and oxygen is 16, so that's a molar mass of 18. So we have 18 grams of water per 1 mole. So the units grams cancel. And next, we're going to convert moles into kilojoules using this number. So this number means that for every mole of ice that you melt, it requires 6.01 kilojoules. So the units moles cancel. And so now we can find the answer. So it's going to be 25 divided by 18 times 6.01. And you should get 8.347 kilojoules. Now, is the answer positive or negative? So as you go from a solid to a liquid, as you melt ice into liquid water, is that an endothermic process or an exothermic process? Well, you have to add heat to melt ice. So because the ice cube has to absorb heat, it's an endothermic process. And for an endothermic process, the enthalpy is positive. So this is going to be a positive answer. The ice cube needs to absorb 8.347 kilojoules of heat to melt into liquid water. And the reverse is true. If you want to freeze liquid water into ice, you have to remove heat. So that would be an exothermic process. So freezing is exothermic, and melting is an endothermic process. So for this problem, the correct answer is answer choice B. Number 17. Which of the following represents the phase change from a gas to a solid? Now this is something you have to know. The answer for this is deposition. So let's review all the different phase changes. So from a solid to a liquid, it is called melting. Think of an ice cube turning into liquid water. It melted. Now, from a liquid to a gas, this is known as vaporization. And from a solid directly to a gas, this is called sublimation. Melting, vaporization, and sublimation, as you go from a solid to a liquid to a gas, these processes are endothermic. The enthalpy will be positive. So now, let's say if you wanted to go from a liquid to a solid. What happens when you put a cup of water in the freezer? It freezes. So liquid to a solid is known as freezing. And a gas to a liquid is known as condensation. And gas to solid is called deposition. So as you go from a gas to a liquid to a solid, all three of these processes are exothermic. So the enthalpy is negative. So energy is released for an exothermic process. Number 18. Calculate the enthalpy of the combustion of ethanol using the following information. So to find the enthalpy of the reaction, we need to use this equation. Delta H is products minus reactants. So on the product sides, we have 2 carbon dioxide molecules and 3 H2O molecules minus the reactants, which are C2H5OH plus 3O2. So now we can plug in what we have. So we have 2 carbon dioxide molecules, each with a value of negative 393.5. Plus we have 3 water molecules, and each with a heat of formation of negative 285.9. Now the value for ethanol is negative 277. And oxygen is a pure element in its standard state, so it has a enthalpy of formation of 0. So now let's plug these numbers into the calculator. So 2 times negative 393.5, that is equal to negative 787, and then 3 times negative 285.9, that's about negative 857.7. And then here, don't forget to distribute the negative sign, so it's going to be plus 277. So if we add these three numbers, we should get a total of negative 1367.7. The closest answer that we have to it is answer choice A. So A is the correct answer for this problem. Number 19, calculate the amount of heat energy released if 10.5 grams of propane reacts with excess oxygen according to the following chemical equation. So this equation is already balanced. So we just need to find the energy in kilojoules, and we're given grams. So here we have a thermochemical equation, and in such a problem, you can convert grams to moles, moles to kilojoules. So let's start with the 10.5 grams of C3H8. Whenever you need to convert grams to moles, you need the molar mass. So 3 carbon atoms, carbon's about 12, so 3 times 12, that's 36, and plus 8 for the 8 hydrogen atoms. So propane has a molar mass approximately about 44. So 44 grams per 1 mole. So the grams of C3H8 will cancel. Now, in a thermochemical equation, you can convert moles into kilojoules by using this number with the balance equation. Now, since we want to convert moles of C3H8 into kilojoules, we need to use this coefficient. If we had oxygen, we would use 5. If we had CO2, we would use 3. So 2200 kilojoules will be released for every 1 mole of propane that burns in this reaction. So we get this number from the balanced chemical equation. So now we just got to plug it in. So it's going to be 10.5 divided by 44 times 2200. So the answer that I got is 525 kilojoules. And it's negative. So the answer is answer choice A. Now granted, if I were to use exact numbers, like carbon is really 12.01, the answer would be closer to 530. But if you use rounded values, you can still get the right answer if the choices are not too close from each other. So that's it. That's what you got to do for this problem. Number 20. Calculate the energy of a photon that has a wavelength of 451 nanometers. There are two equations that you need. The energy is equal to Planck's constant times the frequency. And the wavelength times the frequency is equal to the speed of light. So first, well actually we can combine these two equations. So if you solve for V, the frequency is the speed of light divided by the wavelength. So we're going to replace the V with that. So to find energy directly from wavelength, you can use this equation. It's E equals H times C divided by lambda. So now let's plug it in. So the energy is going to be Planck's constant 6.626 times 10 to the negative 34 times the speed of light, which is 3 times 10 to the 8 meters per second, all divided by the wavelength. Now the wavelength is in nanometers, so you got to convert it to meters. If it's in nanometers, this is all you need to do. Rewrite 451, but add times 10 to the negative 9. So now it's in meters. And then once you type this in, you're going to get the answer. So it's going to be, we're just going to plug it in the way it is, and you should get 4.408 times 10 to the negative 19 joules, if you typed it in correctly. So the correct answer for this problem is answer choice B. Number 21, what is the ground state electron configuration of fluorine? Now, if you have a multiple choice test, the quickest way to find the ground state or the right answer is to use the atomic number. The atomic number of fluorine is 9. So for the electron configuration, the exponents must add up to 9. Looking at answer choice A, it's 1s2, 2s2, 2p3. If we were to add the exponents, 2 plus 2 plus 3, we would get 7, so it's not A. Looking at B, if we add 2 plus 1 plus 5, that will give us 8, so it's not B. And for C, which is 1s2, 2s2, 2p5, if we add up 2 plus 2 plus 5, it gives us a total of 9. C is the correct answer. Fluorine has this electron configuration. Number 22. Which of the following 4 sets of quantum numbers correspond to the last electron found in nickel? Well, the first thing we need to do is find the electron configuration of nickel. So nickel, based on the periodic table, has an atomic number of 28. Now, we're going to write out the sublevels so we can write the electron configuration for nickel. So first you have 1s, then there's 2s, 2p, 3s, 3p, 3d. The third level has 3 sublevels, and the fourth level has 4s, 4p, 4d, 4f. And hopefully we don't need to go past that. So S can only hold 2 electrons, P can hold 6, D can hold 10, F can hold 14. Now, we need to write the electron configuration until it adds up to 28. So first we have 1s2. We're going to add the exponents. After 1s, we have the 2s sublevel, so 2s2. And then after 2s is going to be 2p, then 3s. P can hold up to 6, so it's going to be 2p6, 3s2. If we add the exponents right now, 2 plus 2 plus 6 plus 2, right now we have a value of 12. So after 3s, we have 3p and then 4s. So 3p6, p can hold up to 6, 4s2. After 4s, we have the 3d level. So right now we have a total of 20. 2 plus 2 plus 6 is 10, and 2 plus 6 plus 2 is 20. So we need 8 more, and the D sublevel can hold up to 10. So the last one that we need is 3d8. If you add all the electrons, it's 28 at this point. So that is the electron configuration for nickel. The very last electron in the nickel atom is the 3d8 electron. So we need to find what the 4 quantum numbers are for that 3d8 electron. So focusing on the 3, n is 3. Whatever that first number that we have, that's the n value. For the s sublevel, L is 0. For P, L will always be equal to 1. For the D sublevel, L is 2. And for F, L will be 3. So because it's 3D, we know L is 2. So we can eliminate C, and we can eliminate B. So we're between A and D. Now, looking at A and D, the ML value is both 0. But the MS value is different, negative a half versus positive a half. The answer for this problem is going to be A, but I'm going to show you why it has a spin of negative a half. So for the 3d8 electron, we said that n was equal to 3 because of this number, and for the D sublevel, L is equal to 2. Now when L has a value of 2, ML can be anywhere from negative 2 to 2. The D sublevel has 5 orbitals. The first one has a value of negative 2, the second one is negative 1, 0, 1, and 2. So we need to fill up 8 electrons since we have 8 in the D level. So we're going to start with the up arrows. So 1, 2, 3, 4, 5, 6, 7, 8. This is the 8th electron. Now notice that it's in the 0 orbital, so that means ml is equal to 0. And also notice that we have a down arrow. For a down arrow, the spin is minus a half, and that's why the answer was A. But let's go over some examples. So let's review a few things. So keep in mind, whenever you have the S sublevel, L is equal to 0. And S only has one orbital, so that means ML is also equal to 0. For the P sublevel, L is 1. And whenever L is 1, ML could be 3 values. P has 3 orbitals, and ML can be -1, 0, and 1. We talked about D already. It has 5 orbitals. So for the D sublevel, L is 2. And for the 5 levels, ML can be anything from -2 to 2. And the last one is the F sublevel, where L is 3. Whenever L is 3, ML can be anywhere from -3 to 3. The F sublevel has 7 orbitals. So let's say if you want to find the 4 quantum numbers for the, let's say the 4p2 electron. So n is the first number that you see, 4. For the p sublevel, L is going to be 1. And the p sublevel has 3 orbitals. If L is 1, ML could be -1, 0, or 1. So those are the ML values. And because we're focused on the second electron, we're going to draw just 2 arrows. So the second electron is in the orbital where ML is equal to 0. And because it's an up orbital, an up arrow, the spin is +1/2. So let's look at another example. Let's say if we have the 4f13 electron. Using the information that we just considered, go ahead and find the 4 quantum numbers that corresponds to this electron. So n is 4. For the F sublevel, L has to be 3. Now, for F, there are 7 orbitals actually, with a value ranging from -3 to 3. And a 13 electron lands in, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So here's the 13th electron. It's in the orbital that has a value for ML, which is 2. And because it's facing in a downward direction, the electron spin is -1/2. So that's just some background information on quantum numbers and how they work. Number 23. Which of the following 4 sets of quantum numbers are incorrect? Is it A, B, C, or D? Typically, the first thing I look at is the electron spin. The electron spin can only be either plus or -1/2. If you see any other numbers other than this fraction, you know it's wrong. So if you were to see ms equals 1, you could eliminate that answer. So looking at the spin, for all of them it's a fraction, plus or -1/2, so all of those numbers are acceptable. The second thing you can do is compare n and L. Now L has to be less than or equal to n-1. So what this means is that if n is 4, L cannot equal 4 or anything more than 4. If n is 3, L can equal 2 or anything less than 2. It could be 2, 1, or 0, but it can't equal 3 or 4. So looking at A, n is 3, L is 2. L has to be at least 1 less than n, so A is okay. Same is true for C. For B, if n is 4, L is 0. And D, if n is 4, L is 3. As long as n is greater than L, at least by a factor of 1, it's okay. Now the last thing we need to look at is the ML values, the orbitals, or the magnetic quantum number. ML has to be between -L and L. So what this means is that, let's say if L has a value of 2, that means ML has to be between -2, or 2. So, looking at D, if L is 3, ML could be anywhere from -3 to 3. That means it could be -3, -2, -1, 0, 1, 2, or 3. And ML is -1, so that's okay. So D is fine. Looking at, let's see, answer choice A, if L is 2, ML could be 0, because ML could be -2, -1, 0, 1, and 2. Same is true of C. The only thing that doesn't work is B. When L is 0, ML can be only one value, 0. It can't be -1. So B is the one that's incorrect. So just to review, whenever L is 0, ML can only be 0. This is the S sublevel and there's only one orbital. So ML cannot equal -1. Now, if L were to equal 1, this would be the P sublevel, which has 3 orbitals, and ML could be -1, 0, or 1. And so this would have worked if L was 1, but since L is 0, ML can't be -1. Number 24, how many orbitals are in the n equal 4 principal energy level? The equation that you need is this. The number of orbitals is equal to n squared. So that's 4 squared, which is 16. So D is the correct answer. Now you might be wondering, okay, why does that equation work? In the first energy level, where n is equal to 1, all we have is the 1s level. In the second energy level, when n is 2, we have the 2s sublevel and the 2p sublevel. When n is 3, we have the 3s level and the 3p sublevel and the 3d. For the fourth energy level, we have 4s, 4p, 4d, and also 4f. Now, the 4s energy level can hold, well, let's start with 1. The first energy level can hold up to 2 electrons. And for every 2 electrons, you only have 1 orbital. So the 1s level has only 1 orbital. Now we know that S has 1 orbital, but P has 3 orbitals, which is a total of 4 orbitals in the second energy level. Notice that the total electrons that we have is 8. And if you divide 8 by 2, you get 4, because there's only 2 electrons that can be in a single orbital. For the third energy level, if we add up the orbitals, S can hold 1, P can have 3 orbitals, D has 5. That gives us a total of 9. And for the fourth energy level, if you add up all the electrons, you should get 32. Half of that is 16. S has 1 orbital, P has 3 orbitals, D has 5, F has 7. If you add those numbers, you get 16. So notice that the number of orbitals is equal to n squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And that's how it works. But if you want to see it visually, the 4s level has only 1 orbital. The 4p level has 3. 4d has 5. And 4f has 7. So therefore, we have a total of 16 orbitals in the fourth energy level. Number 25. Which of the following choices correctly ranks the different forms of electromagnetic radiation in order of increase in wavelength? So you need to know it in this order. All the way to the left, we have radio waves, after which we have microwaves, and then infrared radiation, and then visible light. So after infrared, it's red light, orange, or Roy G. Biv, yellow, green, blue, and then violet. After violet, next comes ultraviolet radiation, and then you have X-rays, and then finally, after X-rays, gamma rays. To the left, radio waves have the longest wavelength. I'm going to put the lambda symbol for wavelength. And to the right, gamma rays have the most energy, and they also have the highest frequency. So these are some things that you want to know with regard to electromagnetic radiation. So based on the question, we want to rank it in order of increase in wavelength. So radio waves have the longest wavelength, and gamma rays have the shortest. So looking at that, we could see it's answer choice A. Gamma rays have the shortest wavelength. Next, X-rays. After X-rays is ultraviolet, and then after ultraviolet is visible light. So out of those four, visible light or light waves, they have the longest wavelength. Gamma rays have the shortest wavelength. And that's it for this particular problem. Number 26. Which of the following elements has the highest first ionization energy? Is it helium, fluorine, oxygen, or chlorine? Ionization energy is the energy that is required to remove a valence electron from a gaseous atom. It could be just the outermost electron. Sometimes it could be a core electron, depending on if it's like the second or third ionization energy. But it's the energy required to remove the outermost electron, which is usually a valence electron. So ionization energy increases as you go this way in the periodic table. So it increases as you go up a column or to the right. Now oxygen, so on the periodic table we have carbon, nitrogen, and then oxygen, and then fluorine. And below fluorine we have chlorine, and then here's like neon, and then helium is over there. So notice that helium has the highest ionization energy compared to oxygen, fluorine, and chlorine. Helium is to the right of all the elements, and it's above it as well. So if we were to rank it, helium would have the highest, and then the next one would be fluorine, and then after that we have oxygen and chlorine. So the correct answer for this problem is answer choice A. By the way, just to review the other trends, atomic radii or atomic size increases as you go this way in the periodic table. So as you go to the left and down, it increases. Electronegativity increases towards fluorine. Fluorine is the most electronegative element, and metallic character increases as you go to the left and down. So those are some other periodic trends that you want to be familiar with. Number 27. Which of the following molecules has a trigonoplanar molecular geometry? Is it A, B, C, or D? So let's draw each one. Let's start with sulfur dioxide. Sulfur has 6 valence electrons, and oxygen also has 6, but we have 2 of them. So there's a total of 18. Now, for molecules that do not contain hydrogen, there's a way that you can calculate the number of lone pairs or electrons on the center atom. If you take 18 and subtract it by the highest multiple of 8, just under 18, you'll get the number of electrons on the center atom. So multiples of 8 are 8, 16, 24, 32, but the highest of this that's under 18 is 16. So if we take 16 from 18, we get 2. What this tells us is that sulfur has 2 electrons, or 1 lone pair, on it. And it also has 2 oxygen atoms. Now, sulfur can have what is known as an expanded octet. It turns out that elements that usually have expanded octets, like third row elements like phosphorus, sulfur, and chlorine, the number of bonds and dots that are on that element is usually equal to the valence electrons. So because sulfur has 6 valence electrons, it's going to have a total of 6 bonds and dots. Since it already has 2 dots, it's going to have 4 bonds. So 1, 2, 3, 4. The exception to this is if sulfur has a formal charge. Now, whenever oxygen has 2 bonds, it requires 2 electrons, or 2 lone pairs. I meant 4 electrons, 2 lone pairs. So notice that every oxygen atom has 8 electrons. If you add up all the electrons, you should get a total of 18. And that's the Lewis structure for sulfur dioxide. And it has a bent molecular geometry. Now, CH4. For most carbon-hydrogen compounds, we really don't need to add the electrons, but if you wanted to, carbon has 4 valence electrons, hydrogen has 1 times 4. We should get a total of 8. Hydrogen can only form a single bond, so this is the only way we can draw it. And as you can see, each bond represents 2 electrons, so we have a total of 8 electrons. Methane has a tetrahedral molecular geometry. And keep in mind, for a tetrahedral structure, the bond angle is about 109.5. For SO2 is less than 120. Now, BF3. Boron has 3 valence electrons. Fluorine has 7 times 3, 24. 24 is a multiple of 8, so that tells us that there are no lone pairs on the central boron atom. That multiple of 8 rule works pretty well if there's no hydrogens involved, because hydrogen can only have 2 electrons and not 8. Now, fluorine wants to have 8 electrons. Each fluorine atom has 1 bond, so we need to add 3 lone pairs, so that every fluorine atom has 8 electrons. 8 times 3, we get 24. And that's the Lewis structure of BF3, and it is the correct answer. It has a trigonal planar molecular geometry and a bond angle of 120. Now, for NH3, the multiple rule of 8 thing doesn't work whenever you have hydrogen. Nitrogen has 5 valence electrons, and hydrogen has 1 times 3, so we get a total of 8. Now, hydrogen can only form 1 bond. So right now that's 6 electrons. To get 8, we need to add a lone pair. So that's the Lewis structure for NH3, and it has a trigonal pyramidal structure with a bond angle of 107. So it's not trigonal planar, but trigonal pyramidal. So C is the correct answer for this problem. Number 28. Which of the following molecules has sp3 hybridization around the central atom? Is it water, BF3, BRF3, or sulfur hexafluoride? Let's start with SF6. Let's draw the Lewis structure. Sulfur has 6 valence electrons and fluorine has 7 times 6, which is 48. Now, because 48 is a multiple of 8, there are no lone pairs on the central sulfur atom. So SF6 looks like this. And each fluorine atom has 3 lone pairs. So if you add up the total electrons, you should get 8 times 6, which is 48. The molecular geometry for this compound is octahedral. The bond angle is about 90 degrees all around. And the hybridization is S1P3D2. Notice that the exponents add up to 6. 1 plus 3 plus 2 is 6, because the sulfur has 6 groups attached to it. So sometimes it could be written as D2 sp3. You might see it written that way as well. Now let's look at BRF3. Bromine has 7 valence electrons, and fluorine also has 7 times 3. So we get a total of 28, which is not a multiple of 8. So we're going to subtract that number by the highest multiple of 8, just under 28. So multiples of 8 are 8, 16, 24. So if we subtract 24 from 28, we get 4. So what this tells us is that bromine has 4 electrons, or 2 lone pairs. And it has 3 fluorine atoms, each of which has 3 lone pairs as well. But I'm not going to draw the lone pairs. But just know that fluorine each have 3 lone pairs. So if you add up all the electrons, you should get a total of 28, including the 3 lone pairs on each fluorine atom. Now, the molecular geometry for this compound is, it has a T shape. And if you were to look at the hybridization, Bromine has 5 groups. It has 3 fluorine atoms and 2 lone pairs. So for 5 groups, the hybridization is S1P3D1, which adds up to 5. So it's not C and it's not D. Now looking at B, we know that boron trifluoride looks like this because we drew it in the last example. And so boron has 3 groups, so therefore it has an S1P2 hybridization. 1 plus 2 is 3. So the answer must be water. If we draw water, water has 8 valence electrons. Hydrogen has 1, and there's 2 of them. And oxygen has 6 valence electrons, so for a total of 8. And right now we have 4 electrons. Each bond represents 2, so we need 2 more lone pairs. And that's the Lewis structure for water. It has a bent shape. And notice that water has 4 groups. It has the oxygen atom has 2 hydrogens and 2 lone pairs. So for 4 groups, the hybridization at the central atom is S1P3. 1 plus 3 equals 4. So the correct answer is A. It has an sp3 hybridization around the central oxygen atom. Number 29. Which of the following molecules is polar? Is it A, B, C, or D? If we were to draw the Lewis structure for CH4, methane, this molecule is nonpolar due to the symmetry that it has. Typically, whenever you have a carbon-hydrogen bond, it's relatively nonpolar. The electronegativity value for carbon is like 2.5, and for hydrogen is 2.1. So if the electronegativity difference is less than 0.5, the bond is nonpolar. So A is eliminated. Now for carbon dioxide, if we were to draw the Lewis structure, it would look something like this. It has a linear molecular geometry. Now the carbon-oxygen bond is polar. Carbon has an electronegativity value of 2.5, and for oxygen is 3.5. So the EN difference is much larger than 0.5, so it has a polar bond. Oxygen has a partial negative charge because it's more electronegative than carbon. So if you were to draw the dipole moment, the arrow would point towards the more electronegative oxygen atom. But notice that these arrows are opposite to each other, and therefore they cancel. And so the net dipole moment for this molecule is 0. Therefore, even though it has polar bonds, overall, CO2 is a nonpolar molecule. Now, for boron trifluoride, the situation is similar as well. Fluorine is much more electronegative than boron, and so it has a partial negative charge. And so the bonds are very polar. However, due to the symmetry of this molecule, all of the arrows, they point in opposite directions, and so they all cancel out. And therefore, this is a nonpolar molecule. If you're wondering why those arrows cancel out, let's go back to physics. You have an arrow going this way, and an arrow going this way, and another one going this way. Now looking at the arrow on the bottom right, it has 2 components. It has a y component and an x component. And the same is true for the arrow on the left. It has a y component and an x component. These 2 x components are opposite to each other, so they cancel. And these 2 y components cancel with the larger one on top. So all of it cancels and it's nonpolar. The only one that is polar is NF3. If you draw the Lewis structure, it has a lone pair, and the dipole moments do not cancel. Let's add up the valence electrons first for NF3. Nitrogen has 5 valence electrons. It's in group 5A of the periodic table. And for fluorine, it has 7. 7 times 3 is 21 plus 5. You get a total of 26. And if you subtract that by the highest multiple of 8, just under 26, 8, 16, 24, you get 2. So what that number tells you is that nitrogen has 2 electrons, or 1 lone pair. And every fluorine atom has 3 lone pairs because they want to have 8 electrons. And so the total number of electrons in the structure is 26. We have a trigonal or trigonal pyramidal structure. Now, fluorine is much more electronegative than nitrogen. It has a value of 4.0, and for nitrogen is 3.0. So fluorine bears the partial negative charge, nitrogen bears the partial positive charge. So if we were to draw the dipole moment, it would point towards the fluorine atom. So notice that we have three arrows going in the, for the most part, the general downward direction. And so these arrows do not completely cancel for the most part. They're going towards the bottom. And so there's a net dipole moment. And also the presence of this lone pair also contributes to the polarity of this molecule. So NF3 is a polar molecule. It has a net dipole moment. Number 30. Rank the following intermolecular forces in order of decrease in strength. What you need to know is that hydrogen bonds are stronger than dipole interactions, which are stronger than London dispersion forces. So the correct answer is answer choice B. Now you have hydrogen bonds whenever H is directly attached to nitrogen, oxygen, or fluorine. Dipole interactions occur whenever you have a polar molecule. So dipole-dipole interactions occur between two polar molecules. LDF, London dispersion forces, also known as van der Waals forces, they're found in everything, but they are the most important interaction in nonpolar molecules. So let's say if you were to have a compound like water. Water has hydrogen bonds, so it has an OH bond, so it has hydrogen bonds. Anything that has hydrogen bonds is polar, so it has dipole interactions, and it also has LDF, which is found in everything. Now let's say if you have a polar substance like SO2. SO2 would contain dipole interactions, plus it would also contain LDF. But if they ask you which one is the strongest intermolecular force in SO2, you would choose dipole interactions. For water, you would choose hydrogen bonds. Now let's say if you have like methane. Anytime you have a substance that contains only carbon and hydrogen bonds is nonpolar. The only intermolecular force that's found in methane would be like LDF, dispersion forces or van der Waals forces. Number 31. Which of the following molecules has the highest boiling point? Now, if we look at A, we have a compound that is completely nonpolar. It only contains carbon and hydrogen bonds. So when it's nonpolar, the only force that it has is London dispersion forces. Now, compound D is also nonpolar, and so it has London dispersion forces only. So therefore, these two, which contain the weakest of the intermolecular forces, they're going to have the lowest boiling point. So we could eliminate answer choice A and D. Now, B, we have a sulfur. And if we were to draw the Lewis structure, there's a sulfur group, a hydrogen, and a methyl group, which is a CH3, and it has two lone pairs. So this molecule is polar. It has a bent shape similar to that of water. And because it's polar, it's going to have dipole interactions. So it's going to have a higher boiling point than A or D. Now looking at answer choice C, methanol, we have an OH bond. So methanol has hydrogen bonds. And hydrogen bonds are stronger than dipole interactions, so therefore we should expect that methanol should have the highest boiling point because it has the strongest of the intermolecular forces. So it has H bonds. So C is the right answer. Number 32. 25 grams of sodium hydroxide is dissolved in 300 grams of water. Calculate the molality of the solution. Now, molality is different from molarity. Molarity with an R is the number of moles of solute divided by the liters of solution. Molality is the moles of solute divided by the kilograms of solvent. So let's find the moles of solute and let's divide it by the kilograms of solvent. Water is a solvent. It dissolves the sodium hydroxide. And we have 300 grams of water. So how many kilograms is that? To convert grams into kilograms, you could divide by 1,000 or move the decimal 3 units to the right. So 300 grams is about 0.3 kilograms. Let's start with 25 grams of sodium hydroxide, and let's convert it to moles. To convert grams to moles, you need the molar mass. According to the periodic table, sodium has an atomic mass of 23, and for hydrogen it's about 1, and for oxygen it's 16. So NaOH has a molar mass of 40 grams per 1 mole. So notice that the units grams of NaOH cancel. So right now we have moles. So now we got to divide it by the 0.3 kilograms of solvent. So whenever you have moles on top and kilograms of solvent on the bottom, that's going to give you the molality. So 25 divided by 40 is about 0.625. That's how many moles we have. And if we take that number of moles divided by 0.3 kilograms, we get a molality of 2.08. So D is the right answer. Number 33. Calculate the molality of a 24% HCl aqueous solution. So how would you do that? When you have a mass percent, a 24% HCl solution, what you need to realize is that you have 24 grams of HCl per 100 grams of solution. Now the solution has two components, the solute and the solvent. The solute plus the solvent is equal to the solution. Now because we have an aqueous solution, the solvent is H2O. So 100 minus 24 is 76. Therefore, we have 76 grams of H2O. Now granted, the ratio is what is important. So we can also have 48 grams of HCl, but that will correspond to 200 grams of solution. Or we can have 12 grams of HCl for every 50 grams of solution. But the best way to answer this problem is convert this percentage into grams and base it out of 100. So if you have a 30% HCl solution, that means you have 30 grams of HCl, 70 grams of water, and 100 grams of solution. If you do it that way, then it's going to be easy to get the answer. So now it's going to be similar to the last problem that we did previously, number 32. So let's start with 24 grams of HCl, and let's convert it to moles. Chlorine has a molar mass of 35.45, and for hydrogen it's like 1.008. So the molar mass for HCl, it's about 36.458 grams per 1 mole. So these units cancel. And the last thing we need to do is divide by the kilograms of solvent. We have 76 grams of solvent. To convert grams to kilograms, divide by 1,000, or move the decimal 3 units to the left. So 76 grams is equal to 0.076 kilograms. So 24 divided by 36.458, that should give you 0.658 moles, and then divide that by 0.076. So the answer for this problem is 8.66. That's the molality of the solution. So that's how you can convert mass percent into molality. 34. Determine the molarity of a 27% HI solution with a density of 1.21 grams per milliliter. So we know molarity is the moles of solute over the liters of solution. So if we can have the grams of solution, we can use the density to get the milliliters of solution and then the liters of solution, so we can find the molarity. But let's write down what we have. So in a 27% solution, that means that there are 27 grams of HI for every 100 grams of solution. And if we subtract the two numbers, 100 minus 27, that means that we have 73 grams of water. But we probably don't need that for this problem since we're not looking for molality. Now, we can easily get moles of solute by converting grams of HI into moles, but we need the liters of solution. So 100 grams of solution, let's convert that to liters. So the density is 1.21 grams per milliliter. That means that 1 milliliter of solution has about 1.21 grams. So notice that the grams cancel. And now we can convert milliliters into liters. There's 1,000 milliliters per 1 liter. So 100 divided by 1.21 divided by 1,000, we have a volume of 0.0826 liters. So now we can calculate the molarity. So starting with 27 grams of HI, let's convert it to moles. Iodine has a molar mass of 126.9 plus 1.008 for hydrogen, so the molar mass is 127.908. Now that we have moles of solute on top, all we need to do is divide it by the liters of solution to get molarity. So 27 divided by 127.908, you should get 0.211, and then divide that by 0.0826, and the final answer is about 2.55. So answer choice C is the right answer. It really rounds to 2.56, but C is the closest answer. Number 35. Determine the boiling point of an aqueous solution of aluminum chloride. So in this problem, we have the molality, we have the Kb. The equation that we need is the temperature of the solution minus the temperature of the solvent is equal to Kb times the molality times the Van Hoff factor. You might have seen this equation as delta T equals Kb times m times I. Just keep in mind that delta T is the temperature difference between the boiling point of the solution and the boiling point of pure water. Now, the only thing that we need in this equation is the Van Hoff factor. What is the Van Hoff factor for this problem? Well, look at aluminum chloride. How many ions can aluminum chloride dissociate into? Aluminum chloride contains an aluminum plus 3 ion and 3 chloride ions. So it has a total of 4 ions. So therefore, the Van Hoff factor is 4. 1 mole of aluminum chloride will generate 4 moles of ions. So now if we plug in the numbers that we have in this equation, this is what we'll have. The temperature of the solution minus the temperature of pure water, which is the boiling point of pure water is 100 degrees Celsius. Kb, that's 0.512. The molality is 1.24. And the Van Hoff factor is 4. So now we have to solve for the boiling point of the solution. So 0.512 times 1.24 times 4 will give us a value of 2.5395. So now we just have to add 100 to both sides. So the boiling point is going to be 102.5 if you add 100 to 2.5. So answer choice C is the right answer. So keep in mind, whenever you add salt to water, the boiling point goes up. So let's say if you have pure water, which has a boiling point of 100. Once you add salt to it, the boiling point could increase to like maybe 102. The freezing point of pure water is about 0 degrees Celsius. And if you add salt to that, the freezing point goes down. It could be like maybe -5 or -10, depending on how much you add. So the equation that we dealt with is called boiling point elevation, because anytime you add salt to water, the boiling point goes up. And there's another equation which is very similar. It's delta Tf is equal to negative Kf m times I. This is called freezing point depression because When you add salt to water, the freezing point or melting point decreases. It becomes less than zero. And this is why salt is added to icy roads, because whenever you add salt to ice, the melting point of ice decreases, and so it's easy for ice to melt whenever its salt is added to it. So those are some things that you want to keep in mind as it relates to this topic. Number 36. 32 grams of an unknown non-electrolyte solute was dissolved in 345 milliliters of solution. The osmotic pressure of the resulting solution is 27.1 atmospheres at 298 Kelvin. Calculate the molar mass of the unknown solute. So the important expression that we have is osmotic pressure. Pi, which is osmotic pressure, is equal to the molarity times the gas constant times the temperature times the Van Hoff factor. Now, in order to find the molar mass, we need the grams, and we need to divide that by the moles. Now, we already have the grams. It's 32 grams. That's the grams of the solute. In order to find moles, we've got to find molarity. So we can rewrite the equation like this. Pi is equal to moles over liters times RT times I. So our goal is to solve for the moles. So let's plug in what we have. The pressure is pi, which is 27.1. And for the moles, we're going to call it X. That's what we're looking for. Now the liters is the volume. We have 345 milliliters of solution. To convert that into liters, we've got to divide that by 1,000. So that's equal to 0.345 liters. And then R is the gas constant. That's 0.08206. The other one, 8.3145, that has units joules per mole Kelvin, but we need to use this one because it has the units ATM in it, and it has liters as well. The temperature is 298 Kelvin, and the Van Hoff factor for a non-electrolyte is always equal to 1 because non-electrolytes do not dissociate into ions. So now we need to do math to solve for X. So let's multiply both sides by 0.345. So these numbers will cancel. So on the left, if we multiply 27.1 times 0.345, we should get 9.3495. And that's equal to 298 times 0.08206. So that's going to give us 24.45388x. So if we divide both sides by 24.45388, x is equal to 0.3823 moles. Now, in order to find the molar mass, we need to take the grams, which is 32 grams, and divide it by the number of moles. And so we get 83.7 grams per mole. And that's it. So D is the right answer. Number 37. 35.1 grams of sodium chloride is dissolved in 200 grams of water. The vapor pressure of pure water is 23.76 torr at 25 degrees Celsius. Calculate the vapor pressure of the solution. The equation that you need for this problem is the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. Now, we already have the vapor pressure of the solvent. For pure water, it's 23.76. But what we need is to find the mole fraction of the solvent. So let's convert everything into moles. So we have 35.1 grams of sodium chloride. And the molar mass for NaCl, for Na it's about 23, and for chlorine it's about 35.45. So that gives us a molar mass of 58.45 grams. Now, we need to take into account that sodium chloride has a Van Hoff factor of 2. That means there's 2 ions per formula unit. And since vapor pressure is a colligative property, which is a property that is dependent on the number of solute particles, we have to find the moles of ions rather than the moles of sodium chloride. So there's 2 moles of ions per 1 mole of NaCl. So we have to multiply the moles of NaCl by 2. So 35.1 divided by 58.45 multiplied by 2, you should get 1.2 moles of ions. Now, let's convert the 200 grams of water into moles. Water has a molar mass of about 18.02 grams per mole. So for water, we have 11.1 moles of H2O. So now we can find the mole fraction of the solvent, which is the mole fraction of water. The mole fraction of water is the moles of water, which is 11.1, divided by the total moles, which is the moles of water plus the moles of the solute particles. So the mole fraction that you should get for water is about 0.902. So now we can use this equation. So the vapor pressure of the solution is equal to the mole fraction of water, which is the solvent, times the vapor pressure of the solvent, which is 23.76 torr. So the answer that you should get is 21.43 torr. So answer choice B is the correct answer for this problem. Number 38. Calculate the average atomic mass of boron if the relative percent abundance of isotopes B10 and B11 are 19% and 81% respectively. So what we need to do is we need to take a weighted average of the mass of the isotopes. So the equation that you need looks something like this. So the weighted average is equal to the first mass times the percentage that corresponds to that mass plus the second mass times its respective percentage. So the first mass, isotope 10 or B10, has a mass of 10, and the percentage for that is about 19%, which as a decimal, that's 0.19. You just divide 19 by 100. Now the second mass, B11, has an atomic mass of 11, and 81% as a decimal is 0.81. So at this point, all you need to do is really you just got to type it in the calculator. So you should get, for your final answer, 10.81. So that's the average atomic mass of boron. So B is the answer. Number 39. 15.5 grams of magnesium metal reacts with excess nitrogen gas to produce 18.2 grams of magnesium nitride. Calculate the percent yield of magnesium nitride. So the first thing we need to do is write a balanced reaction. So magnesium is Mg, and it's going to react with nitrogen gas, which is N2, it's diatomic, and that's going to produce magnesium nitride. So magnesium nitride is an ionic compound, so we can't just write MgN. You have to make sure you write it in the correct ratio. Magnesium is in group 2, so as an ion, it has a +2 charge. And nitrogen is in group like 15 or 5A, and it has a minus charge, a -3 charge. So you got to use like this crisscross method where the 2 is going to go here, the 3 is going to go there. And so the correct formula is Mg3N2. So now we need to balance the reaction. We have two nitrogen atoms on both sides, so we don't have to worry about that. All we need to do is put a 3 in front of Mg. So it's 3, 1, 1. So now this problem wants us to find the percent yield. The equation for percent yield, it's equal to actual yield divided by theoretical yield times 100%. Now usually the actual yield is given to you if you need to find a percent yield. And the yield is based on a product. So notice that they mention, or this problem mentioned that 18.2 grams of magnesium nitride was produced. So that's the actual yield for this particular reaction. So we got to find the theoretical yield. The theoretical yield is the maximum amount of mass, or grams, it could be in moles too, the maximum amount of product that can be produced in a reaction. So we know nitrogen gas is the excess reactant. That means magnesium metal is the limiting reactant. So let's go ahead and solve this problem. So we need to convert grams of magnesium to grams of magnesium nitride, and that's going to be the theoretical yield. So let's start with 15.5 grams of magnesium, and let's convert it to moles. In order to convert it to moles, we need to use the molar mass. For magnesium, it's about 24.31 grams. So the units grams cancel. So now we can convert moles of magnesium to moles of magnesium nitride. So we need to use the molar ratio. It's a 3-to-1 ratio. So for every 1 mole of magnesium nitride that's produced in a reaction, 3 moles of magnesium are consumed. The last step is to convert magnesium nitride from moles to grams. So we need to find the molar mass. So we have 3 magnesium atoms, so it's going to be 3 times 24.31, and 2 nitrogen atoms, which is 2 times 14.01. And I'm going to use the calculator for this. If I did that correctly, that is equal to 100.95. So it's 100.95 grams per 1 mole of magnesium nitride. So moles of Mg cancel, and moles of MgN3 cancel. So now we have the grams. So to calculate it, it's going to be 15.5 divided by 24.31. Take that result and then divide it by 3, and then multiply it by 100.95. If you did it correctly, you should get this answer. This is the theoretical yield of the product. So that's the maximum amount of magnesium nitride that we can get if all of the 15.5 grams of magnesium metal reacts. That's the most that we can produce in this reaction. But now, according to this problem, we only got 18.2 grams of magnesium nitride out of the maximum 21.455 grams. So this is how you calculate percent yield. It's going to be the actual yield, which I'm going to represent as AY, divided by the theoretical yield, and then times 100%. So if you plug those numbers in, the answer should be 84.8%. So that's the answer to the problem. So answer choice C is the correct answer for this problem. Number 40. Calculate the pH of a 5.43 times 10 to the minus 3 mole solution of barium hydroxide. The first thing we need to do is find the concentration of hydroxide. If we can do that, we can find the pOH and then we can find the pH of the solution. So barium hydroxide dissociates into the barium plus 2 ion and 2 hydroxide ions in water. Barium hydroxide is fairly soluble in water. And so notice that we have a 1 to 2 ratio between barium hydroxide and the hydroxide ions. So if you wish to find the concentration of hydroxide, we need to multiply the concentration of barium hydroxide by 2 because we have a 1 to 2 ratio. But if you wish to convert it, you can write it like this: 5.43 times 10 to the minus 3 for barium hydroxide, and then you can multiply it by the 2 to 1 ratio. So therefore, the concentration of hydroxide is about 0.01086 m. So now we can find the pOH, which is negative log of the hydroxide concentration. So if you type in negative log 0.01086 in your calculator, you should get a pOH value of 1.964. Now another equation that you want to know is that the pH plus the pOH must add to 14 whenever water is a solvent. So therefore, the pH is 14 minus the pOH, or 14 minus 1.964. And that's going to give you the answer. So the pH is equal to 12.04. Answer A is the right answer. Number 41. The average atomic mass of chlorine is 35.45 atomic mass unit, which is based on isotopes Cl35 and chlorine-37. Calculate the relative percent abundance of the isotope Cl35. So this is the reverse of the other question that was similar to this. So in the last example, we're looking for the average atomic mass. In this problem, they gave it to us. Now the equation that we wrote last time was something like this. It was the average atomic mass is equal to the first mass times the percentage that is associated with that mass, plus the second mass times that percentage. And if there's another one, it could be plus M3P3 plus M4P4. And it can keep on going forever depending on how many isotopes you have. So that's a weighted average. Now, we're looking for the percentages, P1 and P2. We're given the average. We know the average is 35.45. And the mass of the first isotope is 35. We don't know the percentage, so I'm going to leave a blank space. And the mass of the second isotope is 37. Now, we have two numbers, and they're percentage based, so they should add up to 100%. 100% as a decimal is equal to 1. So we're going to say this is x because we're looking for the percentage of Cl35, and then the other one has to be 1 minus x. So let's say if it's 30% and 70%. X could be like 30%, which is 0.3, and then the other one 70%, which will be 1 minus 0.3, that's 0.7. So when you add x and 1 minus x, the x's cancel, x plus negative x is 0, and you get 1, which is the total percentage, 100. So whenever you get a question, always set up this way. One of them is going to be x, and the other is going to be 1 minus x. So now let's solve for x. So on the right side, it's going to be 35x, and now we need to distribute the 37. So 37 times 1 is 37, and 37 times negative x is negative 37x. So now let's combine these two like terms. So 35x minus 37x is negative 2x. And at this point, we can subtract both sides by 37. So 35.45 minus 37, you should get negative 1.55, and that's equal to negative 2x. So now we can divide both sides by negative 2. So negative 1.55 divided by negative 2, that is equal to 0.775. That's the value of x. So as a percentage, 0.775 is 100%. Multiply 0.775 by 100. I mean, I didn't meant to say 100%. 0.775 times 100 is 77.5%. So that's how much, that's the percentage of the chlorine-35 isotope. So for chlorine-37, if you want to find it, it's 100 minus 77.5. So chlorine-37 has a percentage of 22.5%. But now, is the answer A or is it C? Since we're looking for chlorine-35, the answer is C. It's 77.5%. Now notice that the average atomic mass, which is 35.45, it's closer to the Cl35 isotope. It's further away from the Cl37. Because the average is closer to chlorine-35, that means we have more of the chlorine-35 isotope than the chlorine-37. We have 77.5% of the chlorine-35 isotope, but only 22.5% of the chlorine-37 isotope, because the average is closer to Cl35. If the average was 36, like right in the middle between 35 and 37, it would be a 50-50 ratio. But since it's not right in the middle, since it's closer to Cl35, we have more of the Cl35 isotope. So answer choice C is the right answer for this problem. Number 42, how many molecules of sulfur tetrafluoride are there in a 25-gram sample? So we need to convert from grams to moles and moles to molecules. Let's begin. Let's start with 25 grams of SF4 over 1. Now we need to find the molar mass of sulfur tetrafluoride. Now the atomic mass of fluorine is 19. We're going to multiply that by 4. And for sulfur is about 32.06. So if you add up the atomic mass, let me write it here, 32.06 plus 19 times 4, you should get 108.06. So that's how you can convert from grams to moles. Now, in our next step, we're going to convert from moles to molecules using Avogadro's number. So 1 mole is equal to 6 times 10 to the 23 molecules of sulfur tetrafluoride. So now we just have to plug in these numbers and we should get the answer. So it's just 25 divided by 108.06 times 6.02 times 10 to the 23rd. So the answer that you should get is 1.39 times 10 to the 23rd molecules of SF4. So the correct answer is B. Number 43. How many atoms of fluorine are there in a 25-gram sample of sulfur tetrafluoride? So this question is very similar to the last one, but now we're looking for atoms instead of molecules. So let's start from the very beginning. Let's start with 25 grams of sulfur tetrafluoride, and let's convert it to moles. So the molar mass is going to be the same. It's going to be 108.06 grams per 1 mole. So the units grams cancel. So now, just like before, we're going to convert it to molecules. So this is going to be 6.02 times 10 to the 23 molecules per 1 mole of sulfur tetrafluoride. So these units will cancel. Now, there's an extra step that we need to take into account. We need to convert molecules of sulfur tetrafluoride into atoms of fluorine. So 1 molecule of SF4 has 4 atoms of fluorine, yes? So all we need to do is take our previous answer and multiply by 4. So if you type this in, you should get 5.57 times 10 to the 23rd atoms of fluorine. So C is the right answer. Number 44. Determine the empirical formula of a compound that is made up of 55.8% carbon, 7.03% hydrogen, and 37.17% oxygen. So percentages is based out of 100. What we're going to do is convert the percentage into grams. We're just going to make them grams. And it's going to work out this way if you do it, because this is mass percent. So we have 55.8 grams of carbon. Our goal is to convert it to moles. If we can get the moles of every element, we can find the empirical formula. According to the periodic table, the molar mass of carbon is about 12 grams. So we'll use 12.01. So 55.8 divided by 12.01, you should get 4.646 moles of carbon. So now let's do the same thing for hydrogen. So we have 7.03 grams of hydrogen, and we're going to convert it to moles. The molar mass for hydrogen is about 1.008. So there are about 6.97 moles of hydrogen. And now finally, let's do the same for oxygen. The molar mass for oxygen is about 16 grams. So you should get 2.32 moles of oxygen. So now we need to divide each of these numbers by the smallest of the three numbers that we got. The smallest one is 2.3. So let's divide everything by 2.3. So you can see 4.6 divided by 2.3 is roughly about 2. Now at this point you want to round it to the nearest whole number. So this is equal to 2, this is about 3, and this is 1. So now we can write the formula. C2H3 and O1. So it's C2H3O or O1. So D is the right answer. (45) The empirical formula of a compound is CH2O. Determine the molecular formula of this compound given that its molar mass is 180 grams per mole. So how would you do this problem? The first thing you need to do is find the molar mass of the empirical formula. So it's CH2O. So carbon has a mass of 12, and for hydrogen it's about 1. We're going to use just whole numbers for this example. And for oxygen is 16. If we add these three numbers, 12 plus 2 is 14, 14 and 16 is 30. So that's the molar mass of CH2O. Now the next thing you want to do is take 180 and divide it by 30. So 180 divided by 30 is equal to 6. You can cancel the zeros. 18 over 3 is 6. So what you need to do is multiply the subscripts of the empirical formula by 6. So if you do that, you're going to get C6H12O6, which is the molecular formula of glucose. And so D is the right answer. Number 46. A 4.532 gram compound consisting only of carbon and hydrogen produce 13.851 grams of CO2, and 6.798 grams of water during combustion analysis. Determine the empirical formula of this compound. Anytime you need to find the empirical formula, get the moles of the elements that are in that formula. So the formula only consists of carbon and hydrogen, so we just need to find the moles of those two elements. So we have 13.851 grams of carbon dioxide. Let's convert that into moles. So the molar mass for carbon dioxide, carbon's about 12, oxygen is 16 times 2, so 32 plus 12. It's about 44. But carbon's like 12.01, so it's like 44.01. So now we can convert to moles of carbon. There's only one carbon atom in a CO2 molecule, so there's only 1 mole of carbon per 1 mole of CO2. It's a 1-to-1 ratio. So therefore you should get 0.315 moles of carbon. So now let's start with water. We have 6.798 grams of water. And water has a molar mass of, let's see, so it's 16 plus 1.008 times 2. You should get about 18.016 grams for the molar mass of water. Now notice that there are 2 hydrogen atoms in a single water molecule. So therefore it's a 1-to-2 ratio. So there are 2 moles of hydrogen per 1 mole of H2O. So 6.798 divided by 18.016 times 2, you should get 0.7547 moles of hydrogen. So let's divide by the smaller of the 2 numbers, which is about 0.315. So these 2 numbers are the same, so we should get 1. And 0.7547 divided by 0.315 is about 2.4. So we have a 1 to 2.4 ratio. So what do you think we should do in this case? We need to multiply both numbers. That's going to give us a whole number. So if you do 2.1 times 2 in your calculator, you're going to get 4.8. 2.4 times 3, you get 7.2. 2.4 times 4, you get 9.6. But if you take 2.4 and multiply it by 5, you'll get 12. So right now we have this as the empirical formula. C1, 1 is associated with carbon, and H 2.4. If we multiply both subscripts by 5, we're going to get whole numbers. It's going to be C5, H12. And that's what you want to do in this scenario. So the correct answer for this problem is C. If you take 12 divided by 5, you get that 2.4 number. If you do like 8 divided by 3, it won't be 2.4. It's going to be like 2.6. And 12 divided by 7, that's 1.7. So only answer choice C has that 1 to 2.4 ratio. So C is the right answer. Number 47. 40 grams of iron metal reacts with 20 grams of oxygen gas to produce iron 3 oxide. Calculate the mass of the excess reactant that remains after the reaction is complete. So in this problem, we need to find the limiting reactant. Once we ID the limiting reactant, we need to take the grams of the limiting reactant and convert it to the grams of the excess reactant. That's going to tell us how many grams of excess reactant was actually consumed in a reaction. So then we just need to take the difference of the original amount of the excess reactant minus the amount that was consumed in the reaction, and that's going to tell us how much is left over. So let's begin. First, let's write a balanced chemical equation. So iron is Fe. It reacts with oxygen gas, which is diatomic, it's O2. And iron 3 oxide, how can we write the correct formula for it? So the Roman numeral 3 tells us that iron has a +3 charge. And oxygen, which is in group 16A, it has a -2 charge. So using this crisscross method, the correct formula should be Fe2O3. So now let's balance the reaction. Notice that we have an even number of oxygen atoms on the left and an odd number of oxygen atoms on the right. So let's find the least common multiple. The least common multiple of 2 and 3 is 6, so we're going to need a 2 here and a 3 on the left side. So we have 6 oxygens on both sides. Now we have 4 Fe atoms on the right, so we got to put a 4 on the left. So now it's balanced. To find out the limiting reactant, let's convert the grams into moles, and we need to divide the moles by the coefficient in the balanced reaction. Whichever reactant has the lowest mole per coefficient ratio, that is going to be the limiting reactant. So we have 40 grams of Fe, and the molar mass of iron is about 55.85. And the coefficient is 4 based on this number. So 40 divided by 55.85, and then take that result divided by 4. You should get 0.179 moles per coefficient. Now let's do the same for oxygen. So we have 20 grams of oxygen gas, and the molar mass for oxygen is it's 16 times 2, so that's 32. And the coefficient in front of oxygen is a 3, so we're going to divide it by 3. So we should get 0.208 moles of O2 per coefficient ratio. So we could see that Fe has the lowest mole per coefficient ratio. So that tells us that Fe is the limiting reactant. So let's make some space. So I'm going to write Lr for the limiting reactant and Er for the excess reactant. So now that we know which one is limiting, let's convert the grams of the limiting reactant to the grams of the excess reactant. So let's start with 40 grams of Fe. We know the molar mass is 55.85. So grams of Fe can now be canceled. So now we need to convert moles of Fe to moles of O2 using the molar ratio. So for every 3 moles of O2 that reacts, 4 moles of Fe reacts with it. So now moles of Fe cancel. And now we need to convert moles of O2 into grams of O2, which we know the molar mass to be 32 grams per 1 mole. So 40 divided by 55.85 times 3 divided by 4 times 32. I got 17.19 grams of O2. So what this means is that 40 grams of iron will react completely with 17.9 grams of O2. So since this is the amount that is consumed in the reaction, and since we started with a total of 20 grams of O2, that means that the amount that's left over, or the amount that remains after reaction, is the difference between those two numbers. So 20 minus 17.19 will give us the mass of the excess reactant that remains. And that answer is equal to 2.81 grams of O2. So answer choice A is the correct answer. Number 48, 30 grams of aluminum metal reacts with 38 grams of fluorine gas, I forgot the word of, to form aluminum fluoride. calculate the theoretical yield of aluminum fluoride. So first let's write the balance reaction. So we have aluminum metal, and it reacts with fluorine, which is diatomic, and aluminum fluoride is an ionic compound. It's composed of a metal and a nonmetal. So we need to balance the charges first. Aluminum is in group 13 or 3A of the periodic table, and so it forms a +3 charge as an ion. And fluoride has a -1 charge. So using this method, the correct formula should be AlF3. So now let's balance the reaction. The least common multiple of 2 and 3 is 6, so we need to put a 3 in front of F2 and a 2 in front of AlF3, and a 2 here as well. So now notice that we have the grams of both reactant, the grams of aluminum metal and of fluorine gas. When you're given the moles or grams of both reactants, you need to know which one is the limiting reactant. However, we don't have to find it right now. Instead of identifying the limiting reactant, we can convert both of them into the grams of aluminum fluoride, and whichever of those two numbers gives us a lower theoretical yield, that is going to be the correct answer. And the reactant that gave us that answer will be the limiting reactant. So we're going to do it this way instead, because we have to find the theoretical yield anyway. You can also use the other method in which we found the lowest mole per coefficient ratio. That's going to work fine as well. But it's up to you to choose whichever method you think will work faster. So let's start with 30 grams of aluminum, and let's convert it to the grams of aluminum fluoride, the product. So the molar mass of aluminum is about 26.98 based on the periodic table. So grams cancel. And the molar ratio between aluminum and aluminum fluoride, it's a 2:2 ratio, or 1:1. So for every 2 moles of aluminum fluoride that reacts, or that is produced in a reaction, 2 moles of aluminum reacts. Now the last thing we need to do is convert moles of aluminum fluoride into grams. So we need the molar mass. So fluorine's about 19. If we multiply that by 3, we get 57. And then we're going to add 26.98 to it. So the molar mass of AlF3 is about 83.98 grams. So now let's calculate the theoretical yield, or the potential theoretical yield. So 30 divided by 26.98 times 83.98. 2 over 2 is just 1, so we could ignore that. So we're going to get an answer of 93.38 grams of aluminum fluoride. So what this means is that if all of the 30 grams of aluminum reacts, the maximum yield of aluminum fluoride that you can get is 93.38 grams. You can't get more than that. So if aluminum is if it's the limiting reactant, then that would be our answer. But we don't know if it's the limiting reactant. So now let's try the other one. Let's start with 38 grams of fluorine gas, and let's convert it to moles. So the molar mass of F2, that's 19 times 2, it's about 38. And the molar ratio, it's 3:2. So for every 3 moles of F2 that reacts, 2 moles of AlF3 are produced. And now let's convert moles of AlF3 into grams. We already have the molar mass, which we know to be 83.98. That number is not going to change. So grams cancel, moles cancel, and moles of AlF3 cancel. So 38 over 38, that's just 1, times 2 divided by 3 times 83.98. So you should get 55.99 grams of aluminum fluoride. So because this number is smaller, because 56 is less than 93.4, this is the right answer. This is the theoretical yield. Because 56 comes before 93.4. So as the reaction proceeds, once we get 56 grams of aluminum fluoride, that means all of the fluorine gas reacts. So aluminum it can't react anymore because there's no more fluorine gas to react with. So the reaction stops at this point. So whichever is the lower of the two numbers, this is the theoretical yield. That's the most that we can get in this reaction. And that means that fluorine, which gave us that answer, is the limiting reactant. And the other reactant, the aluminum, is the excess reactant. So the answer for this problem is answer choice D. Number 49. Which of the following is a homogeneous mixture? Is it air, oil, and water, or sodium chloride and water? So let's start with oil and water. Oil and water do not mix. If you try to put them together, typically the water layer is going to be on the bottom, and on top you're going to have the oil layer. And if you could see two distinct phases, it's going to be a heterogeneous mixture and not a homogeneous mixture. So number 2 is eliminated. Now, if you were to mix sodium chloride and water, the two would mix, and you would see one clear solution. And because you would see one clear solution and not two distinct parts, it's going to be a homogeneous mixture. The sodium chloride ions are uniformly distributed throughout water. So therefore, number 3 is correct. And air is a homogeneous mixture of gases. All of the gases are evenly distributed throughout one another. And so this is also homogeneous. It's not heterogeneous. You're not going to have nitrogen on one side of the room and oxygen on the other. They're completely evenly distributed within a container or in a given space. So 1 and 3 is the right answer. Number 50, which of the following is not a representative element? Representative elements are elements in the first two columns, group 1 and group 2, and then like group 13 and group 18. Transition metals and intertransition metals are not representative elements. So sodium is in group 1, so it is a representative element. Aluminum is in group 13, that's a representative element. Sulfur is in group 16, but iron is a transition metal, so this is not a representative element. So D is the answer. Now make sure you are aware of the names of the different columns in the periodic table. So for example, in the first column, you have your alkali metals. This is like lithium, sodium, potassium. And then in the second column, you have the alkaline earth metals, such as magnesium, calcium, strontium, barium, beryllium. Then in between those two columns, and then group 13, this is the transition metals. So then you have like group 13, like boron, aluminum, and then you have carbon, silicon, germanium, and then like nitrogen, phosphorus, arsenic, I think antimony. Now after that column, you have the chalcogens, like oxygen, sulfur, selenium, Te, and then you have the halogens, fluorine, chlorine, bromine, nitrogen, and then you have the noble gases like helium, neon, argon, krypton, xenon. On the left side you have metals, and on the right side you have the nonmetals. Metals like to give away electrons. Nonmetals, they like to acquire electrons. So metals tend to be reducing agents. Nonmetals tend to be oxidizing agents. The most reactive metals are like the alkali metals. And the second most reactive are the alkaline earth metals. Over here, you have the inner transition metals. So the transition metals and the inner transition metals are not representative elements. Everything else is a representative element. The noble gases, they're inert. So chemically, they're not reactive. They're very stable. Now, the most reactive nonmetals are the halogens. I think I wrote N here. This is supposed to be iodine. So the halogens, they're very reactive. They really want electrons. And then you have the chalcogens, which are fairly reactive, but not as reactive as the halogens. Now, between the metals and the nonmetals, you have the metalloids. So in the periodic table, there's like this line that looks something like this. The most common metalloids that you need to know are like silicon and germanium. Some other ones would be like boron, arsenic, antimony, but not aluminum. Those are metalloids. A metalloid is in between a metal and a nonmetal. Metals, they like to conduct electricity. They also conduct heat. They're malleable, they're ductile. They can be pulled into wires, they can be hammered into sheets. So those are some properties of metals that you need to be familiar with. Nonmetals, they do not conduct heat or electricity. They're poor conductors. In fact, they're insulators. And nonmetals tend to be soft. They form like molecular solids. And they usually have like low boiling and melting points. The metalloids, like silicon and germanium, they're not insulators and they're not like good conductors. They conduct electricity just a little. The metals conduct electricity very well. Nonmetals do not conduct electricity at all. Metalloids, they conduct a small amount of electricity. But if you heat up a metalloid, or if you shine light on it, the electrical conductivity goes up. In contrast, if you were to heat up a metal, it actually becomes less conductive. If you can supercool a metal, the conductivity will greatly increase. So those are some properties of elements that you want to be familiar with. Make sure you know the names of the groups, like the columns in the periodic table, and make sure you know the properties of metals, nonmetals, and metalloids, because sometimes you might be tested on it one way or the other. Number 51. Calculate the mass of sodium fluoride required to make a 0.35 molar solution of sodium fluoride in 200 milliliters of water. So let's solve this problem using a conversion or stoichiometry. Let's start with molarity. We can write molarity as moles per liter. So a 0.35 molar solution tells us that there are 0.35 moles of sodium fluoride in a 1 liter solution. So now we can multiply by liters to cancel liters. So 200 milliliters, if we want to convert that to liters, divide by 1,000, or move the decimal 3 units to the left. So 200 milliliters is about 0.2 liters over 1. So the units liters cancel. Now the last thing we need to do is convert moles to grams. So we need to find the molar mass of sodium fluoride. Sodium has a molar mass of about 23, and for fluorine, according to the periodic table, it's about 19. So that means the molar mass is about 42 grams per 1 mole. So now we can get the answer. So 0.35 times 0.2 times 42 is equal to 2.94 grams of sodium fluoride. So that's the answer for this problem. Number 52, which of the following is a chemical change? Is it A, B, C, or D? So let's look at the first one, distillation. Distillation is a process that separates one component of a mixture from another, and it does so by converting one of the lower boiling point liquids into a gas. Anytime you go from a liquid to a gas, that's like vaporization, and that's a physical change, not a chemical change, so A is out. Melted ice, so we're going from a solid to a liquid. That's a physical change. When ice converts into water, the chemical formula remains H2O. So as long as the chemical formula is the same, it's a physical change. If the chemical formula changes, then it's a chemical change. So like boiling water, going from a liquid to a gas, or a liquid into steam, we still have H2O, so it's a physical change. But burning coal, that's a chemical change. Coal, for the most part, is mostly carbon, and when you burn it in oxygen, you get a new substance, carbon dioxide. Since we're changing the chemical formula, it's going to be a chemical change, so C is the right answer. Number 53, which of the following compounds is insoluble? So you need to know your solubility rules for this. All of the group 1 metals like lithium, potassium, and sodium, these are always soluble. So C is eliminated because we have sodium, it's soluble. Also, ions such as nitrate, ammonium, acetate, when you see these ions, they're always soluble. So B is eliminated, silver nitrate, that's soluble. A is out, lead acetate, that's soluble. If you know this, that's half of the solubility rules. So the one that's insoluble is magnesium sulfide. But let's go over some basic rules as well. The halides like chloride, bromide, iodide, for the most part, those ions are soluble with some exceptions. The exceptions are if they're bonded to Ag+, Pb+2, or like mercury. If you see them with these ions, it's going to be insoluble. But other than that, the halides for the most part are soluble. Sulfates are usually soluble with the exception of certain group 2 elements such as calcium, barium, strontium. Then they will be insoluble. Now, these other ions I'm going to show you are usually insoluble, like hydroxide, sulfide, carbonate, phosphate. These are usually insoluble unless they're paired with an ion that's like always soluble. So the exception is if they're paired with a group 1 metal like sodium or potassium, then it's soluble. Or if they're paired up with like NH4+, which is always soluble, then these will be soluble. But for the most part, this group is fairly insoluble. However, with hydroxides are soluble with group 1 or group 2 metals. So for hydroxides, if you see like calcium hydroxide, barium hydroxide, or strontium hydroxide, then it's going to be soluble. Magnesium hydroxide is, for the most part, insoluble. But if you see hydroxide with any other metals, like a transition metal or like aluminum, it's going to be insoluble. But if it's like with group 1 or group 2, starting with calcium and anything below calcium in group 2, then the hydroxides are soluble. Other than that, the rest, sulfide, carbonate, phosphate, usually insoluble. So those are some basic rules that you want to keep in mind as relates to solubility. Number 54. Which of the following species is the reducing agent in the reaction shown below? So what we need to do first is identify the oxidation states. Any element in its natural state is or has an oxidation state of 0. So elemental chromium and hydrogen gas has an oxidation state of 0. Chlorine is usually -1. Now, in HCl, because chlorine has a minus charge, the hydrogen has to have a plus charge. So hydrogen is +1. And in CrCl2, because we have 2 chloride ions, therefore the chromium must have a +2 charge to neutralize these 2 negative charges. So chromium is +2. So which species is oxidized and which one is reduced? If the oxidation number goes up, it's oxidation. If it goes down, it's reduction. So chromium was oxidized. It went from 0 to 2. The oxidation number increased. Whenever a substance is oxidized, it lost electrons. Now hydrogen was reduced because it went from +1 to 0. So if the oxidation state decreases, it's reduction. The substance on the left that was oxidized is the reducing agent. And the substance that was reduced is therefore the oxidizing agent. And that's how you find it. Now, if this seems confusing, Chromium is the reducing agent because it caused the other substance, HCl, to be reduced. HCl is the oxidizing agent because it caused the other substance, chromium, to be oxidized. At least that's the way I see it. But for this problem, chromium is the reducing agent. So the correct answer is A. Number 55. Calculate the new volume of a 245 milliliter sample of gas if the temperature increased from 25 to 83 degrees Celsius. So in this problem we have T1, T2, V1. We're looking for V2. Let's use the combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. Now we only need volume and temperature. The pressure, we're going to assume that it's constant, so we could eliminate P1 and V1. So now what we have is Charles' law, and so all we need to do is plug in what we have. The first volume is 245 milliliters, and the temperature that corresponds to that volume is 25 degrees Celsius. But for this equation to work, the temperature has to be in Kelvin. So to convert Celsius into Kelvin, let's add 273. So that's about 298 Kelvin. We're looking for the new volume, V2. The second temperature is 83. So let's add 273 to 83. And so that's about 356 Kelvin. So to solve for V2, what we could do is cross multiply. So 245 times 356 is about 87,220. And if we multiply the other two, we could just write it as 298 V2. So now we need to divide both sides by 298. So V2 is equal to, it's about 292.7 milliliters. Because V1 was in milliliters, V2 is going to be in milliliters. So we can round that to 293. So answer choice B is the right answer. Number 56. Which of the following represents the correct formula for copper 1 sulfide? So to do this, make sure you know your polyatomic ions. Feel free to go to Google Images, look it up, and commit that to memory. So right now there are three types of ions that we have. We have S, which has a -2 charge, SO3 2-, and SO4 2-. That's irrelevant to this problem. S2- is known as sulfide. When the ending is IDE, it's not polyatomic, it's a monoatomic ion. It doesn't have oxygen. Now, SO3 2- is known as sulfites, and SO4, which has one extra oxygen, is sulfates. 8 always has one more extra oxygen than I. So, since we're looking for sulfite, we need SO3, which means we can eliminate C and D. So now we need to choose between A and B. So we got to find out which one has an oxidation state of 1. Let's start with B. In CuSO3, we can write it as Cu plus SO3 equals to 0. Now we don't have to separate the sulfur and the oxygen in order to find the oxidation state on copper, because we can replace the entire SO3 with a -2 because that's the net charge of SO3. If you solve for copper, you'll see that it has an oxidation state of +2. So B is not the answer. Now let's do the same for the other compound. If you want to find the oxidation state, write an equation. We have 2 copper atoms plus 1 SO3 ion, and the net charge should equal 0 because there's no net charge in this compound. It's just Cu2SO3. If there was, I'll give an example of what to do if there was a net charge. So let's solve for copper. I'm going to put X for Cu. SO3 has a charge of -2. So we're going to move the -2 to the other side. If we add 2 to both sides, we'll get 2x is equal to +2. So now we got to divide both sides by 2. And so x is equal to +1. So that's the oxidation state of copper in this compound. So therefore, that's the right answer. This is copper 1 sulfite. The other one, B, CuSO3, that's copper 2 sulfite because it has a +2 charge. But A is the correct answer. So let's say if we want to find the oxidation state of phosphorus in phosphite, you would write an equation P plus 3O equals the net charge, which is -3. If there's no charge here, this number should therefore be 0. So solving for phosphorus, we're going to insert a -2 for oxygen. Whenever you have an oxide ion, it's usually -2. And then add 6 to both sides. So -3 plus 6 is 3. So phosphorus has an oxidation state of 3. So that's how you can find the oxidation state of an element. Number 57, calculate the volume necessary to produce a 0.75 molar solution using 15 grams of potassium fluoride. So let's solve this using conversions. So let's start with 15 grams of potassium fluoride. So what we need to do is convert it to moles first. Once we convert it to moles, we can convert it to liters because molarity connects moles and liters. Molarity is moles over liters, so it can help us to convert moles to liters, and then we can convert liters into milliliters. But first, to convert grams into moles, we need the molar mass. The atomic mass for potassium is about 39.1, and for fluorine it's about 19. So if we add those two numbers, you should get 58.1. So for every 58.1 grams of Kf, there exists 1 mole of Kf. So these units cancel. So now we can use the molarity to go from moles to liters. A 0.75 molar solution means that there are 0.75 moles of Kf per 1 liter solution. Molarity is the ratio of moles per 1 liter. So the moles cancel. And now the only thing we need to do now is convert liters into milliliters. And there are 1,000 milliliters for every 1 liter. And you just have to know that conversion. If you don't know it, just add it to your list of things that you got to know. So 15 divided by 58.1. Take that result, divide it by 0.75 times 1,000. And you should get about 344.2 milliliters. So the correct answer is D. Now, for those of you who prefer to use equations, maybe these equations can help you. So mass is equal to molar mass times moles. So the first thing I would do is find the moles. The mass is 15 grams, and the molar mass we said was 58.1. So let's solve for the moles, which I'm going to use N to represent moles. N is for moles, M is for mass. So 15 divided by 58.1. So you should get 0.258 moles. And then you could use this equation. Molarity is moles over liters. So the molarity of the solution is 0.75. The moles is 0.258. And we're looking for the liters, so let's label it V. So what you need to do at this point is cross multiply. So we have 0.75 V is equal to 0.258. So let's divide both sides by 0.75. Using equations, I personally think it's longer. At some point, you want to make sure you can master the ability to convert from one unit to another, because it's going to make chemistry a lot easier. If you divide these two numbers, you're going to get 0.344. Now you need to realize that at this point what you have is liters. To get milliliters, multiply by 1,000. And so you should get this answer, D. 58. Calculate the mass of silver chloride that will be produced from mixing a solution of magnesium chloride with a solution of silver nitrate. Now, we're given the information for both, and we don't know which one is the limiting reactant, and we need to find the grams of the product. So what we're going to do in this problem is we're going to take each reactant and convert it to the grams of product separately, and whichever one gives us the smaller theoretical yield or the least amount of grams of product, that's going to be the answer. So let's write a balanced reaction first. So we have silver nitrate reacting with an aqueous solution of magnesium chloride. And we need to predict the product of this reaction. We know one of the products will be AgCl. We need to pair up the Ag and the Cl. And then the other one is going to be between magnesium and nitrate. So we need to write the formula correctly. Magnesium is found in group 2 of the periodic table, so it has 2 plus charge. And for nitrate, it's -1. So therefore, the correct formula is going to be Mg1NO3 Don't just assume that it's MgNO3. Always check whenever you need to write the formula of an ionic compound if you're not given that formula. So now, we need to balance this reaction. We have 2 nitrates on the right side, so we're going to put a 2 in front of AgNO3. And so that means we've got to put a 2 in front of AgCl. And so here we just need a 1. And now it's balanced. Let's start with magnesium chloride. Let's convert that into grams of AgCl. So if you're given molarity and volume, and you want to convert it to the grams of a different substance, start with molarity. So we can write molarity as moles per liter. So a 0.255 molar solution means that there are 0.255 moles of MgCl2 per liter of solution. Next, we're going to multiply that by the liters. That corresponds to the magnesium chloride solution, which is 48.6 milliliters. To convert milliliters into liters, divide by 1,000, or move the decimal 3 units to the left. So 48.6 divided by 1,000 is like 0.0486 liters. And volume just has liters only, so it's going to be over 1. It's not like molarity where it has 2 units, moles per liter. So now liters cancel, which means we only have moles of MgCl2 at this point. So we need to use the molar ratio to convert from moles of MgCl2 to moles of AgCl. So as we can see, it's a 2-to-1 ratio. So for every 2 moles of AgCl that are produced, 1 mole of MgCl2 reacts. The last thing we need to do is convert it to grams. So we need the molar mass for AgCl. For Ag, it's 107.9, and for Cl, it's 35.45. And so if you add those two, you should get 143.35 grams per 1 mole of AgCl. So the units AgCl cancels, and also moles of MgCl2 cancel as well. So now we could just do the math. So 0.255 times 0.0486 times 2 times 143.35. So you should get, I'm going to write it here, 3.55 grams of AgCl. Now we don't know if that's the answer yet, because we don't know if MgCl2 is the limiting reactant. So we need to do the same 4 steps for the other reactant. So let's start with 0.186 moles of AgNO3 per liter. And let's convert the 72.8 milliliters into liters. So if we divide that by 1,000, it should be 0.0728 liters. So the units liters cancel, Now let's convert moles of AgNO3 to moles of AgCl. It's a 2-to-2 ratio. So at this point, moles of AgNO3 cancel. And the last step is going to be the same. We need to convert moles of AgCl into grams. So the molar mass is going to be 143.35 again. So now we can plug in the numbers. 2 over 2 is 1, so we don't have to worry about those numbers. So 0.186 times 0.0728 times 143.35. You should get 1.94. Now, between these two numbers, 1.94 is smaller than 3.5. So the theoretical yield, or the maximum amount of AgCl that can be produced in this reaction, is 1.94. So answer choice B is the right answer. So what this tells us is that because this is the answer, AgNO3 is the limiting reactant. It's the reactant that gave us the theoretical yield. The other reactant, MgCl2, is the excess reactant because it gave us a greater or larger theoretical yield. So B is the right answer for this problem. Number 59. Which of the following is not a redox reaction? So let's identify the types of reactions that we have. If we look at answer choice A, it's a single replacement reaction. Whenever you have a solid metal and an aqueous solution, and it generates like another type of pure element and another aqueous solution, that's usually single replacement. Here, the magnesium displaces hydrogen out of the solution. Now the next one is a combustion reaction. Whenever you have CO2 and water as products, it's a combustion reaction. Now the third one is a decomposition reaction. Actually, I take that back. That is not decomposition. It is a combination or a synthesis reaction. Whenever you see the reaction A plus B turns into AB, that's a combination reaction. Here we have two elements joining to form a compound. So I'm just going to write synthesis. Now the reverse of a synthesis or combination reaction is a decomposition reaction. So if you have a large compound breaking into two smaller compounds, that's a decomposition reaction. Now the last one is a double replacement reaction. Here Ag pairs up with iodide, and the nitrate pairs up with the sodium atom, and so it's a double replacement reaction. The general formula for that's like AB plus CD turns into A and D is going to pair up together, and then B and C is going to pair up. So that's a double replacement reaction. In a single replacement reaction, it's like A plus BC, and that becomes AC plus B. So that's a single replacement. So now, which of the following is not a redox reaction? Let's find out which one is, and then we'll figure out which one is not. Single replacement reactions are always redox reactions, so I'm going to put a check. Combustion reactions are always a redox reaction. Anytime you have a pure element like magnesium, and if it turns into a compound, it's going to be a redox. That means there was a change in oxidation state. Magnesium went from 0 to +2, so it was oxidized. So anytime you see an element in its elemental form, like by itself, and then that same element into a compound, you know it's redox. If you look at the combustion reaction, we have elemental oxygen on the left, and in water we have oxygen in a compound. Whenever you see that, it's going to be redox. C is a synthesis reaction. Not all synthesis reactions are redox. Some are, some are not. But notice that in C we have elemental hydrogen gas, and then on the right side it's in a compound. Hydrogen went from 0 to +1 in that reaction. So because the oxidation state went up, it was oxidized. Iodine was reduced. So this particular synthesis combination reaction is a redox reaction. But not all combination reactions are redox. Now, a double replacement reaction, I've never seen it as a redox reaction. 99% of the time, it's not a redox reaction. So this one is eliminated. Notice that there's no pure elements in this compound. You have 4 compounds and no pure elements, it's not a redox reaction. The oxidation state of every element is identical, it doesn't change. For example, Ag in AgNO3 has a +1 charge, and the Ag ion in Ag and silver iodide also has a +1 charge. So if there's no change in oxidation state, you don't have a redox reaction. So D is the answer. D is the only one that is not a redox reaction. So just keep that in mind. A double replacement reaction, for the most part, is never a redox reaction. But single replacements and combustion reactions, those are redox. And every time you see a pure element on one side and that same element in a compound on the other side, that also is a redox reaction. Number 60, which of the following represents a precipitation reaction? A precipitation reaction occurs when you mix 2 aqueous solutions and if you get a solid product. A is an acid-base neutralization reaction, so we can eliminate A. Anytime you add a strong base with a strong acid, you get salt and water. B is a decomposition reaction. C is a gas evolution reaction. You get a gas on the right side. But if you look at D, we have 2 aqueous solutions, and when we mix them, sodium nitrate and sodium bromide, we get a solid product, silver bromide. So that is a precipitation reaction. So D is the right answer. 61. A 5-gram sample of an unknown metal reacts with excess nitrogen gas to produce 0.04158 moles of the metal nitride M3N2. What is the metal? So we know we could eliminate answer choice A and D. Sodium has a +1 charge and nitrogen has a -3 charge. If we pair these two together, they're going to produce a formula of Na3N1, which doesn't match M3N2. Aluminum has a +3 charge, and nitrogen has the same charge but opposite in sign. And whenever you have 2 ions with the same charge, or the same magnitude of charge, they combine in a 1-to-1 ratio. So these two will not form a metal nitride with the formula M3N2. But magnesium and calcium have a +2 charge. If we were to pair up, let's say, magnesium with the nitride ion, this would work. We would get the formula Mg3N2. So we know that the answer is either B or C. So now we need to do some sort of stoichiometry. So first, let's write a balance reaction. So the metal reacts with nitrogen gas and it produces the metal nitride, M3N2. So the nitrogen atoms are already balanced, but we need to put a 3 in front of the M to get the metal atoms to be balanced as well. So we have a 3-to-1-1 ratio. Now, our goal is to find the molar mass of the metal. If we can find that, then we can use the periodic table to ID the right element. So we have the grams of the sample already. We need to find the moles of the unknown metal. Grams divided by moles will give us the molar mass. So we have 0.04158 moles of Mg3N2. And we're going to convert it to the moles of the metal. It's a 3-to-1 ratio. So for every 3 moles of metal that reacts, 1 mole of M3N2 is produced. So 0.04158 times 3 will give us 0.12474 moles of metal. So now we're going to take the mass, which is 5 grams, and we're going to divide it by the moles of the metal, which is 0.12474 moles. And that should give us the molar mass. If you divide those two, you're going to get 40.08 grams per mole. And in the periodic table, calcium has a molar mass of 40.08. So the correct answer is B. Number 62. A metal reacts with oxygen gas to produce a compound with the molecular formula MO2. What is the molecular formula of the compound that is produced when the metal reacts with chlorine gas? So the first thing we need to do is find the oxidation state or the charge of the metal. So let's write an equation. M plus 2 oxygen atoms have a net charge of 0. So we're going to plug in a -2 for oxygen and solve for M. So therefore, the oxidation state of the metal is +4. So keeping that in mind, if we were to pair up the metal with a chloride ion, we would get the formula M1Cl4. So therefore, the answer is D, MCl4. And that's all you need to do for this problem. 63. Calculate the pressure inside a 450 milliliter container at a temperature of 298 Kelvin if 42.5 grams of nitrogen gas was added to it. So we can use the equation PV is equal to nRT, the ideal gas equation. Now, we need to get the moles. We have the grams. So let's convert 42.5 grams of N2 into moles. The molar mass of nitrogen is 14.01, so times 2, that's going to be 28.02 grams per 1 mole. So therefore, we have about 1.517 moles of N2. So let's plug it into the equation. So the volume, we need to convert it into liters. So we have to divide 450 milliliters by 1,000. So that's going to be 0.45 liters. And N is equal to 1.517. R is the gas constant, 0.08206. Now R has the units liters, ATM per mole per Kelvin. And because it has the units liters and ATM, the volume has to be in liters and the pressure has to be in ATM. And the temperature is already in Kelvin, so we don't need to change that. So to solve for the pressure, we're going to multiply the three numbers on the right. 1.517 times 0.08206 times 298. So that's about 37.1. And then divide that by 0.45. So that should give you the pressure, which is 82.44 ATM. So the closest answer is answer choice A. Now granted, I used a rounded answer for the moles. If I were to use an exact answer, it might round to 82.5. '64. Calculate the density of oxygen gas at 325 Kelvin if the pressure is found to be 825 torr. So the equation for density, it's equal to the pressure times the molar mass of the gas divided by the R constant times temperature. So we need the pressure to be in ATM. So let's convert 825 torr into ATM. 1 ATM is equivalent to 760 torr. So the pressure is about 1.0855 ATM. So at this point, we have everything that we need to plug it in to get the answer. Now the only thing that we're missing is the molar mass of oxygen gas. Oxygen is O2, and so 16 times 2, it has a molar mass of 32. We're going to use the 0.08206 value for R, and the temperature is going to be 325 Kelvin. So if you plug these numbers in, you should get 1.302 grams per liter. And that's the density of oxygen gas at that temperature and pressure. So the right answer is B. 65. A sample of gas has a density of 1.556 grams per liter at a pressure and temperature of 724 millimeters mercury and 298 Kelvin respectively. Determine the identity of the unknown gas. Anytime you wish to identify the element, given some set of data, you want to find the molar mass. And the equation that has density and molar mass, we've considered it in the last problem. If we rearrange it, it's going to be D times RT is equal to pressure times molar mass. So let's plug in what we have. The density is 1.556. The gas constant is 0.08206. The temperature is 298 Kelvin. And we need to convert the pressure into ATM. And to do that, just take the 724 millimeters mercury and divide it by 760. And so the pressure in ATM is going to be 0.9526. So now we could solve for M. All we need to do is divide both sides by 0.9526. So if you take 1.556 multiplied by 0.08206 and 298, that's 38.05. Then divide that by 0.9526. And then so you get a value of 39.94. Now we need to find out which of these elements or compounds have a molar mass of 39.94. For CO2, the molar mass is 44. For N2 is about 28. For neon, I think that's like 20. But argon is about 39.95. So A is the right answer. 66. The total pressure of a sample containing nitrogen gas, oxygen gas, and argon is 755 torr. The partial pressure of N2 and O2 are 615 torr and 121 torr respectively. Calculate the partial pressure of argon. So Dalton's law of partial pressure states that the total pressure is the sum of all the partial pressures in the container. So in this case, we have the partial pressure of N2 plus that of O2 and for argon, and that should add up to the total pressure. And the total pressure is 755 torr. The pressure for N2 is 615, and the partial pressure of for O2 is 121. So we can solve for the partial pressure of argon. So if we add 615 plus 121, that's going to equal 736. So now all we need to do is subtract 755 by 736. And that's going to give us a value of 19. So that is the partial pressure for argon. It's 19 torr. So answer choice C is the right answer. 67. A sample contained a mixture of N2 and O2 plus neon. The mole fraction of N2 and O2 are 0.625 and 0.219 respectively. Calculate the partial pressure of Ne if the total pressure in the sample is 785 torr. Now, we could find the partial pressure of Ne if we know the mole fraction of Ne. The partial pressure is the mole fraction times the total pressure. Now, another useful equation that you want to know is that the mole fraction, the total mole fraction, always adds to 1. So the mole fraction for N2 plus the mole fraction for O2 and for neon should equal 1. So we know the mole fraction for N2, that's about 0.625, and for O2 is about 0.219. So we could solve for the mole fraction of Ne. So it's basically going to be 1 minus 0.625 minus 0.219. So the mole fraction for Ne is equal to 0.156. So now we can plug this into the partial pressure equation. So we're going to replace XNE with 0.156, and then we're going to multiply by the total pressure, which is 785 torr. And so therefore, the partial pressure for NE should be about 122.46. So B is the right answer. 68. Calculate the volume of sulfur trioxide produced if 21 grams of oxygen gas reacts with excess sulfur dioxide gas at STP. So first, let's write a balanced reaction. So we know that sulfur dioxide reacts with oxygen gas and it produces sulfur trioxide. So all we need to do is put a 2 in front of SO2 and SO3 and it's now balanced. So we need to convert grams of O2 to liters of SO3. And it's at STP, standard temperature and pressure. At STP, 1 mole of gas has a volume of 22.4 liters. So if we can get the moles of SO3, we can get the liters of SO3. So let's start with 21 grams of O2. Let's convert it to moles. The molar mass of oxygen, or oxygen gas, is about 32 grams per mole, 16 times 2. So grams of O2 cancel. So now we can use the molar ratio to convert from moles of O2 to moles of sulfur trioxide, SO3. As we can see, it's a 1 to 2 ratio. So for every 1 mole of O2 that reacts, 2 moles of SO3 are produced. So the units moles of O2 cancel. Now the last thing we need to do is convert from moles to liters using the fact that 1 mole of gas, in this case SO3 gas, occupies a volume of 22.4 liters under standard temperature and pressure conditions. So moles of SO3 cancel. So now we can get the answer. 21 divided by 32 times 2 times 22.4. That should give you 29.4 liters. So C is the right answer. Number 69. Calculate the mass of hydrogen gas collected over water if the total pressure inside the 2-liter container is 765 torr at a temperature of 25 degrees Celsius. If the vapor pressure of water at this temperature is 23.76 torr. So how can we find the mass of hydrogen gas? Well, we know we're dealing with gases, and we could use PV equal nRT. We need to find the moles, and once we have the moles, we can convert it into the grams. But we also have to take into account the vapor pressure of water. So because we have two gases, water vapor and hydrogen gas, we need to write an equation that involves total pressure. The total pressure is the sum of all of the partial pressures for every gas that's in this container. So we only have H2 and H2O. So the total pressure is 765, that's in the container. We need to find the partial pressure of hydrogen, and the vapor pressure of water is 23.76. So if we subtract 765 by 23.76, we're going to get the partial pressure of hydrogen gas, which is 741.24 torr. Now we need to convert that into ATM. So we have to divide by 760. So this is the partial pressure of hydrogen gas. So now, at this point, we can use this equation, PV equal nRT. We need to find the moles of hydrogen gas. So let's plug in everything that we have. The pressure is 0.975. The volume is 2 liters. We're looking for N. We're going to use the gas constant 0.08206 for R. And for the temperature, which is 25 degrees Celsius, we need to convert that to Kelvin. So we're going to add 273 to it. And so 25 plus 273, that's 298 Kelvin. So to solve for N, let's divide both sides by 0.08206 and 298 Kelvin. So 0.975 times 2 divided by 0.08206, and then take that result divided by 298. So the number of moles is 0.0797. And then we can multiply that by the molar mass of hydrogen gas, which is about roughly 2 grams per mole. I'm always running out of space. So if we multiply by 2, you should get about 0.1594. So answer choice A is the correct answer. If we took 0.0797 and multiplied by 2.016, we would get an answer close to 0.161. Because hydrogen's like 1.008, so when you times by 2, that's 2.016. And then the answer would be closer to A. 70. Calculate the root mean square velocity of a sample of argon gas at 343 Kelvin. The equation that you need for this problem looks like this. The root mean square velocity is equal to the square root of 3RT over m, where m is not molarity but molar mass. Now you have to be careful with the units here, because the molar mass is not in grams per mole, rather it's in kilograms per mole. So argon has a molar mass of 39.95 grams per mole. So we need to convert grams to kilograms. So we got to divide by 1,000. So therefore, what we need to plug in for m is going to be 0.03995 kilograms per mole. So let's go ahead and begin. Another thing that you need to know is that for this equation to work, R, you don't want to use 0.08216. You want to use 8.3145 joules per mole times Kelvin. So we're going to plug in 3 times 8.3145. The temperature is 343 Kelvin, and the mass, the molar mass, is 0.03995. So if you type that into the calculator, you should get 462.8 meters per second. So that's the answer for this problem. So C is the right answer choice. Number 71. The rate of effusion of neon was measured to be 0.158 moles per second at a certain temperature. Calculate the rate of effusion of nitrogen gas at this temperature. The equation that we need is Graham's law of effusion, and it looks like this. It's R2 divided by R1 is equal to the square root molar mass 1 divided by molar mass 2. So in this equation, we can see that the molar mass is inversely related to the rate of effusion. As the molar mass increases, the rate of effusion decreases. By the way, effusion is the process of a gas escaping through a tiny hole or opening inside a container. Diffusion is just the movement of a gas particle from a region of high concentration to a region of low concentration. But for this equation, as the molar mass increases, the rate of effusion decreases. Heavy molecules, they move slower. Light molecules move fast. But now let's plug in the information that we have in this problem. So we have two compounds, neon, which has a molar mass of about 20.18, and nitrogen gas, which has a molar mass of 28.02. Since we're looking for the rate of effusion for N2, we're going to make R2 associated with N2. So what we have now, R of N2 over R1 is going to be the other rate, the rate of diffusion for neon, which is 0.158. And that's equal to the square root. And M1, if R1 corresponds to neon, M1 is associated with neon as well. So we're going to plug in 20.18 for that. And for M2, that's going to be 28.02. So now we could solve for R and 2. So what we need to do is multiply both sides by 0.158. If you do that for the left side, these numbers will cancel. So 0.158 times square root 20.18 divided by 28.02. If you type it in correctly, you should get this for your answer. The rate of diffusion for nitrogen gas is 0.134. Now, nitrogen gas is heavier than neon. As you can see, it has a higher molar mass than neon. So therefore, the rate of diffusion for nitrogen gas should be lower than that for neon. Number 72. An unknown gas has a rate of diffusion that is 2.646 times faster than nitrogen gas. Determine the identity of this gas. So we need to find the molar mass and cross-reference it with the periodic table, and we can ID the right element. So let's start with the Graham's law of diffusion equation. So we're looking for the molar mass of the unknown gas, which we'll label X. And so the rate of diffusion for the unknown gas has to be on the bottom right. So the rate of diffusion of N2 is on top, and this is the molar mass of N2. Now, let's focus on the first sentence. The unknown gas has a rate of diffusion that's larger than that for N2. So, if the rate for N2 is about 1, the rate of diffusion for the unknown gas is going to be 2.646 times greater than 1, which is 2.646. So if we plug in what we have, this is what we're going to get. The molar mass of N2 is about 28.02. Now the first thing we need to do is square both sides to solve for M. This is going to get rid of the radical. So at this point, this is what we now have. Our next step is to multiply both sides by 28.02. If we do that, these numbers will cancel. So now we have the molar mass, which is equal to 28.02 times 1 over 2.646 squared. So we can type this in the calculator. So 28.02 divided by 2.646 squared, and you should get the answer, which is 4.00. So that is the molar mass of the unknown gas. So it's not hydrogen. Hydrogen has a molar mass of 2. It's not CO2, that's about 44. O2 is 32, but it's helium. Helium has a molar mass of 4. So that's the identity of the unknown gas. 73. It takes 2.15 seconds for a sample of argon to fuse from one compartment into another at a certain temperature. Determine the time it takes for an equivalent sample of xenon to do the same job. Now, based on Graham's law of diffusion, we know that the rate of diffusion is inversely proportional to the square root of the molar mass. Now, this makes sense because heavy molecules, they move slower. And because they move slower, they take a longer time to get from point A to point B. Lighter molecules, which move faster, they take a shorter time. So the time is directly proportional to the square root of the molar mass. Big molecules, they take a longer time to get from point A to point B. Small molecules, they take a shorter time. So we have a direct relationship. So we're going to use this portion of the equation because we're dealing with molar mass and time. So now let's set it up correctly. We want to find the time it takes for xenon to do the same job. So we want xenon to be on top. The other substance is argon. And because it's directly related, we're going to have the molar mass of xenon on top and the molar mass of argon on the bottom. So now let's plug in the numbers now that we have. So we're looking for the time it takes for xenon to get the job done. For argon, it's 2.15. And the molar mass of xenon, I might need a second to look that up. So that is about 131.3. And the molar mass for argon is about 39.95. So all we need to do right now, mathematically, is to multiply both sides by 2.15. So these numbers will cancel. And then we can get the time it takes for xenon to get the job done. So here's what you need to type in your calculator. It's going to be 2.15 times the square root of 131.3 divided by 39.95. So if you type in correctly, the answer that you should get is about 3.898, which rounds to 3.9 seconds. So answer choice D is the right answer. 74. Which of the following statements is correct? Is it A, B, C, or D? Let's look at each one. Pressure decreases as volume increases. Is that true or false? That is a true statement. As the volume goes up, pressure goes down. They're inversely related. The graph that corresponds to it looks something like this. It's an inverse relationship. Now, number 2, pressure decreases as temperature increases. Is that true or false? So that is a false statement. As the temperature goes up, the pressure goes up. Let's say if you put water in a pot and you close it. If you were to heat it up, the pressure inside will increase. The graph between temperature and pressure, it's a straight line graph, and it looks like this because it's a direct relationship. And number 3, volume increases as temperature increases. That is a true statement. If you were to heat up a gas, the volume of the gas will expand. And this is Charles' law, and it's a direct relationship, and it looks like this. The relationship between pressure and volume is Boyle's law. Between pressure and temperature is Gay-Lussac's law. And between volume and temperature, that's Charles' law. So 1 and 3 are true statements. So therefore, B is the correct answer. 75. Which of the following gases has the highest root mean square velocity at any given temperature? So heavy gas molecules move slow, light gas molecules move fast. So as the molar mass decreases, the velocity increases. So we need to find out which one has the lowest molar mass. Neon has a molar mass of 20.18. For nitrogen gas, it's 28.08. For helium, it's 4. But for hydrogen gas, it's about 2. So H2 is the lightest molecule, and so it's therefore going to have the highest root mean square velocity, regardless of the temperature. And if you want to, you can plug in the equation. Root mean square velocity is equal to the square root of 3RT over the molar mass. And at the same temperature, the one with the lower molar mass is going to have the highest root mean square velocity. So A is the right answer. 76. Which of the following is not a postulate of the kinetic molecular theory of gases? So let's go through each answer choice. So for A, the volume of all molecules in a gas is negligible compared to the total volume of the container. This is true because let's say if you have a container, and let's say it's a 2-liter container. The gas molecules are very tiny, but they're there, and they do take up space. The volume of these gas particles might be like 0.001 liter, maybe even less. But let's say if you want to plug in PV equal nRT. When you plug in the volume, you're going to plug in 2 liters. You're not going to take into account the small space that these gas particles occupy. The right answer might be like 1.99, but it's negligible. So A is true. the volume of these gas particles is negligible compared to the total volume. Now for B, attractive and repulsive forces between gas molecules are negligible. That is true. Even though they do exist, we don't take them into account. Now, PV or nRT. The pressure and volume depends on the moles of gas, or the quantity of gas particles. So right now in this diagram we have 6 gas particles, but let's say if 2 of them were to attract to each other and they stick together, we would have a total of 5 particles, because one of them would be like diatomic. And so therefore, the number of moles of gas would change. But however, in the ideal gas law equation, we don't take this into account. We don't consider the attractive and repulsive forces between gas molecules, so it's negligible. So B is a true assumption for the kinetic molecular theory of gases. And C is also true. We also assume that molecular collisions are perfectly elastic. So when one gas particle collides into another, they pretty much bounce off, and the kinetic energy is conserved. So D is the right answer. All of the above are true statements. For the exam, simply commit this to memory. I mean, you can go deep into it, but as long as you know these statements, you should be fine. You just have to know which statements are true and which ones are false, which ones are part of the molecular theory of gases and which ones are not. 77. Which of the following compounds contain ionic and covalent bonds? Ionic bonds usually exist whenever you have a positive and a negative charge. And for the most part, metals and nonmetals comprise most of the ionic bonds that you'll encounter. So if we look at A, magnesium is a metal, it has a +2 charge, and chloride is a nonmetal, it has a -1 charge. So A contains an ionic bond, but it doesn't have a covalent bond. Covalent bonds are formed when electrons are being shared, typically between 2 nonmetals. So in carbon disulfide, which looks like this, the electrons are shared between carbon and sulfur. So this is a covalent bond. Carbon is a nonmetal, sulfur is a nonmetal. Usually 2 nonmetals indicates the presence of a covalent bond, and a metal and a nonmetal usually indicates the presence of an ionic bond. So B is eliminated. It doesn't have both ionic and covalent bonds. So now let's consider answer choice D. Answer choice D contains only covalent bonds. It's glucose, or it could be fructose. And it's composed of nonmetals, and there are no ions that can be formed. Glucose doesn't ionize, so D is eliminated. Answer choice C is the right answer. We have a metal and a nonmetal. Potassium is a metal, and it forms a +1 cation. Nitrate is a polyatomic ion that has a negative charge. So we do have an ionic bond due to the presence of the charges. But within the polyatomic ion, nitrate, we also have covalent bonds. The electrons are shared between oxygen and nitrogen, so C is the right answer. Now, there are other compounds that contain both ionic and covalent bonds but do not contain any metals. A good example of this is ammonium chloride. Ammonium has a +1 charge, and chloride has a -1 charge. So as you can see, there exists the ionic bond between the positive charge and the negative charge. But within the ammonium ion, it's a polyatomic ion, it contains covalent bonds. Both nitrogen and hydrogen are nonmetals, and the electrons are shared between the nitrogen and hydrogen as indicated by these bonds. And so that's a covalent bond whenever you have a sharing of electrons. It might be polar covalent, but nevertheless it's a covalent bond. So ammonium chloride has both ionic and covalent bonds, yet that compound doesn't have any metals. So just because metals are not there doesn't mean it can't be ionic. Just keep that in mind. What you need to know is if it dissociates into ions. If it does, it's going to be ionic, regardless if it has metals or not. #78. A gas absorbs 780 joules of heat and expands from 1.2 liters to 1.6 liters at a pressure of 2.3 atmospheres. Calculate the change in the internal energy of the system. There are two equations that we need. The change in internal energy is the sum of the heat energy that's transferred plus the amount of work that's performed. And the amount of work is equal to negative P delta V. So let's calculate the amount of work first. So W is equal to negative 2.3 times the change in volume, final volume minus initial volume, so 1.6 liters minus 1.2 liters. So negative 2.3 times 0.4, you should get negative 0.92. Now the units are liters times ATM, and we need to convert that into joules. So it's about 101.3 joules per liters times ATM. So the work that's performed is about negative 93.2 joules. But we're not done. So now we need to plug that information into the other equation. Now, since the gas absorbs 780 joules of heat, it's going to be positive because it gained energy. And we're going to plug in negative 93.2 for W. So 780 minus 93.2, we should get an answer of positive 686.8 joules of energy. So that's how much energy the system gained. So D is the right answer. So anytime the system absorbs heat, Q is positive. If the system releases heat, if it's an exothermic reaction or an exothermic process, Q is negative. So you have to be careful with the signs. The math isn't bad. And anytime you use this equation, negative P delta V, make sure you convert the units into joules using the conversion that we mentioned. The next thing that we want to take into account is work. If you hear the expression work is done by the system, that means the system consumed energy or used up energy to do work. Work is negative. If the surroundings do work on a system, or if you hear the expression work is done on a system, that means the system gains energy. So work would be positive. So just keep in mind those expressions. Work done by the system, work is negative. Work done on a system, it should be positive. 79. It takes 121.6 joules of energy to heat a 12-gram sample of an unknown metal from 21 to 44 degrees Celsius. Determine the specific heat capacity of the unknown metal. The equation that we need is Q is equal to MCAT. Q represents the heat energy, and that's 121.6. The mass is 12.5. The specific heat capacity, we're looking for it, and the change in temperature, final minus initial, it's 44.2 minus 21.2. So we just got to solve for C. So 44.2 minus 21.2, that's equal to 23. And if we multiply that by 12.5, on the right side we should get 287.5 times the heat capacity, C. So now we need to divide both sides by 287.5. So 121.6 divided by 287.5, that should equal 0.423 joules per gram per Celsius. So that's the specific heat capacity of the unknown metal. So B is the right answer. Number 80. 40 milliliters of water at 25 degrees Celsius is mixed with 100 milliliters of water at 82 degrees Celsius. The density of water is about 1 gram per milliliter. Determine the final temperature of the water. So this is a heat transfer problem. We have two samples of water at different temperatures. So the equation for this type of problem, it's QA is equal to negative QB. Now you need the negative sign for it to work, because for one sample it's going to be endothermic, it's going to absorb heat, The other sample is exothermic. It's going to release heat. So we need the negative sign. So we're going to use Q equals MCAT, but just for both sides. Now, because the density of water is 1 gram per milliliter, what this means is that a 40 milliliter sample of water has a mass of 40 grams, and a 100 milliliter sample of water has a mass of 100 grams. So we can plug in 40 grams. The heat capacity is going to cancel because the substance is identical. C is 4.184 for water, but we can cancel it at this point because it's the same. The final temperature, we're looking for that. The initial temperature of the cold water sample, it's 25. The mass of the hot water sample is 100 grams. Now it's going to have the same final temperature as the cold water sample because they are going to reach equilibrium at the same temperature. Once they have the same temperature, the heat transfer process stops, and that's it. Nothing else can happen. So the initial temperature of the hot water solution is 82. And let me not forget the negative sign that should be there. So now let's solve for T. So let's distribute the 40. So we have 40 TF, and 40 times 25 is 1,000. And now let's distribute the negative 100. So on the right side we have a negative 100 TF is equal to plus 8,200. So let's add 1,000 to both sides, and simultaneously let's add 100 TF to both sides as well. So these numbers will cancel, as well as that. On the left, 100 plus 40, that's going to be 140 TF. And on the right, 8,200 plus 1,000, that's 9,200. So 9,200 divided by 140 is equal to 65.7. So that's the final temperature. So D is the right answer. So notice that the final temperature is closer to 82 than it is to 25. The reason for that is we have a greater quantity of the hotter sample, or the high temperature sample, than the cold water sample. So because we have more of the 82 degree sample of water, the average, or the final temperature, is going to be closer to 82. So D is the right answer for this problem. Number 81, which of the following correctly represents the heat of formation of ammonia? To write the reaction that is associated with the heat of formation of a substance, write the substance on the right side. Now the coefficient must be 1. You can't change it if it's a heat of formation reaction. It can't be 2, it can't be 3, it can't be 4, it has to remain 1. On the left side, you need to write the elements that create or compose that compound. So nitrogen in its standard state exists as N2, it's diatomic, and hydrogen gas in its natural elemental state is H2. So now we have to balance the reaction, and we may have to use fractions. We have one nitrogen atom on the right side, so a half times 2 is 1, so we got to put a half in front of 2. And we have 3 hydrogens on the right, so we need 3 over 2 to balance it. 3 over 2 times 2 is 3. And so that's the equation. So the right answer is answer choice C. So let's go over some other examples. Let's say if we wish to write the heat of formation for methanol. So the coefficient for methanol has to be 1. We can't change it. So methanol is composed of carbon, hydrogen, and oxygen. Carbon in its natural state is just C, and it's a solid. Hydrogen gas in its elemental state is H2, and it's a gas. And for oxygen, it's O2, which is also a gas. Now the carbon atoms are balanced already. We have a total of 4 hydrogen atoms on the right side, so we got to put a 2 in front of H2. And we only have 1 oxygen atom, so we got to put a half in front of it. And so that's how we can balance that particular reaction. So let's try another example. Let's say if we wish to balance the equation C5 H9 NO2. So we have carbon, hydrogen gas, nitrogen gas, and oxygen gas. So this number has to remain 1. We need 5 carbon atoms. We have 9 hydrogens, so we need 9 over 2 H2 molecules. We have only 1 nitrogen, so we need 1 over 2. And we have 2 oxygens, so we just need a 1 in front of O2. And so that's how you can write the heat of formation reaction for any type of substance. 82. Use Hess's law to determine the enthalpy of the combustion of methane using the following information. So according to Hess's law, we need to somehow modify equation 1 and 2 such that it adds up to equation 3. If we can do that, then we can add the enthalpies of equation 1 and 2 to estimate the enthalpy of the reaction for equation 3. And that's the idea of Hess's law. So how can we modify equations 1 and 2 such that when we add them, we'll get equation 3? Now, you can do it the easy way or you can do it the hard way. If you want to do it the easy way, you need to focus on the right compounds. So let's look at equation 1. Should we focus on H2O, CO, O2, or CH4? Now, you don't want to focus on O2 or CO. The reason being is O2 is found in equations 1 and 2, and CO is also found in equations 1 and 2. You don't want to focus on those elements and compounds, because if you do, it's going to make it harder. You want to focus on the species that are found only in 1 and not in 2. So what you want to focus on could be either water or methane, because it's not found in equation 2. If you do it that way, it's going to work out nicely. So let's focus on methane, CH4. So we have 2 methane molecules on the right side, but we only have 1 on the left side. And we want to change equation 1 and 2 to make it look like 3. So we need to reverse equation 1 so that the CH4 could be on the left side, and we need to multiply by half to get 1 CH4 as opposed to 2. So let's do that. So let's multiply the first equation by a half, and let's reverse it at the same time. So it's going to be 1 CH4. Let me rewrite it up here. Plus half of 3 O2s would be 3 over 2 O2. And then on the right side, half of 4 H2O molecules, half of 4 is 2. And for CO, half of 2 is 1. So this is what we now have. Now, because we multiplied the equation by a half, we have to multiply the enthalpy value by a half as well. And because we reversed it, we need to change the sign from positive to negative. So 1215 divided by 2 is 607.5. So for this reaction, the enthalpy is going to be negative 607.5. Now for the second equation. So we don't want to focus on CO or O2 because they're found in both equation 1 and 2. So we're going to focus on CO2 because it's only found in equation 2 and not in 1. Now, notice that CO2 in equation 2 is on the left side, but we want it to be on the right side. So all we need to do to fix equation 2 is we just got to reverse it. So we're going to have 1/2 O2 on the left plus CO on the left, and on the right side it's going to be CO2. Now the enthalpy, all we need to do is change the positive sign into a negative 283. Anytime you reverse the reaction, you just got to change the sign of the enthalpy. So now let's add these two reactions and let's see if it's going to give us reaction 3. So first let's find out what cancels. Notice that we have a CO on the left and a CO on the right. So those two will cancel. And on the left, we have a methane molecule, so that's going to drop down to the left side. Also on the left, we have 3/2 O2 molecules and half of an O2 molecule. If we add the coefficients, 3/2 plus 1/2, we get 4/2. 4 divided by 2 is 2, so we get 2 O2 molecules on the left side. And on the right side, there's nothing to cancel with the water and the CO2, so we're just gonna drop them down over here. So notice that what we now have is the net reaction, the reaction that we're trying to find. So since we have the net reaction, we can now add the enthalpy values. So negative 607.5 plus negative 283. So the enthalpy for the third reaction is going to be negative 890.5. So the answer is C. So that's how you can use Hess's law to estimate the enthalpy of a reaction. So make sure you focus on the right compounds. Number 83. Sulfur dioxide reacts with oxygen gas to produce sulfur trioxide as shown in the following chemical equation. Calculate the amount of sulfur trioxide produced if 742 kilojoules of heat energy was released. So how do you think we can do this problem? So we're given the kilojoules of heat energy, and we want to convert to grams. If we look at the answer choices, all the units are in grams. So we have a thermochemical equation. Whenever you're given a thermochemical equation, where you have a balanced reaction and the enthalpy that's associated with that reaction, you can use that to convert kilojoules into moles. So let's begin. So we have 742 kilojoules. We don't have to worry about the sign because if we're converting it to grams, everything's going to be positive. Now, for every 2 moles of sulfur trioxide that's produced, 196.6 kilojoules of heat energy will be released. So we can use that in our next conversion factor. So for every 2 moles of SO3, 196.6 kilojoules of heat will be exchanged. So the units kilojoules cancel. The last thing we need to do is convert moles to grams. So let's find the formula mass of sulfur trioxide. Sulfur has a molar mass of 32.06, and for oxygen it's about 16. So the molar mass is 80.06 grams per 1 mole of sulfur trioxide. So now we can get the answer. So 742 divided by 196.6 times 2 times 80.06. You should get 604.3 grams. So D is the right answer. 84. 20 grams of potassium hydroxide was dissolved in 75.63 milliliters of water. The temperature increased from 25 to 90. The density of water is 1 gram per milliliter, and the specific heat capacity of water is 4.184 joules per gram per Celsius. Calculate the enthalpy of the reaction shown below. So if the temperature of the water were to go up, the dissolution of potassium hydroxide, would you say it's an endothermic reaction or an exothermic reaction? Now, the reaction is exothermic. So let's say we have a beaker, and here's the solution, and here's KOH. As KOH dissolves and separates into K plus and OH minus, it releases heat energy. So that's the system, the reaction. And because it releases heat energy, the surrounding water molecules absorb that energy, and so the temperature of the solution goes up. So for the reaction, it's exothermic. Energy was released from the reaction. But for water, it's endothermic. Because the temperature of the water rose, water gained energy. It absorbed the heat. So for water, water is the surroundings. It's endothermic for water, but exothermic for the reaction. Likewise, let's say if the temperature of the solution were to decrease, that means that energy was removed from the surrounding water molecules, and that's why the temperature would go down. And that means that the reaction, it absorbed that energy, it pulled it away from the surrounding water molecules. And so the reaction would be endothermic, but for water, it would be exothermic if the temperature were to decrease. So make sure you understand that for these types of problems. So now let's focus on the question. How can we find the enthalpy of this reaction? In order to find the enthalpy of the reaction, we need to know how much heat energy the reaction released. And we need to divide it by the number of moles. Q can be in joules or kilojoules, but if we look at the units of the answer, it's in kilojoules per mole. So we need to divide by the moles. Now, in order to find Q of the reaction, we need to find out how much heat energy was absorbed by the water, because that should equal to the amount of heat energy released by the reaction. So Q of the reaction is equal to negative Q for water. Because for water, it's an endothermic process. Water is going to absorb the heat, but for the reaction, it's exothermic. So for water, Q is positive, but for the reaction, Q is negative. So we have to incorporate the negative sign. And in order to find the heat energy absorbed by water, we can use Q is equal to MCAT. So those are the equations that we're going to use in this problem. So I just want to give you an overview before we begin. So now we can begin. So let's find out how much heat energy was absorbed by the water. So the density of the solution is about 1 gram per milliliter. So that means if we have 75.63 milliliters of water, the density of water is 1 gram per milliliter. But if we have 75.63 milliliters of water, because it has a density of 1, that means that we have 75.63 grams of water. And the specific heat capacity for water is about 4.184. And the temperature rose from 25 to 90. So delta T is final minus initial temperature. So 90 minus 25. So if you type this in, you should get 20,568 joules. If my math is correct. Now let's convert that to kilojoules. To convert joules to kilojoules, simply divide by 1,000, or move the decimal point 3 units to the left. So 20,568 joules is 20.568 kilojoules. But Q is positive since the water it absorbed heat. That was an endothermic process. But Q of the reaction is going to be exothermic, so it's going to be negative 20.568 kilojoules. Now the next thing we need to do is find the moles of the solute. So we have 20 grams of KOH. So let's convert that into moles. So we need to find the molar mass of potassium hydroxide. According to the periodic table, potassium has an atomic mass of 39.1, for oxygen is 16, and for hydrogen is 1.008. So the molar mass is about 56.108 grams per mole, or per 1 mole. So if we divide these two numbers, you should get 0.3565 moles. So now we can find the enthalpy of the reaction. Delta H is equal to Q divided by N. So Q is negative 20.568 kilojoules, and we're going to divide that by 0.3565 moles. So the answer is negative 57.69 kilojoules per mole. So the closest answer is answer choice A, negative 57.8. So that's it for this problem. That's how you can find the enthalpy of the reaction for this situation. 85. Calculate the energy of a photon released if an electron in a hydrogen atom falls from the n equal 4 state into the n equal 2 state. The equation that you need is this one right here. It's E is equal to negative 2.178 times 10 to the negative 18 joules multiplied by 1 over n final squared minus 1 over n initial squared. So all we need to do is just plug in the numbers. So the electron, it falls from the 4th energy level to the 2nd energy level. So what's the final state and what's the initial state? So what's n final? The final state is the 2nd level because that's where it's going to end up. And the initial state is the 4th energy level because that's where it started from. So 1 over 2 squared, that's like 1/4. And 1 over 4 squared is 1 over 16. You could just type this in your calculator at this point. So 1 over 4 minus 1 over 16, that's 3 over 16. As a decimal, that's like 0.1875. Then take that result, multiply it by negative 2.178 times 10 to the minus 18. The answer that you should get is equal to negative 4.08 times 10 to the negative 19 joules. So the answer is B. So that's how you can calculate the energy of a photon released by an electron anytime the electron goes from one energy level to another energy level inside a hydrogen atom. 86. A ground state electron inside a hydrogen atom absorbs a photon that has a wavelength of 102.7 nanometers. Into what final state will the electron jump to? So we need to use the equation that we used in number 85. And we got to solve for n. But before we can use that, we got to find the energy of the photon that was absorbed by the electron. So first, let's find frequency. We know that wavelength times frequency is equal to the speed of light. So we're going to plug in 107.2 times 10 to the minus 9 meters for the wavelength. You can't plug it in as 102.7 nanometers. You have to convert it to meters. In order to do that, just replace nanometers with 10 to the minus 9 meters. It's a quick way to get the answer. And the speed of light is 3 times 10 to the 8 meters per second. Thus, you could see why the unit has to be in meters. They have to match. So the frequency is going to be 3 times 10 to the 8 divided by 102.7 times 10 to the minus 9 meters. So the frequency of the photon should be 2.921 times 10 to the 15 hertz, or seconds to the minus 1. That's the unit for frequency. So now we could find the energy of the photon. And it's Planck's constant times the frequency. Sometimes the frequency can be written as a V instead of an F. Planck's constant is 6.626 times 10 to the minus 34, and then multiplied by the frequency. So the energy of the photon that you should get should be about 1.9355 times 10 to the minus 18 joules. So now we can find n using this equation. E is equal to negative 2.178 times 10 to the minus 18, 1 over n final squared, minus 1 over n initial squared. So we can replace E with 1.9355 times 10 to the minus 18. Now, there's two n values. Which one are we looking for? Now, the question asks, into what final state will the electron jump into? So we're looking for n final. So let's write it as 1 over x squared. But now, what is the initial state? What is the initial energy level? Now, notice that the first sentence of the problem said that a ground state electron inside a hydrogen atom. A hydrogen atom only has one electron. And so that electron is going to be found in the first energy level if it's in the ground state. The only way it's going to be at a higher energy level if it's in the excited state. So the ground state is the first energy level, so therefore n is 1. So now to solve this, the first thing we need to do is to divide both sides by negative 2.178. And for this problem, do not ignore the negative sign. It is very important. By the way, another important question I have to ask you. The energy of the photon, is it positive or is it negative? Because the hydrogen atom absorbed a photon, it's positive. Anytime energy is absorbed, you can say like it's endothermic and it's positive. If the photon were to release the electron, if the electron were to release the photon, or if it were to emit energy by releasing the photon, it would be exothermic and E should be negative. So if that was the case, we would have to add a negative sign here. And if you didn't add that negative sign, it won't be correct. So right now it's going to be a positive sign, and that means n final should be higher than n initial. So now, let's divide those two numbers. So 1.9355 times 10 to the minus 18 divided by negative 2.178 times 10 to the minus 18. So you should get negative 0.8887, and that's equal to 1 over x squared minus 1 over 1 squared is just 1. So since this number is gone, we don't need the brackets anymore. We can open it. So now let's add 1 to both sides. So negative 0.8887 plus 1 is about 0.1113, and so that's equal to 1 over x squared. You can put this number over 1 if you want. So now let's raise both sides to the minus 1. If we do that, we're going to have 1 over 0.1113 is equal to x squared. So to solve for x, we can now take the square root of both sides. So therefore, let's type it in. 1 divided by 0.1113 is about 8.98, which is close to 9. If you take the square root of 8.98, you're going to get 2.997, which is approximately 3. The square root of 9 is 3. And so that's the answer. What this tells us is that the final state is the third energy level. So when the electron inside the hydrogen atom, when it absorbs a photon, particularly with a wavelength of 102.7 nanometers, it's going to jump from the first energy level to the third energy level. And so the answer is B. But now let's review some concepts. So here's the hydrogen atom. That's the first energy level. Here's the second, and here's the third. So here's the electron. It absorbed a photon of light, and when it gained energy, the electron, it jumped to the third energy level. So anytime the electron goes, when it jumps to a higher energy level, that means it absorbed energy. That's an endothermic process. If the electron were to fall back from the third to the first energy level, it would emit a photon rather than absorb a photon. So anytime an electron jumps to a higher energy level, it absorbs energy. When it falls back down, it emits energy. 87. What is the electron configuration of copper used in noble gas notation? So copper has an atomic number of 29. So when we write the electron configuration, it should add up to 29. So what we could do, since it's a multiple choice problem, we could just look at the answers. So argon has an atomic number of 18. So if we look at A, it's 18 plus the exponent of 4s2 is 2, and the exponent of 3d9 is 9. If you add these numbers, this will equal 29. So A is okay. If you do the same for B, it's 18 plus 1 plus 10, so that equals 29. For C, it's 18 plus 2 plus 10, so that's about 30. We can eliminate answer choice C. And for D, it's 18 plus 2 plus 8, so that's 28. So D is out. Now another way you can do this is you can write out first the sublevels. So we have 1s, 2s, 3s, 4s. In the second energy level, you have the p sublevels as well, like 2p, 3p, 4p. And in the third energy level, you have the d sublevels. Now after 4d, you have 4f, but I don't think we need to go that far. Just keep in mind, s can hold 2 electrons, p can hold 6, d can hold up to 10. So first we have 1s2, and then we have 2s2. After 2s is 2p, then 3s. So 2p6, 3s2, then it's 3p6, 4s2. If we add the exponents, we have 2 plus 2 plus 6 plus 2 plus 6 plus 2. That's 20. So we need 9 more. Now the D level can hold up to 10, so we're going to stop at 3D9. So it appears as if the answer is A. Argon has a configuration of 1s2, 2s2, 2p6, 3s2, but it stops at 3p6. So you would write argon and then 4s2, 3d9. That's the noble gas notation. If they ask you for the ground state electron configuration, you would write everything from 1s2 to 3d9. It turns out that the answer is not A. The correct answer for this problem is B. Copper is one of the exceptions. Let's talk about it. So initially, when you write it out, you would get a 4s2, 3d9. And if we were to draw that, here is the 4s2 sublevel, and here's like the 3d sublevel. They're very close in energy. So here this is 4s2. We have 2 electrons in that orbital, and then 3d9, 1, 2, 3, 4, 5. We're going to add it one at a time with parallel spins anytime the orbitals have the same energy based on Hund's rule. And now we can add the opposite spin. So that's 3d9. It turns out that one of the s electrons in the 4s sublevel, it wants to jump to the 3d sublevel and fill that spot. And for some reason, it happens to be more stable. Maybe because the 4s energy level is a little bit higher than the 3d. But we know it happens. So it turns out that the right configuration is actually 4s1, 3d10. So for the test, just make sure you know that copper is one of the exceptions. Now, there are some other elements that show the same trend. And the ones that you have to know is chromium and the element that's below it, which I believe is not tungsten, but molybdenum. Let me pull out my periodic table. So like chromium, if you were to write the electron configuration, naturally you would get 4s2 3d4. But the s electron is going to move to the 3d sublevel, and it's going to be 4s1 3d5. Now the elements in the column where copper is, copper, silver, and gold, they follow the same trend as copper. So instead of being 4s2 3d9, it's going to be like 4s1 3d10 for copper. For silver, it's going to be like 5s1 4d10, and for gold 6s1 5d10. So if you see those elements on the test and you need to find the electron configuration, just know that they are exceptions to the rule, and all you need to do is take an s electron and move it to the d sublevel, and you should be okay. So that's my 2 cents for this problem. So B is the right answer. 88. Which of the following corresponds to the quantum letter L? So these are just some facts to know. The principal quantum number is n. The angular momentum quantum number is L, so B is the answer. The magnetic quantum number is ml, and the electron spin is ms. So just know that for the exam, or whichever test you're studying for. 89. Which of the following principles state that no two electrons can have the same set of 4 quantum numbers? Is it A, B, C, or D? The correct answer is D. This is the Pauli exclusions principle. So let's say if we have 4 quantum numbers, let's say n is 3, L is 2, ml is 1, and ms is minus a half. There's only one electron that can have these 4 quantum numbers. 2 electrons cannot have it, and that's the idea behind Pauli exclusions principle. So let's find out which electron has those 4 quantum numbers. So n is 3. When L is 2, that means we have the D sublevel. If L was 0, it would be S. For P, L is 1. For D, L is 2. For F, L is 3. And for the D sublevel, there are 5 orbitals. And because L is 2, ML could be anywhere from -2 to 2. So now, we want an electron that has a down arrow. Because the electron spin is -1/2, we need the down arrow. But first, we're going to draw the up arrows, or the arrows facing the upward direction. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the electron that we want. It has an electron spin of -1/2, but it's in the orbital that's designated 1 for ml. So that is the 9th electron in the 3d sublevel. So these 4 quantum numbers corresponds to the 3d9 electron. Now what about Hund's rule? What is Hund's rule exactly? Well, Hund's rule states that whenever you add electrons to orbitals, they have to have the same spin. They have to have parallel spins, and you have to add it one at a time. So let's say if you want to add two electrons to the 3d sublevel, you can't add it like this. That will be a violation of Hund's rule. You have to add the electrons one at a time. So you would add an electron to an empty orbital first before you would pair it up with another electron. And they have to have parallel spins. So if the first arrow is going up, the second arrow, it can't be going in a downward direction. That would be anti-parallel. The second arrow has to go in the same direction. So you have to add electrons one at a time with parallel spins. And that's the idea behind Hund's rule. Now, Heisenberg uncertainty principle, it basically states that the more you know of one thing of an electron, the less you know of the other. So for example, the more you know about the position of an electron, the less you know about its momentum. Let's say if you were able to look at an electron somehow with a powerful microscope. If you were to shine light on the electron with some microscope of some sort, the electron would behave differently when you're looking at it compared to when you're not looking at it. So you can never be too sure what an electron is doing or where it's located. The more that you know of one variable, the less you know of another, and that's Heisenberg's uncertainty principle. If you think about like the definition of an orbital is just the probability of finding an electron at any given moment. An orbital is where you're most likely to find an electron. A node is where you're least likely to find it. So you can never know exactly where an electron is. You have to use probability. You could say, okay, the electron is a 95% chance that the electron could be in this region, in this orbital, but you can't be certain about it. So that's an example of the Heisenberg uncertainty principle. The last one is the off-bar principle. The basic idea of the off-bar principle is that when you add electrons, you have to fill the lower energy levels first before you fill the higher energy levels. So let's say if an atom has 5 electrons. So you have the 1s orbital, the 2s orbital, the 2p orbital, and the 3s orbital. So the first 2 will go in the first orbital, and the second 2 will go in the next orbital. Now the fifth one is going to go in the 2p orbital. 3s has more energy than 2p. So based on the off-bar principle, we're going to put the fifth electron in a 2p orbital. If we put it in a 3s orbital, that will be a violation of the off-bar principle, which states that electrons prefer to add to lower energy levels first before they fill the higher energy levels. A good way to illustrate this, let's say if you're inside a huge hotel with like 40 or 50 stories. And let's say you're on the first floor and you want to find the food court where they're selling ice cream. And let's say there's a food court on the second floor and on like let's say the 30th floor. And let's say the elevators are not working. And the quality of ice cream is the same on the second floor and on the 30th floor. If you had to take the stairs, would you get the ice cream on the second floor or on the 30th floor? Which is easier? Well, the average person will go to the second floor. There's not many people in their right mind that will actually climb 30 stairs to get some ice cream, unless you want to get a good workout. But an electron is like the same thing. If an electron has a choice to go between the 2p orbital and the 3s orbital, if both are available, it prefers to fill the lower energy level. It's easier to get to the 2p level than the 3s level. It takes more energy for that electron to get to that 3s sublevel. Just as the same, it takes you more energy to get to the 30th floor as opposed to the second floor. So the electron is going to try to find an orbital where it's easier to get to. And so that's the idea behind the off-bar principle. Electrons, they fill up the lower energy levels first before filling up the higher energy levels. But for this problem, D is the right answer. Now I know some of you out there might be having some questions regarding Hund's rule and the off-bar principle. So let me see if I can address them before they come up. So let's say if we have a 1s orbital, 2s orbital, 2p, and the 3s orbital. Now, let's say we wanted to add 3 electrons. Should we add them with parallel spins one at a time like this? Or should we add them like this? What would you say? Now, you might be thinking of Hund's rule, which states that you should add the electrons with parallel spins first, one at a time, rather than add in 2 electrons in one orbital. Because Hund's rule states that electrons, they prefer to occupy orbitals by themselves before being paired. They like to be unpaired than paired, and they like to have parallel spins first. Now, the only problem with this is a violation of the off-bar principle, which states that electrons prefer to fill lower energy levels first rather than higher energy levels. So once you add the first electron, you don't want to add the second electron to a higher energy orbital. You want to fill the lower energy levels first. So two electrons can't have the same spin in a single orbital. If one is up, the other has to be down. So because in the first energy level there's only one orbital, we have to put the second electron there. Now the third electron has to go in the 2s sublevel. It's not going to go into the 2p. That will be a violation of the Aufbau principle. We got to fill the lower energy levels first. Now if we were to add another electron, it's not going to go into the 2p level. It's going to go to the lower energy level, the 2s. And it's going to have the opposite spin. Now, if we were to add a fifth electron, we would add it to the 2p level before we add it to 3s, because 2p is lower. Now, Hund's rule states that whenever you're adding electrons to degenerate orbitals, that's orbitals of the same energy, that's when Hund's rule apply. If the orbitals have different energy, Hund's rule doesn't apply. So let's say if you want to add the fourth electron, Hund's rule wouldn't apply between the 2s and 2p level because they have different energies. So you have to put the fourth electron in 2s orbital. But now if you look at the 2p sublevel, these two orbitals have the same energy. And whenever you add in electrons to degenerate orbitals or orbitals of the same energy, now Hund's rule will apply. So when you add the fifth electron, initially it's going to go up. When you add the sixth electron, you don't want to add it to the same energy level because, you don't want to add it to the same orbital because that would be a violation of Hund's rule. Electrons, they prefer to be unpaired rather than paired if the orbitals have the same energy. If they have different energies, then they'll pair up rather than go into a high energy level. So, because these two orbitals have the same energy, now we have to follow Hund's rule rather than the Aufbau principle. And so, the next electron is going to occupy the empty orbital as opposed to occupying an orbital that has an electron. So the third electron is going to go in the empty orbital and it's going to have the same spin. It's going to have a parallel spin. Now if we add, let's say the eighth electron, it doesn't want to go into the 3s level because that would violate Aufbau's principle. It wants to go in the lower energy level. So now it has no choice but to pair up with one of these electrons. So it's going to have the opposite spin. So I just want to clarify Hund's rule and the Aufbau principle. So whenever you're putting electrons between two orbitals that have different energies, the Aufbau principle has priority. You got to put it in the one that has a lower energy. And whenever you add in electrons to degenerate orbitals or orbitals that have the same energy, then you have to consider the Hund's rule, which you don't want to put electrons in the same orbital if there's an empty orbital. Rather, you want to add electrons to the empty orbital first with parallel spins, and then once they're filled, or once they're half filled, then you can pair up electrons with the opposite spin. So, I hope I didn't confuse you on that. Hopefully it clarified any potential questions that you may have. And that's it. That's all I'm going to say on this matter. Number 90. Which of the following correctly lists the elements sulfur, fluorine, and selenium in order of increase in electronegativity? So, in the periodic table, here is oxygen and this is fluorine. Below oxygen we have sulfur and selenium. Electronegativity increases towards fluorine. It increases as you go up and to the right of the periodic table. Fluorine is the most electronegative, so it should be the highest. Since we want to rank it in order of increase in electronegativity, we need to go from low to high, so fluorine is going to be the last one. And the arrows should point in this direction. So now, which one is more electronegative, sulfur or selenium? Well, sulfur is higher or above selenium, and as you go up, the electronegativity increases, so it's going to be higher for sulfur, and it's going to be lower for selenium. So the right answer for this problem is answer choice B. 91. Which of the following correctly lists the elements magnesium, sulfur, cesium, and silver in order of increase in atomic radius? So let's place some of the elements on the periodic table. So here we have lithium, sodium, potassium, rubidium, and I'm going to highlight cesium in blue. Next to sodium we have magnesium, and then we have like the transition elements. So silver is in the same row as rubidium. It's like somewhere over here. There's Ag. And here we have gallium, germanium, arsenic, selenium, and above selenium we have sulfur. So these are the 4 elements of interest. Atomic radius, or atomic size, increases as you go towards cesium. It increases as you travel to the left of the periodic table and as you go down a column. So sulfur should have the smallest atomic radius, or the shortest. So sulfur should be like the smallest atom compared to the 4 that's listed. So since we're ranking it in increase in order, sulfur should be the first one. This means that we can eliminate answer choice C and answer choice B. Now, we know that cesium should be the largest because it's all the way to the right and all the way to the bottom. So cesium should be at the end. That means we can eliminate answer choice D. So the correct answer is A. 92. Which of the following correctly lists the ions oxide, Na+, Mg+2, and fluoride in order of increase in ionic radius? So on the right side of the periodic table we have the oxide and the fluoride ions. And on the left side we have the sodium and the magnesium cations. Now all of these ions are isoelectronic, which means that they have the same number of electrons. As an atom, oxygen has 8 electrons, but when it has a -2 charge, it gains 2 electrons, and so it has 10. Fluorine also has 10 electrons, or the fluoride ion. Sodium as an atom have 11 electrons, but because it has a +1 charge, it lost an electron, and so it has 10. Magnesium naturally has 12 electrons, but it lost 2, so it has 10 as well. Oxygen has 8 protons, fluorine has 9, sodium has 11, and magnesium has 12. It turns out that for isoelectronic species, as the number of protons increases, the ion decreases. And generally speaking, anions, which have negative charges, are a lot bigger than cations, which have positive charges. So oxide is very big. And fluoride, which has more protons, is going to be a little bit smaller than oxide. As you add protons to the nucleus, the positive charge of the nucleus increases. And when that happens, those protons can pull the electrons with a greater force towards the nucleus. And so the electron cloud, it shrinks as the electrons move closer to the nucleus. And so it becomes smaller. So the more protons you have, the smaller the atom or the ion will be. So if we compare sodium and magnesium, magnesium is going to be a lot smaller than sodium. So if sodium is, let's say, this big, magnesium is probably going to be like that big. So as you can see, the anions, the negatively charged ions, are a lot bigger than the cations, the positively charged ions. Because as you add electrons, the electron cloud, it expands. As you take away electrons, you lose an electron shell, so it becomes smaller. But as you can see, the one with the more protons usually is the smallest, and so Mg+2 is the smallest. So the right answer for this problem is answer choice C. Magnesium has 12 protons, sodium has 11, fluoride has 9, and oxide has 8. So as the number of protons increases, the ionic radius decreases. Also, we know that atomic radii increases as you go to the left. The atom becomes bigger. Now the same is true for ionic radii, but you have to be careful. You see, as we go from fluoride to oxide, it gets bigger. Oxide is bigger than fluoride. However, as we go from the anions to the cations, it doesn't get bigger, it gets smaller. So as we go from oxide to magnesium, the size decreases. But as we go from magnesium to sodium, it increases again. So, ionic radii increases as you go to the left if you're comparing two ions of similar charge. So if you're comparing two negatively charged ions, it increases as you go to the left. So nitride is going to be a lot bigger than oxide because these three ions have negative charges, and as you go to the left, it increases. If you look at the aluminum cation, which has a +3 charge, it's going to be even smaller than the magnesium cation. So I'm going to draw a red circle to indicate the size. So as you go from aluminum to magnesium to sodium, it increases. Which of the following elements has the most metallic character? Is it A, B, C, or D? So here we have lithium, sodium. To the right of sodium we have magnesium, and below magnesium we have calcium, strontium, and below strontium we have barium. And then we have the transition metals, and zinc is at the end of the 3D sublevel, and aluminum is not too far away from zinc. So the elements of blue are the ones that we're interested in. Metallic character increases as you go this way in the periodic table. So it increases as you travel to the left and as you go down. So this tells us that barium is the most metallic element out of those that are listed. It's the one that's furthest to the left, and then it's furthest down a column. So A is the right answer. Now let's think about this, like why that's the case. Let's say if we start with carbon. As we go to the left from carbon, you have boron, and then you have like beryllium, and then lithium. Carbon is a nonmetal, but as you travel to the left, the elements become metallic. Lithium is a metal. And as you go down, you have silicon, germanium, tin, and lead. So carbon is a nonmetal, and silicon is a metalloid. It conducts electricity only partially. Germanium is a metalloid, but as you go down, it turns the nonmetal, which eventually becomes a metalloid, becomes a metal. Tin is a metal. It conducts electricity very well. And lead is a metal as well. So as you can see, as you travel to the left of the periodic table, the elements become more metallic. And as you go down, metallic character increases. So it increases as you go down and to the left. So in our last example, we can see why barium has the greatest metallic character. It's further towards the left and furthest down in the periodic table. '94. Which of the following processes is associated with the energy change that occurs during the addition of an electron to a gaseous atom? This is the definition for electron affinity. Electron affinity is a process of adding an electron to a gaseous atom. Ionization energy involves the removal of an electron from a gaseous atom. Electronegativity is the ability of an atom to attract electrons to itself. So nonmetals are usually electronegative because they wish to acquire electrons. So fluorine, which is a halogen, is the most electronegative element. It really wants an electron. Now, lattice energy is the energy associated when gaseous ions they get together to form an ionic compound, and the energy that's released during that process that is associated with the lattice energy. So B is the right answer for this problem. Which group of elements has a valence shell electron configuration of Ns2? So the alkali metals would include like lithium, sodium, potassium, rubidium. The alkaline earth metals includes beryllium, magnesium, calcium, strontium, and so forth. And then on the right side of the periodic table, you have the halogens like fluorine, chlorine, bromine, iodine, and then you have the noble gases such as neon, helium, argon, krypton, and xenon. Now, the configuration for the alkali metals is NS1. For hydrogen, it's 1s1. For lithium, it's 2s1. Sodium, 3s1. Potassium, 4s1. Rubidium, 5s1. So NS1 corresponds to the alkali metals. NS2 corresponds to the alkaline earth metals. So B is the right answer. So beryllium would have the electron configuration 1s2, 2s2. Magnesium would end in 3s2. Calcium would end in 4s2. Strontium would end in 5s2. The halogens, their valence shell electron configuration ends with NP5. So like fluorine, its electron configuration is 1s2, 2s2, 2p5. For chlorine, it's like 1s2, 2s2, 2p6, 3s2, 3p5. Bromine ends in 4p5, iodine ends in 5p5. Now, the noble gases, with the exception of helium, they usually end in NP6. Helium ends in, it's 1s2, so that's an exception. But the rest is NP6. Neon is 2p6, argon 3p6, krypton 4p6, xenon 5p6. So NP6 corresponds to the the noble gases. NP5 is for the halogens. NS2 is for the alkaline earth metals, and NS1 is for the alkaline metals. So those are just some things to know for your next chemistry exam. 96. Which pair is isoelectronic? So isoelectronic means that it has the same number of electrons. So let's consider calcium. As an atom, calcium only has 20 electrons. For an atom, the number of protons and electrons are the same. Now, if we look at the potassium plus 1 ion, potassium has an atomic number of 19. And to find the number of electrons, it's the atomic number minus the charge. So 19 minus 1, potassium has 18 electrons. So A is eliminated. Those two do not have the same electrons. Let's look at D. So K plus, which you already have, and the oxide ion, O negative 2. So as we said, the number of electrons is the atomic number minus the charge. So 8 minus negative 2. The oxide ion has 10 electrons. So it's not the same as K plus, so that's eliminated. Now chlorine, which is an atom, it doesn't have any charges. The number of electrons is equal to the atomic number, which is 17, minus the charge of 0. So chlorine as an atom has 17 electrons. Rubidium with a plus 1 charge, the number of electrons is equal to the atomic number, which is 37, minus a charge of 1. So rubidium has 36 electrons, which is not the same as the chlorine atom, so C is eliminated. Now, if we compare Mg plus 2 and fluoride, let's see what we get. So magnesium has an atomic number of 12, minus the plus 2 charge, it has 10 electrons. And fluoride, which has an atomic number of 9, minus the negative 1 charge, also has 10 electrons. Whenever you have two negative signs, it turns into a plus. So 9 plus 1 is 10. So magnesium and fluoride are isoelectronic. They have the same number of electrons. 97. Which of the following elements is most similar to oxygen in chemical reactivity? So we need to look at the periodic table. So here is boron, carbon, nitrogen, oxygen, fluorine. And here we have chlorine. Fluorine is one of the elements we're considering. Nitrogen, Below oxygen, we have sulfur and then selenium. So the elements in blue are the one we're focusing on. Now, the one that's similar to oxygen is the one that's in the same column or the same group as oxygen, and that is the chalcogens. These elements, they're very similar in chemical reactivity. So selenium is more similar to oxygen in chemical reactivity than nitrogen, fluorine, or chlorine because selenium is in the same column or in the same group as oxygen. So C is the right answer. So anytime you need to find the element that's most similar to another element in chemical reactivity, make sure that those two elements are in the same column or in the same group, and that's going to give you the answer. 98. Which of the following elements has the highest fourth ionization energy? Ionization energy is the energy required to remove an electron from a gaseous atom. Now, for this particular problem, you need to know that it takes a lot of energy to remove a core electron compared to a valence electron. So let's find the number of valence electrons in each of these elements. Fluorine has 7 valence electrons. It's found in group 7A or group 17 of the periodic table. Phosphorus has 5, silicon has 4, aluminum has 3. The correct answer for this problem is answer choice A. Because aluminum has 3 valence electrons, the fourth electron is a core electron. And so the fourth ionization energy is going to be very high for aluminum. For silicon, the jump occurs during the fifth ionization energy because the fifth electron is a core electron. Phosphorus has 5 valence electrons, so the jump in ionization energy occurs during the sixth ionization energy. And for fluorine, since it has 7 valence electrons, the 8th electron is a core electron, so the 8th ionization energy will be very high for fluorine. So since we want the highest fourth ionization energy, we need to find out which one has a core electron for the fourth ionization energy, and that's aluminum. The first 3 are valence electrons. The fourth electron is the first core electron for aluminum. So A is the right answer for this problem. 99. Which of the following species is not paramagnetic? So we need to draw the orbital diagram for each of these elements. Let's start with manganese. Manganese has an atomic number of 25. And so it has the electron configuration argon, which covers everything from 1s2 to 3p6, so that's 18 electrons, plus 4s2, so that's 20, 3d5, so 25 electrons. Now, we just need to draw the orbital diagram for the last 2 sublevels. So this is going to be for 4s and then 3d. The 4s level is filled with electrons, but the 3d sublevel is half filled. Whenever you have unpaired electrons, you have an element that's paramagnetic. So manganese is paramagnetic. It's going to be weakly attracted to an external magnetic field. Now chromium, it's an exception. It has the electron configuration argon, 4s1, 3d5. So if we were to draw the orbital diagram, it would look like this. Chromium has 6 unpaired electrons, and so it's also paramagnetic. Now for zinc, the electron configuration is argon, that's 18, and then 4s2, 3d10. Zinc has an atomic number of 30. So notice that the electrons add up to 30. Argon is 18 plus 2, that's 20, plus 10 is 30. So if we were to draw the orbital diagram for zinc, everything would be completely filled. It has 2 electrons in the 4s level and 10 electrons in the 3d sublevel. So because it's completely filled, it is not paramagnetic. Rather, it is diamagnetic. And so zinc would be weakly repelled by an applied external magnetic field. So C is the right answer. So if you're wondering what the electron configuration for answer choice D, the Fe plus 2 ion, here's what you need to do. First, let's talk about Fe. Iron has 26 electrons, so the configuration is argon, which is 18, 4s2, that's 20, 3d6. So for the Fe plus 2 ion, you need to take away 2 electrons. Usually, you would take away 2 electrons from the higher energy level. That's it. That's the 4s level. So it's going to be 4s0, 3d6. So the 4s level is going to be empty. And so it's going to be 3D 1, 2, 3, 4, 5, 6. So as we can see, Fe has, well, the Fe plus 2 ion has 4 unpaired electrons. And so it's going to be paramagnetic as well. Number 100, which transition occurs at the highest frequency? Now let's say this is for an electron in a hydrogen atom. Is it going to be A, B, C, or D? Now, you need to know that frequency is proportional to energy. As the frequency of a photon that's emitted from an electron, as that frequency increases, the energy is going to increase as well, but the wavelength is going to decrease. The equation that we mentioned earlier that's related to this transition between an electron and a hydrogen atom, the equation is negative 2.178 times 10 to negative 18 joules times 1 over n final squared minus 1 over n initial squared. So the transition that is associated with the highest frequency is the one that's going to release the photon with the most energy. So this number is constant. So we could focus on this portion of the equation. Now typically, the one that's going to have the highest energy or the highest frequency is the one that goes to 1. Even though A, it looks like it changed by 4 levels, C is going to be the highest because it goes to 1. When it goes to 1, the energy change is going to be very, very high. A quick way to find it is just to use this part of the equation. Let's look at A. 1 over 10 squared, actually 1 over 6 squared, minus 1 over 10 squared. Type this in your calculator and get the decimal value for it. It's going to be very small. This is only 0.017. Now for B, 1 over 7 squared, n final is 7, and initial is 9, minus 1 over 9 squared. It's going to be a little higher. This is actually lower. I take it back. This is 0.008. So that's less than A. Now for D, it's going to be 1 over 2 squared minus 1 over 6 squared. And that's about 0.22, so that's the highest so far. And then for A, it's 1 over 1 squared minus 1 over 2 squared. And that's 0.75, that's the highest. So C is the right answer. The transition from 2 to 1 is going to release the most energy and or the highest frequency compared to the other transitions. Now, when you have a hydrogen atom, it looks something like this. This is the first energy level, and this is like the second energy level, and this is like the third energy level, and this is like the fourth. Notice that as you move away from the nucleus, the energy levels, they're closer together. So let's say if we drew the energy levels as a straight line. Let's say this is the hydrogen nucleus. Here's the first energy level. That's n equals 1. The second energy level will be like over here. And then you would have the third energy level. And then the fourth. And then the fifth. And then the sixth. And then like the seventh. So as you can see, the energy levels are getting closer and closer together. So a transition from, let's say, 5 to 3 compared to 2 to 1, the distance between 2 to 1 is greater than 5 to 3. So you can't just say 5 minus 3 is 2 and 2 minus 1 is 1, so 5 minus 3 is big. It doesn't work that way. As you can see, the distance between the first and second energy level is huge compared to the fifth and third energy level. Even if you were to go from the seventh to the third, the distance between the second and the first is much greater. And if you want to quantify it, just use this equation, 1 over n final squared minus 1 over n initial squared. 1 over 1 squared minus 1 over 2 squared, that was 0.75. But if you compare 1 over 3 squared minus 1 over 7 squared, it's going to be much smaller. The larger the denominator of a fraction is, the smaller the value of the fraction. So this would be like 0.091. So it's much smaller than 0.75. 101. Which of the following molecular geometry correctly describes the SF4 minus 2 ion? Well, let's draw it. The first thing we need to do is we need to add up the valence electrons. Sulfur has 6 valence electrons. Fluorine has 7, and there's 4 of them. And we have to add 2 electrons for the minus 2 charge. So we have 6 plus 28 plus 2. So this is equal to a total of 36. Now we need to subtract 36 by the highest multiple of 8, just under 36. So 8, 16, 24, 32. Now this number is going to give us the number of electrons on the central sulfur atom. So sulfur is going to have 4 electrons, or 2 lone pairs. Fluorine likes to form one bond. It has 7 valence electrons. It needs 1 more to get to 8. So it forms 1 bond to acquire that extra electron that it needs. Whenever fluorine has 1 bond, you need to add 3 lone pairs to it so it can have 8 electrons and satisfy its octet requirement. So if you add up the electrons, each fluorine atom has 8 electrons. 8 times 4 is 32, plus the 2 lone pairs, you get a total of 36 electrons. And typically, for this polyatomic ion, you would enclose it in a bracket and then put the negative 2 charge on the outside. This compound, or this ion, has a molecular geometry that's called square planar. Let's go over the other ones. Octahedral would look something like this. You would have a central atom with like 6 fluorine atoms attached to it. It could be something else. It could be bromine or chlorine, but it has like 6 outer atoms. That's the octahedral shape. A trigonal bipyramidal shape would look something like this. PCl5 is a good example of a trigonal bipyramidal shape, or a trigonal bipyramidal. By the way, what do you think the hybridization of the center element is for these 2 structures? Now, for the octahedral shape, we have 6 fluorine atoms attached to the central atom, so the hybridization is going to be S1P3D2. Notice that it adds up to 6. For the trigonal or trigonal bipyramidal structure, the phosphorus atom has 5 chlorine atoms attached to it, so the hybridization at phosphorus is going to be S1P3D1. Notice that 1 plus 3 plus 1 adds up to 5. For the square planar shape that we had at the beginning, what do you think the hybridization will be around the sulfur atom? So sulfur has 4 fluorine atoms, and it has 2 lone pairs, so it has 6 groups. So the hybridization is going to be S1P3D2. And the last one we need to consider is the square pyramidal shape. So typically you would have an atom with one lone pair and 5 atoms. So this structure is called square pyramidal. Now the atom in the center is attached to 5 fluorine atoms, plus it has a lone pair. So it has 6 electron groups. So the hybridization will also be S1p3d2. 102. Which of the following molecules has the longest bond length? In the periodic table we have fluorine, chlorine, bromine, and iodine, or iodine. Fluorine is the smallest, chlorine is a little bit bigger, bromine is bigger than fluorine, and iodine is the biggest. So as you can see, atomic size increases as you go down the group. So therefore, HI is going to have the longest bond length. So let's say if we were to draw these 4 compounds. So this will be HF, HCl, HBr, and HI. So hydrogen is relatively small. However, fluorine is a little bit bigger than hydrogen, and chlorine is bigger than fluorine, and bromine is bigger than chlorine, but iodine is the biggest. So if you were to compare the distance between the center of the hydrogen atom and the center of the fluorine atom with the center of hydrogen and the center of the iodine atom, you can see that the bond length of HI is much larger than the bond length of HF because iodine is a much bigger atom than fluorine. So the correct answer for this problem is answer choice D. 103. Which of the following statements is incorrect? So let's compare a triple bond with a double bond and a single bond. As you can see, triple bonds are very short and single bonds are very long. Double bonds are in the middle. Now, triple bonds are relatively strong and single bonds are relatively weak. A triple bond has 3 bonds. It's harder to break 3 bonds than it is to break 1 bond, so triple bonds are usually stronger than single bonds. And triple bonds tend to be short. The stronger the bond, the shorter it is. A bond is very weak if the atoms are far apart, but as those atoms approach each other, if they are close together, the bond is stronger. So now let's look at our choices and let's ID which one is incorrect. So looking at A, triple bonds are stronger than single bonds. That is a true statement. Looking at D, double bonds are shorter than single bonds. That's true. Single bonds are the longest compared to the 3 that are listed. Now C, single bonds are weaker than double bonds. That is also true. If we look at B, triple bonds are longer than single bonds. That's false. Triple bonds tend to be short. So B is the incorrect statement, and so B is the answer. (104) Determine the correct number of sigma and pi bonds in the following structure. So every single bond is a sigma bond. A double bond contains 1 sigma and 1 pi bond, and a triple bond contains 1 sigma and 2 pi bonds. So those are some things to know. Now, we need to draw the Lewis structure completely because you have to consider the carbon-hydrogen bonds. So let's expand the CH3 part of the molecule. So every bond contains 1 sigma bond. So let's count every bond as 1. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 sigma bonds. So we could eliminate answer choice A, B, and D. So we know C is the right answer. And a triple bond has 2 pi bonds. So out of the 3 bonds, 2 of them are pi bonds, 1 of them is a sigma, so we can see why C is the right answer. 105. Which of the following compounds has the highest melting point? We need to consider lattice energy. As the lattice energy increases, the melting point for an ionic compound will increase as well. Lattice energy is proportional to the charges of the ions, Q1, Q2, and it's inversely related to the size of the ions, or the radius, or the distance between the centers of the nuclei of the 2 ions. So what you need to know is that as the charge of the ions increases, the lattice energy will increase as well. And as the size of the ions decrease, the lattice energy will increase as well. The charge has more priority than the size, by the way. Now, sodium has a +1 charge, and fluoride has a -1 charge. The same is true for potassium and fluoride. So we could eliminate answer choice A and D because magnesium has a much larger charge. The same is true for oxide. And calcium has a +2 charge, and sulfur has a -2 charge. So B and C have the higher charges. The next thing we need to look at is size. So here's sodium, this is potassium, and magnesium is next to sodium. And then to the right, or in the upper right, we have oxygen and fluorine. And then below oxygen, we have sulfur. So if we were to compare magnesium and below that, which is calcium, magnesium is smaller than calcium. Atomic size increases as you go down. And looking at oxygen and sulfur, oxygen is smaller than sulfur. So B is the right answer. Magnesium oxide should have a higher lattice energy and a higher melting point because magnesium oxide is smaller than calcium sulfide. Now, if you were to go online and look up the melting points for these compounds, for sodium fluoride, the melting point is like 993 degrees Celsius. For magnesium oxide, it's very high. It's 2852. For calcium sulfide, it's 2525. And for KF, it's like 858. So if we were to compare NaF and KF, sodium is smaller than potassium. And so that's why sodium fluoride has a higher melting point than potassium fluoride. Even though the charges are the same, sodium is smaller than potassium. And as the size decreases, the lattice energy increases, and the melting point will be higher. Now, if we were to compare sodium fluoride with magnesium oxide, we could see that the magnitude of the charges found in magnesium oxide is greater than that in sodium fluoride. Magnesium has a +2 charge, sodium has a +1 charge. Oxide has a -2 charge, fluoride has a -1 charge. So if you multiply Q1 and Q2, for sodium fluoride it's 1 times 1, which is 1. For magnesium oxide it's 2 times 2, which is 4. And because the product of the charges is so much higher in magnesium oxide, we could see why the melting point is significantly higher. 2,852 compared to 993. That's an increase of almost about 1900 degrees Celsius. Now, if we compare magnesium oxide with calcium sulfide, the charges are the same, but since magnesium is smaller than calcium and since oxygen is smaller than sulfur, magnesium oxide has a higher melting point than calcium sulfide. It's about 300 degrees Celsius more than calcium sulfide. And it's due to the size. So these are the important factors you need to look at. So first, look at the ionic compounds with the higher charge if you want to find which one has the highest melting point. And then the next thing you should take into account is the sizes of the ions. The smaller the ions, the greater the lattice energy will be, and thus the higher the melting point. Which of the following molecules has the largest dipole moment? So basically, we need to find out which molecule is polar. Let's start with xenon tetrafluoride. Xenon has 8 valence electrons, and fluorine has 7 times 4. 7 times 4 is 28, plus 8, that's 36. If we subtract that by the highest multiple of 8, just under 36, that's 32. This tells us that there are 4 electrons, or 2 lone pairs, on the center xenon atom. So xenon tetrafluoride looks like this. If we were to draw PCl5, phosphorus has 5 valence electrons, chlorine has 7. 7 times 5 is 35, plus 5, which is 40. Because 40 is a multiple of 8, there are no lone pairs on the central phosphorus atom. So the Lewis structure looks like this. For sulfur hexafluoride, it's 6 times 7. Fluorine has 7 valence electrons. 6 times 7 is 42. Sulfur has 6 valence electrons. 42 plus 6 is 8. 48 is a multiple of 8, so sulfur has no lone pairs on it. So the Lewis structure would look like this. We would have an octahedral molecular geometry. Now for SF4, let's write this one. Sulfur has 6 valence electrons. Fluorine has 7 times 4. So that's 28 plus 6, that's 34. If we subtract that by 32, the highest multiple of 8, just under 34, we get 2 left over. So sulfur has, well, I should probably draw it this way. It has 1 lone pair and 4 fluorine atoms. So it has a shape, it has a seesaw shape. That's the molecular geometry for it. Now if we look at the polarity, all of the dipole moments for xenon tetrafluoride cancel. Now even though it has lone pairs, the lone pairs are like opposite to each other. They're like symmetrically apart. And due to the symmetry of the molecule, it's nonpolar. Now for PCl5, all of the dipole moments cancel out, and so it has a net dipole moment of 0. The same is true for sulfur hexafluoride. All of the arrows cancel. They all point in opposite direction. So therefore it's nonpolar. The only one that has a net dipole moment is sulfur tetrafluoride. Now even though these two arrows are opposite to each other and they cancel, there's nothing to cancel with these 2 fluorine atoms. They point towards the right. And so this molecule has a net dipole moment and it's polar. So because the other ones are nonpolar, because they have a dipole moment of 0, A is the one with the largest dipole moment. It's the one that's most polar. So A is the answer. So let's talk more about the polarity of these molecules. Let's consider sulfur hexafluoride. And let's see why it's nonpolar. Now if we were to draw the dipole moment, you have to point the arrow towards the more electronegative fluorine atom. Notice that the 2 arrows in red, they cancel because they point in opposite directions. Now the 2 arrows in blue, they're opposite to each other, and so they cancel as well. And the 2 arrows in purple are opposite. So as you can see, there's no net dipole moment because it's completely nonpolar. All of the dipole moments cancel. Now in sulfur tetrafluoride, they don't cancel. Let's see why. Because of the seesaw molecular geometry, only 2 arrows cancel, and that's the one in red, because those 2 are directly opposite to each other. They're 180 degrees apart. But the 2 arrows in blue, they don't cancel. Well, they partially cancel, but not completely. And plus we have this lone pair. Whenever you have 2 lone pairs that are like opposite to each other, like in the case of xenon tetrafluoride, because these 2 lone pairs are opposite to each other, they sort of cancel. But when you only have 1 lone pair in a molecule, it's going to be polar because there's no other lone pairs to cancel it. Now let's look at the 2 blue arrows. Let's see why they don't cancel out completely. So one arrow, let's go into physics a little. One arrow goes this way and the other arrow goes like that. Now let's think of it as a vector. The arrow on top has an x component and a y component. The arrow on the bottom also has an x component and a y component. As you can see, the y components of these 2 vectors, they cancel because one is up, the other is down. However, the x components, they're additive. They're both going towards the right. And because they go in the same direction, we get a larger arrow in the x direction. And so that's why there's a net dipole moment that points towards the right. And so SF4 is a polar molecule. It has the largest dipole moment. And that's why it was the answer. Which of the following molecules has a bond order of 3? This is going to be the one that likes to form a triple bond. Let's start with fluorine. Fluorine has 7 valence electrons and it needs one more to get to 8. So fluorine likes to form one bond to get that one extra electron that it needs. And so fluorine, which is diatomic, looks like this. Because it has a single bond, it has a bond order of 1. That's the quick and easy way to find the bond order. Now oxygen has 6 valence electrons. It needs 2 more to get to 8. So oxygen likes to form 2 bonds to get the 2 extra electrons that it needs. So oxygen likes to form double bonds. And this is the Lewis structure for O2. As you can see, oxygen has a bond order of 2. Now nitrogen has 5 valence electrons. It needs 3 more to get to 8. So nitrogen likes to form 3 bonds to get the 3 electrons that it needs, so it could satisfy its octet requirement. So nitrogen likes to form a triple bond. And so it has a bond order of 3. And so C is the answer. Hydrogen has 1 valence electron. It needs 1 more to get to 2 because in the first row elements can only have 2 electrons in their shell. So hydrogen, since it has 1 valence electron, it only needs 1 more to get to 2, so it only forms 1 bond. So this is the Lewis structure for hydrogen, and therefore it has a bond order of 1. So C is the right answer. Nitrogen is the one that has a bond order of 3 since it likes to form triple bonds. 108. Which of the following types of compounds has the lowest melting and boiling point? Is it A, B, C, or D? The correct answer for this problem is answer choice D. Molecular compounds have the lowest melting and boiling points. So for an example, let's say if we have a nonpolar molecular compound like methane. The melting point for that is it's very low, it's like negative 182. The boiling point is also low. It's negative 162. Now let's say if we have a polar molecular compound like sulfur dioxide. The melting point for this one, it's a little bit higher than the nonpolar molecular compound. It's about negative 72. And the boiling point is a little higher. It's negative 10. Now if you have a molecular compound that has hydrogen bonding like water, it's going to be a little higher. The melting point is 0 for water and the boiling point is 100. But relatively speaking, molecular compounds have a much lower melting and boiling point compared to ionic compounds, network solids, and metals. So as you can see, the boiling points for the molecular compounds, they were about less than 100 degrees Celsius. Let's consider the ionic compounds. Sodium chloride has a melting point of about 801 degrees Celsius. That's much higher than water. And magnesium oxide, that's another ionic compound between a metal and a nonmetal, the melting point is 2,852 degrees Celsius. It's very, very high. Now let's move on to the network solids. Network solids, such as carbon, graphite, and diamond, the melting point is above 3,000 degrees Celsius. For silicon carbide, which is another network solid, that's around 2,700 degrees Celsius. And boron nitride, another network solid, it's close to 3,000 degrees Celsius. So network solids, they have a very, very high melting point. Metals also have high melting points, but metals can vary. Some metals have a low melting point, like mercury. Mercury is a liquid under room temperature conditions. Its melting point is around negative 39, so it's pretty low. The melting point of like zinc metal, that's about 420. That's much higher than water. And then the melting point of a metal like tungsten is extremely high. It's like 3,400 degrees Celsius. Most metals have a very high melting point, but as you can see, they can vary. But generally speaking, molecular compounds have a very low melting and boiling point relative to these other 3 compounds. So D is the right answer. 109. Which of the following is not conductive to electricity? We can eliminate answer choice D. Copper is a metal and metals conduct electricity. A, B, and C are ionic compounds. Sodium chloride, which is composed of a metal and a nonmetal, that is an ionic compound. Now, if you dissolve sodium chloride in water, it's going to be conductive to electricity. So we could eliminate B. Whenever you hear the word aqueous, that means it's dissolved in water. So we have a salt water solution which conducts electricity. Now, an ionic compound in a liquid state can also conduct electricity. So if you fuse an ionic compound or if you melt it to the liquid state, it will be conductive to electricity. Solid ionic compounds cannot conduct an electric current. So A is the answer. So make sure you keep this in mind. Ionic crystals do not conduct electricity in the solid state, but they can in the liquid state or if they're dissolved in a solvent like water. 110. Which of the following elements is a liquid at room temperature? Fluorine is a gas at room temperature. Chlorine is a gas which has like a yellowish green color. Bromine is a red liquid, and iodine is a purple or violet solid. So the answer for this problem is C. You need to know that bromine is a liquid at room temperature. Which of the following statements is/are correct? Ionic compounds dissolved in water or in a liquid state conducts electricity due to the presence of free-flowing ions. That is a true statement. In a solid state, the ions are not free to move, and that's why solid ionic crystals do not conduct electricity. But in a liquid state or when dissolved in water, the ions, they're free to move. So let's say here we have a salt water solution. So you have free-flowing sodium ions and chloride ions. And because they're free to move, the solution can conduct electricity. B. Metals conduct electricity due to the presence of a free-flowing sea of valence electrons. That is true. In order for any type of substance to conduct electricity, there has to be a charge carrier. So there has to be some particle that carries a charge that's free to move. In the case of ionic compounds, it's free-flowing ions. In the case of metals, it's free-flowing valence electrons. The electrons are the charge carriers in metals. C. Graphite conducts electricity due to the delocalization of free-flowing pi electrons. That is true. Make sure you know that. And diamond is an excellent conductor of heat but not of electricity. That is true. In diamond, the electrons are not free to move. So that's why diamond doesn't conduct electricity, but it conducts heat very, very well. So E is the right answer for this problem. All of the above statements are true. So make sure you know the reasons behind why certain compounds can conduct electricity and why others cannot. So just make sure that you study the key terms for these types of problems. So for ionic compounds, your key term is free-flowing ions. For metals, it's free-flowing electrons. For graphite, it's the delocalization of free-flowing pi electrons. (112) Which of the following is not an allotrope of carbon? Allotropes of carbon are made up of elemental carbon, but the atoms are arranged in different ways. It's just different forms of carbon. Graphite is completely composed of carbon atoms. Buckminster fullerene is also an allotrope of carbon. It's a molecule that contains 60 carbon atoms. And diamond also is made up of elemental carbon. Moissanite is composed of silicon carbide, and so moissanite is not an allotrope of carbon. Moissanite actually looks very similar to diamond. It has that same sparkle as diamond, but it's different. graphite has these hexagonal shapes, and it has double bonds. Now this is just part of the structure. This structure extends for like thousands and thousands of chains. So that's an example of the graphite structure. It has a lot of alternating single and double bonds. So because of this conjugated system, these pi electrons, which are the electrons in a double bond, they're free to move around the graphite structure, and so that's why graphite conducts electricity. And there's another layer of carbon atoms in the graphite structure. And so graphite has like a two-dimensional structure, and there's a weak interaction between the different layers of the graphite structure that holds them together. But that's the structure for graphite. It conducts electricity, and it's made up of carbon-carbon bonds. It has alternating single and double bonds. Now diamond, it's made up of carbon atoms as well, but diamond has a 3D structure as opposed to a two-dimensional structure. So like in graphite, the carbon atoms have 4 bonds, but every carbon atom at least has one double bond in graphite. So this is like a graphite structure. In diamond, the carbon atoms, they all contain single bonds. And so they have like a tetrahedral structure. And because it doesn't have any alternating double bonds, the electrons in diamond, they're not free to move. They can't move from one carbon atom to another. And so that's why diamond doesn't conduct electricity. And Buckminster fullerene, you can check it out in Google Images. It looks like a ball of carbons. It's a ball of 60 carbon atoms. I'm not going to draw it here. But that's it for this problem. 113. Which of the following compounds will form a clear solution when dissolved in water? What you need to know for this problem is that transition metals form colored solutions when dissolved in water. Copper sulfate will form a nice blue solution in water. Potassium permanganate can form a pink/purple color. It really depends on the concentration. If you have a very dilute concentration of KMnO4, it's going to look light pink. If it's concentrated, it can look purple, and if it's like very concentrated, it can look even black or like dark violet. Nickel chloride usually forms a green solution in water. So copper, manganese, and nickel are all transition metals. Most transition metals usually form colored solutions when dissolved in water. Now there are some exceptions. One exception is zinc. Zinc chloride, zinc sulfate usually is a clear solution if you dissolve it in water. So the correct answer for this problem is potassium bromide. Potassium is not a transition metal, rather it's an alkali metal. And alkali metals like potassium, sodium, lithium, they don't really form colored solutions. So A is the right answer. 114. Which of the following gases is least soluble in water? Is it A, B, C, or D? Water is a polar compound, and polar gases is going to have a high solubility in water. Nonpolar gases will have a low solubility in water. So we need to find out which gases are nonpolar if we want to find the gas that is least soluble in water. So NH3 has hydrogen bonded, and because of that, ammonia, NH3, is very polar. So we could eliminate A. Carbon monoxide is also polar. It has a net dipole moment, and the Lewis structure looks like this. The dipole points towards the more electronegative oxygen atom, and so that molecule is polar. Carbon dioxide is a nonpolar molecule, and nitrogen gas is also nonpolar. Carbon dioxide looks like this. It has a linear molecular geometry with a bond angle of 180, and the dipole moments, they cancel. The molecular geometry for NH3 is trigonopyramidal or trigonal pyramidal, and it has a bond angle of 107. Now, nitrogen gas also has a linear shape. And because it's composed of the same element, it's also nonpolar. So, is the answer B or is it C? Because both of these gases are nonpolar. So therefore, they have a very low solubility in water. However, the solubility of carbon dioxide can increase because carbon dioxide can react with water, and it can be stored in water in a form of carbonic acid. And also, carbon dioxide, has polar bonds. Even though the molecule overall is nonpolar, the bonds are polar. And so, the carbon is partially positive, the oxygen is partially negative. And those polar bonds could also increase the solubility in water. Whereas nitrogen gas is completely nonpolar. The molecule is nonpolar and it doesn't contain any polar bonds, so therefore we should expect that N2 should be least soluble in water. By the way, when carbon dioxide reacts with water to form carbonic acid, the carbonic acid is soluble in water. This is the Lewis structure of carbonic acid. As you can see, it has hydrogen bonds, and so therefore this form of this molecule is very polar. So when CO2 reacts with water, it can dissolve in water in the form of carbon or carbonic acid. A third reason why N2 is less soluble than CO2 in water is due to the molar mass. So I'm going to write less soluble for N2. The molar mass of nitrogen gas is about 28, and for carbon dioxide it's 44. So because nitrogen has a smaller or lower molar mass than CO2, it has a lower boiling point and thus a higher vapor pressure. Gases with high vapor pressures, they can easily escape the solution, and so the solubility is going to be lower. Because CO2 is heavier, it's going to have a higher solubility in water. So because it's heavier, it has a higher boiling point relative to N2, and it's going to have a lower vapor pressure relative to nitrogen gas. So thus, relative to nitrogen gas, we should expect that it's going to be more soluble in water. So if you have two nonpolar gas molecules, and if you want to find out which one is more soluble in water, let's say if we're comparing hydrogen gas and nitrogen gas, both of these gases are completely nonpolar. The only thing that we can look at is the molar mass. For hydrogen gas, the molar mass is about 2 grams per mole. For nitrogen, it's about 28 grams per mole. And so we should expect that the lighter gas molecule, which is hydrogen, it's going to have a much higher vapor pressure. So it can easily escape the solution. So therefore, it should be less soluble in water. The heavier gas should be, it should have a higher solubility in water. 115. Which of the following compounds has the name sodium superoxide? Oxide has an oxidation state of -2. So this is the most common form of oxygen as an ion. And then there's peroxide. You probably have hydrogen peroxide in your bathroom or something, or in your cabinet. Peroxide is a form of oxygen where the oxidation state is -1. And then there's superoxide. Superoxide has oxygen with the oxidation state of -1/2. So that's what you need to know. So in this problem, to find the answer, we need to know which one has an oxidation state of -1/2. So let's start with Na2O. Let's write an equation. So we have 2 sodium atoms plus an oxygen atom, and the net charge equals 0. So we're going to plug in +1 for Na and solve for oxygen. So let's put X for oxygen. So this is 2 plus X equals 0. If we subtract by 2 from both sides, we can see that the oxidation state of oxygen is -2. So this is sodium oxide. Now for NaO, we're going to write an equation. Na plus O, or X, is equal to 0. So sodium has a +1 charge, and then plus X equals 0. So we can see that X is -1. So the second compound has the name sodium peroxide. C is the right answer. If we write an equation, it's going to be Na plus 2O, or 2X, is equal to 0. So for Na, the oxidation state is 1. And if we subtract both sides by 1, we'll get 2X is equal to -1. So our next step is to divide both sides by 2. So X is -1/2. So this compound is called sodium superoxide. (116) Which of the following halogens is most reactive? What you need to know is fluorine is the most electronegative element. Electronegativity increases towards fluorine. So electronegativity increases as you go to the right and as you go up. So below fluorine you have chlorine, and then bromine, and then iodine. So fluorine is the most reactive nonmetal. So the answer is A. After fluorine, the second most reactive nonmetal is chlorine, and then bromine, and out of these 4 halogens, iodine is the least reactive. (117) Which of the following elements is most electropositive? So we know that electronegativity increases towards fluorine. However, electropositivity increases this way. So nonmetals tend to be electronegative, and metals are usually electropositive. Nonmetals like to acquire electrons, and so that's why they're electronegative. And as they acquire these electrons, they develop a negative charge. Metals, which are electropositive, they like to give away electrons. And as they lose electrons, they generate positively charged cations. So we need to find out which metal is the most reactive. That's going to be the metal that is the most electropositive. So let's place these elements in their respective location in the periodic table. So here's hydrogen, and below hydrogen you have like lithium, sodium, potassium, rubidium, and then you have cesium. Magnesium is to the right of sodium. And then you have the transition elements, and then zinc is in the upper right corner of the 3D block, or the D block, I should say. And then after zinc, you have elements such as gallium, arsenic, selenium, and above selenium you have sulfur. Sulfur in its natural form exists as an S8 molecule. And then above and to the right of sulfur you have fluorine. So nonmetals are electronegative. We can eliminate D and E. So we need to find out which metals are most reactive. Metallic character, or metal reactivity, increases as you go to the left and as you go down. So cesium is the most reactive metal. Also, electropositivity increases as you go towards cesium and francium. So as you go to the left and to the right, the elements are more electropositive. So A is the right answer. 118. Which of the following metals is resistant to corrosion by oxygen. So the first thing you might be thinking is the activity series. Sodium is more active than aluminum, and aluminum is more active than zinc, which is more reactive than Fe. Hydrogen is like the standard. And below hydrogen, you have elements like copper, silver, and gold. Gold is very resistant to corrosion. In fact, it's rare that gold tarnishes. It can, but it doesn't corrode very easily. Copper and silver, they can corrode, but very slowly. Now, the active metals, they corrode pretty quickly. So we could eliminate A. Sodium metal is very reactive. If you put it in water, it's going to explode, and it can definitely react with oxygen on contact. We know iron metal corrodes. Iron metal will form rust in the presence of air and water. So C is out. Zinc can corrode as well. Even though aluminum is more reactive than zinc and iron, aluminum is resistant to corrosion. Consider this piece of aluminum metal. Initially, aluminum will react with oxygen in the air, and you're going to get a thin layer of aluminum oxide. As this passive layer forms, it prevents further corrosion. It protects the atoms on the inside. So the oxygen in the air, it can't access these aluminum atoms on the inside, and so that passive layer, it acts as a barrier, preventing further corrosion, and that's why aluminum is resistant to oxidation or corrosion by oxygen, because of that passive layer. And there are other elements that can form this passive oxide layer as well. Titanium is one of them. So make sure you know that aluminum is resistant to corrosion by air due to that passive oxide layer that it forms. So B is the right answer. That's it. 119. Which of the following statements is/are correct? Photosynthesis is a process that uses sunlight, carbon dioxide, and water to produce oxygen gas and carbohydrates. That is a true statement. So photosynthesis, it takes in CO2 and water, and using the energy of the sun, plants, they can absorb CO2 and water and make carbohydrates like glucose, which is a type of sugar, and oxygen gas for us to breathe. The opposite process is cellular respiration. Animals, even plants, and most cells, they consume sugar, use up oxygen, and they make CO2 and water. So respiration is the reverse of photosynthesis. Nitrogen fixation occurs during lightning storms. This is true. In a lightning storm, nitrogen gas can be fixed into compounds that contain nitrogen and oxygen. And this is very useful for plants. They can fertilize the soil and allow plants to grow. Now, looking at C, transition metals usually possess a variable oxidation number. And that is true. Chromium is a good example. You have the chromium plus 3 ion, the chromium plus 2 ion, and then there's chromate, which has a positive 6 oxidation state. And so that's 3 different oxidation numbers. Another example is iron. You have Fe plus 2, Fe plus 3. So most transition metals contain a variable oxidation number. D is also true. Soap reacts with ions in hard water such as calcium to form a scummy precipitate. So the correct answer for this problem is E. All of these statements are true. So these are just some facts to know. 120. 45 milliliters of a solution of 0.275 molar NaOH was mixed with 85 milliliters of a 0.95 molar solution of sodium hydroxide. What is the concentration or molarity of the final solution? So here we're taking two solutions of the same substance, we're going to mix it together, and we're going to try to find the molarity of that new solution. Now the volume of the new solution will increase. But it turns out that the molarity is going to be the weighted average of the two solutions. So it's going to be somewhere between 0.275 and 0.95. Do you think it's going to be closer to 0.275 or closer to 0.95? The weighted average of the concentration is going to be closer to 0.95 because we have more of the higher concentrated solution than the dilute solution. 85 is much more than 45. So the answer should be close to 0.95 rather than 0.275, but it's still between the two numbers. Now, the simplest way to get the answer is to find the moles of each solution, add them up, then divide by the total volume. So here's the equation that you need. So the moles that's in the first solution is going to be the molarity times the volume. And the moles that's in the second solution is the molarity times the volume as well. So M1V1 plus M2V2 represents the total moles in both solutions. And then we're going to divide that by the total volume, and that's going to give you the concentration of the new solution. By the way, this equation can extend. Let's say if you were to combine three solutions of the same substance, then you can add M3V3 and then plus V3 on the bottom to get the combined molarity. And it can keep on going forever depending on how many solutions you're adding together. But for now, we only need two. So let's use the equation. Now we don't have to change the volume we don't have to convert milliliters into liters, because if we use milliliters on top and on the bottom, it's going to cancel. And so we'll still get the right answer if we use liters or milliliters. But they have to match. So if you use milliliters on top, you can't use liters on the bottom. It has to remain milliliters. So M1, that's going to be 0.275, and times the volume, which is 45 milliliters, plus M2, which is 0.95 times 85 milliliters, divided by the total volume, 45 plus 85. So 0.275 times 45 plus 0.95 times 85. The total moles is about 93 well, that's not really moles because that's like molarity times milliliters, so that's like millimoles. So we have 93.125 millimoles, which is like 0.093 moles. And then 45 plus 85, so that's 120 milliliters. If we divide these two, the concentration should equal 0.716. So let me write the units here. This is millimoles, and this is milliliters. The milli part is going to cancel, and then you're going to get moles per liter, which is molarity. So D is the right answer for this problem. 121. Nitrogen monoxide reacts with oxygen gas to produce dinitrogen pentoxide when the stopcock valve is released. Calculate the partial pressure of N2O5 when the reaction is complete at 298 Kelvin. So feel free to take a minute and see if you can solve this problem. So pause the video and unpause it when you're ready. So let's begin. The first thing we need to do is we need to find the moles of NO and O2. Now the moles are going to be the same because they have the same PV value. The pressure times the volume is going to be 6 liters atmospheres. 3 times 2 is 6. But let's start with NO. So using PV equal nRT, the pressure is 3 atm, volume is 2. We're looking for N. R is 0.08206, and Kelvin temperature is 298. So to solve for N, it's going to be 3 times 2, which is 6, divided by 0.08206. So that's 73.1, and then divide that result by 298. So N is equal to 0.2454 moles. Now for O2, R and T is going to be the same. If you plug in 3 for V and 2 for ATM, PV will equal 6, so you're going to get the same number of moles. Now what we have to take into account is we need to write a balanced reaction, and we need to know which of these gases is the limiting reactant. So let's do that now. So NO reacts with O2 to form N2O5. So notice that we have an odd number of oxygen atoms. To make it simple, let's put a 2 in front so we can make it even. So we have 10 oxygen atoms. So now we have 4 nitrogen atoms on the right side and we need a 4 on the left. So now the nitrogen atoms are balanced. We have 10 oxygens on the right side. We have 4 in this compound. We need 6 more. So 6 divided by 2 is 3. We need to put a 3 in front of O2 to balance the reaction. So now it's balanced. So we have 0.2454 moles of NO and O2. So how can we find which of these is the limiting reactant? If you have the moles of both reactants and you wish to find which one is limiting, divide the moles by the coefficient in a balanced reaction. The one that's going to give you the smaller number is the limiting reactant. The larger the denominator of a fraction, the smaller its value. So NO is going to be a limiting reactant. If you take 0.2454 and divide it by 4, you're going to get 0.061. And 0.2454 divided by 3 is 0.08. So NO has the lowest mole per coefficient ratio, so it's the limiting reactant. We're going to use that to convert it to the moles of N2O5. So starting with 0.2454 moles of NO, we're going to multiply it by 2 moles of N2O5 per 4 moles of NO. So it's based on the coefficients of the reaction. That's how we got the 2 to 4 ratio. So 0.2454 times 2 over 4, which is basically half of it, that's going to equal 0.1227 moles of the product N2O5. Now our goal is to find the partial pressure of N2O5. Now that we have the moles of N2O5, we can use PV equal nRT to get the partial pressure. Now, once the stopcock is removed, N2O5 will have a volume of 5 liters because it can be in the 3-liter container and in the 2-liter container. So it's going to be spread out in a volume of 5 liters. So we have to use 5 for V now. So first, let's make some space in order to complete this problem. So PV equals nRT. So we're looking for P. The volume is now 6 liters. N is 0.1227. R is the gas constant, 0.08206. And the temperature is 298 Kelvin. So to solve for P, let's multiply the 3 numbers on the right side. So 0.1227 times 0.08206 times 298. And you should get about 3.0 for that. So divide both sides by 6. 3 divided by 6 is 0.5. So the partial pressure for N2O5, dinitrogen pentoxide, is 0.5 atmospheres. So therefore B is the right answer. 122. 35 grams of ethane reacts with excess oxygen gas to produce carbon dioxide and water. If this process is 80% efficient, how many grams of carbon dioxide should you expect to collect in this reaction? So this is like a percent yield problem. The only difference is they gave us a percent yield. It's 80% efficient, so we're looking for the actual yield. But to do that, we got to find a theoretical yield first. So let's write a balanced reaction. Ethane has the chemical formula C2H6. Methane has 1 carbon, ethane has 2 carbons, propane has 3, butane has 4, pentane has 5, hexane is 6, heptane is 7, octane is 8, nonane is 9, decane is 10. Make sure you know your alkanes up to 10. And now this is going to react with O2, and it's going to produce CO2 and water. So go ahead and pause the video and go ahead and balance this combustion reaction. Now, whenever you want to balance a combustion reaction, the first thing you need to do is balance the carbon atoms. So we have 2 carbons on the left. We need to put a 2 in front of CO2. So now let's balance the hydrogen atoms. We have 6 on the left. We need 3 on the right. Notice that we have an odd number. Whenever you see this situation, go ahead and double it, particularly for combustion reactions. So I'm going to put a 2 in front of C2H6, and I'm going to rebalance it. So now I have 4 carbon atoms on the left. So I need to put a 4 in front of CO2. And I have 12 hydrogen atoms on the left, 2 times 6. So I need to put a 6 in front of H2O. So now I'm going to add up all of the oxygen atoms that I have. I have 8 oxygen atoms in CO2. 4 times 2 is 8. And 6 from water. So that's 14. 14 divided by 2 is 7, so I need a 7 in front of O2. So now the reaction is balanced. So let's go ahead and calculate the theoretical yield for this reaction. So we have 35 grams of C2H6. We need to convert grams into moles, so we got to find the molar mass of C2H6. So carbon's about 12.01. Let's multiply that by 2. And hydrogen is 1.008. Let's multiply that by 6 and add those two numbers. The molar mass for C2H6 is about 30.068 grams per 1 mole of C2H6. Now our goal is to convert to grams of CO2, because that's going to be the theoretical yield for carbon dioxide. At this point, we need to use the molar ratio, and it's a 2 to 4 ratio. So for every 2 moles of ethane that reacts, 4 moles of CO2 are produced. Now the last thing we need to do is convert moles of CO2 into grams. So if we add up carbon, 12.01, plus oxygen, which is 16, and there's 2 of them, so times 2. So 16 times 2 plus 12.01, you should get a molar mass of 44.01 grams of CO2. So 35 divided by 30.068 times 4 divided by 2 times 44.01, you should get a theoretical yield of 102.46 grams. So this is the maximum amount of CO2 that can be produced in this reaction. So if this process was 100% efficient, this is how many grams of carbon dioxide that we should expect to collect. But since it's only 80% efficient, we're going to multiply it by 0.80. 80% is 0.80. You just divide 80 by 100. So if you multiply it by 80%, the actual yield is 81.97 grams, which we can round it as 82.0. So theoretical yield times the percent yield is equal to the actual yield if you rearrange the equation. 123. Which of the following compounds contains the greatest percentage of oxygen? Is it A, B, C, or D? So in this problem, we need to calculate the mass percent of oxygen in each one of those choices. The mass percent is equal to the mass of the element divided by the total mass times 100%. So let's start with compound A. So we have 3 oxygen atoms, so that's going to be 3 times 16 divided by the total molar mass. So there's 5 carbon atoms, so 5 times 12 plus 10 hydrogen atoms, so that's 10 times 1, and then the 3 oxygen atoms, or 3 times 16, and then times that by 100%. So the mass percent for answer choice A is about 40.7%. So now let's do the same thing for B. So it's going to be 2 oxygen atoms, 2 times 16, divided by 2 carbon atoms, so that's 2 times 12, plus 4 for hydrogen, and plus 2 times 16 for the 2 oxygen atoms, times 100%. So that's 32 divided by 24 plus 4 plus 32. So that's going to be about 53.3%. By the way, you can put this in brackets or in parentheses when you type this in your calculator to make it faster. So now let's calculate the mass percent for the other two. So for C, it's going to be 16 because we only have one oxygen atom, plus 12 for carbon, 4 for hydrogen, and 16 for the other oxygen, times 100%. So 16 divided by 32. So compound C is 50% oxygen by mass. Compound D has one oxygen atom, two carbon atoms, so that's 12 times 2, 6 hydrogen atoms, and the oxygen that we've accounted for already, times 100%. So if you type it in correctly, you should get 34.8%. So the correct answer for this problem is B. It contains the greatest percentage of oxygen. 124. What volume of Ki is needed to titrate 73 milliliters of KMnO4 according to the net ionic equation shown below? So notice that we have molarity, volume, and another molarity and another volume. So whenever you see a situation like this, we can use the equation M1V1 is equal to M2V2. But we need to take into account the molar ratio. And the way we solved an acid-base titration using this equation before, it's going to be a little different for this particular video. So for example, if you had H2SO4, because there's two hydrogens in H2SO4, you would put a 2 in front of one side of the equation. But here it's going to be a little different. So let's say the left side represents potassium iodide and the right side is for potassium permanganate. The coefficient for Ki is 10, and the coefficient for potassium permanganate is 2. Now, to get the right answer, you need to switch the 10 and 2. The 10 is going to go on the right side, and the 2 is going to go on the left. If you do it this way, you're going to get the right answer. So we're going to put a 2 on this side and a 10. I'm going to solve this problem both ways, using the equation and using stoichiometry. So now let's plug in the information that we have. M1 is 0.35, that's for Ki. We're looking for V1. And M2 is 0.225, and V2 is 73. So to get the answer, type it like this in your calculator. It's going to be 10 times 0.225 times 73, and then take that result, divide it by 2. You should get like 82.1 at this point, and then divide it by 0.35. The final answer should be equal to 234.6 milliliters. So D is the right answer. But now let's try to get the same answer using stoichiometry. So, since we want to find the volume of Ki, let's start with the other reactant. We're going to start with the molarity. So molarity could be written as moles per liter, and this is for KMnO4. Now we need to multiply by the liters. To convert milliliters to liters, divide by 1,000. So 73 milliliters is 0.073 liters. So liters cancel, and now we can convert moles of KMnO4 to moles of Ki. And I deleted the reaction, but if you pause the video and rewind, we had a 10 in front of I, or I minus, and a 2 in front of permanganate. So it's a 10 to 2 ratio. So for every 2 moles of KMnO4, or just MnO4 minus, we require 10 moles of iodide, or just Ki. So moles of KMnO4 cancel. The last thing we need to do to get the molarity, well actually we need the volume. we need to use the molarity of Ki. So a 0.35 molar solution means that there are 0.35 moles of Ki per 1 liter of solution. And since the final answer is in milliliters, we need to multiply by 1,000 milliliters per 1 liter. So the units moles of Ki cancel, and liters cancel as well. And so now let's type it in. So 0.225 times 0.073 times 10 divided by 2 times 1,000 divided by 0.35. So you should get the same answer, 234.6 milliliters. So D is the right answer. 125. Use the bond dissociation energies to estimate the enthalpy of the reaction shown below. So there was one example which we covered earlier in this video where we calculated the enthalpy of the reaction using heats of formation. And the way we did that was we did products minus reactants. Well, if you're using bond dissociation energies, it's going to be reactants minus products. So make sure you remember that difference. So let's go ahead and do this one. So delta H is equal to reactants minus products. By the way, I know I have carbon solid, but let's assume that this is the gaseous form of carbon. So let's say this reaction is gaseous carbon plus gaseous chlorine, yielding gaseous carbon tetrachloride. So we need to consider the bonds in Cl2. We have to break those bonds, and anytime you break a bond, you got to put energy into it. It's endothermic. And the bonds that are formed in CCl4, energy is going to be released. So Cl2 looks like this. It's two chlorine atoms connected by means of a single bond. And CCl4 has a carbon with 4 chlorine atoms. So the reactants, we need to break 2 chlorine-chlorine single bonds due to the 2 that's in front of it. And for carbon tetrachloride, we're going to form 4 carbon-chlorine bonds. So it's going to be 4 CCl bonds. So reactants minus products. Now, the reason why it's like that way, it's reactants minus products, is because when you break the chlorine-chlorine bonds, you got to put energy into it. It's endothermic, so it has to be positive. So that's why the reactant side is positive. And whenever the carbon-chlorine bonds are formed in this reaction, energy is going to be released, so it's exothermic. That's why we have a negative sign for the products. So let's go ahead and plug in the information that we have. So it's going to be 2 times the value for the CCl, for the chlorine-chlorine bond, which is 242, minus 4 times the value of the carbon-chlorine bond, which is 328. If you type this in your calculator, you should get negative 828 kilojoules per mole. So the right answer is A. This reaction is exothermic overall. 126. Estimate the enthalpy of the reaction using bond dissociation energies. So the first thing we need to do is draw the Lewis structure for these compounds. Acetylene, C2H2, looks like this. It's a triple bond between 2 carbon atoms, and it has 2 hydrogen atoms. Oxygen has a double bond, and carbon dioxide looks like this, and this is water. So we know the enthalpy of the reaction is going to be reactants minus products. But we need to find out what bonds we need to break on the reactant side and what bonds are going to form on the product side. So let's focus on the reactant side. we need to break two carbon-carbon triple bonds. In C2H2, there's only one carbon-carbon triple bond, but there's a 2 in front of it in a balanced reaction. So we're going to write 2C triple bond C, and then plus, we need to also break two carbon-hydrogen bonds. So I'm going to write two CH bonds plus the oxygen molecule has a double bond and there's 5 of them. So we need to break 5 oxygen double bonds. And then minus, on the right side, we have carbon dioxide. In a single carbon dioxide molecule, as you can see, there's 2 carbon oxygen bonds. And there's a 4 in front of it, so 4 times 2, we need to break 8 carbon oxygen bonds. Now, in water, there's 2 oxygen hydrogen bonds, or 1, 2, and there's a 2 in front of it in the reaction, so 2 times 2, we need to break 4 oxygen hydrogen bonds. So now let's plug in the values that we have. So it's going to be 2 times the value for the triple bond between 2 carbon atoms, which is 839 according to the table. And for the carbon-hydrogen bonds, it's going to be 2 times 413 plus 5 times 495. And then minus, I'm going to distribute the negative sign to the last 2 terms. So minus 8 carbon-oxygen bonds, so 8 times 799. And then minus 4 times the OH value, which is 463. So type this in your calculator just exactly the way you see it. And if I type this in correctly, what I got is negative. I did not get that answer. Let me try this again. You know what? I've missed something. The carbon-hydrogen bonds, I see the mistake. So I have 2 carbon-hydrogen bonds in a single acetylene molecule, but I forgot to multiply by 2. A simple mistake can change the entire answer. So this should be 4 CHs. So I need a 4 in front of the 413. So let me try it again. So if you type it in now, you should get negative 2439 kilojoules per mole. So B is the right answer. And I believe I've accounted for every other bond. So that's it for this problem. 127. Rank the following molecules in order of increase in boiling point. The first thing we should do is arrange the elements in the way that it's presented in the periodic table. So first we have fluorine, and then chlorine, and then bromine, and then iodine. Now, the molecule that has the highest boiling point is the one that's going to have the most intermolecular forces, which is going to be iodine. Iodine has the highest molar mass. As the molar mass or molecular weight increases, the London dispersion forces increases as well, which increases the overall intermolecular forces. So iodine has the most, that's why it's going to have the highest boiling point. And all of these molecules are nonpolar. Nonpolar molecules only have London dispersion forces, also known as van der Waals forces. They don't have dipole interactions or hydrogen bonding. But keep in mind though, since they only have London dispersion forces, they do have temporary induced dipole moments. Since iodine is the most polarizable element, it's going to have the highest boiling point. So fluorine is going to have the lowest boiling point since it's the lightest gas. Chlorine is going to be next, then is bromine, and then it's iodine. Fluorine is a gas, chlorine is a gas, bromine is a liquid, and iodine is a solid. So iodine has the highest boiling point. So the correct answer for this problem is answer choice A. 128. Which of the following molecules has the highest boiling point? Is it A, B, C, or D? The answer is D, HF. HF has hydrogen bonds. Hydrogen bonds exist whenever H is directly attached to any one of these elements: nitrogen, oxygen, or fluorine. So HF is going to have the highest boiling point. The second highest will be HI, and then it's HBr, and then it's HCl. So here's fluorine on the periodic table, and then there's chlorine, bromine, and iodine. So fluorine has hydrogen bonding when it's attached to HF, so that's why it's the highest. After that, the remaining three, HCl, HBr, and HI, they don't have hydrogen bonds. They're polar, so they have dipole interactions, and they also have London dispersion forces. But as the size increases, the dispersion forces increase. So that's why HI has a higher boiling point than HBr and HCl. It's because it's bigger and it has more intermolecular forces. So what you need to know is this: whenever you're comparing like four gases or four compounds, and they're all molecules, the one that's going to have the highest boiling point is the one that has hydrogen bonds. After that, look at size. The one that's bigger is going to have the highest boiling point after that. So HI is bigger than HBr, so it has a higher boiling point, and HBr is bigger than HCl. So HCl has the lowest. But D is the right answer for this problem. 129. Which of the following molecules has the lowest vapor pressure? What you need to know for this problem is that as the intermolecular forces increases, the boiling point goes up and the vapor pressure goes down. So therefore, the molecule that has the lowest vapor pressure has the highest boiling point. So we need to see which one has the most intermolecular forces. So looking at A, methane is nonpolar. Anytime you have a compound or molecule that has carbon and hydrogen bonds only, it's going to be nonpolar. Now, if you have a molecule that contains only one type of element, it's nonpolar as well, since the electrons are shared equally. Carbon tetrafluoride is also nonpolar. If you were to draw the Lewis structure, all of the dipole moments cancel, and so therefore it's nonpolar. The arrows will point towards the more electronegative fluorine atom. Water is very polar, and water also have hydrogen bonds, so therefore it has the greatest amount of intermolecular forces, so it has the highest boiling point and the lowest vapor pressure. At room temperature, water is a liquid. Methane is a gas. Chlorine is a gas, and carbon tetrafluoride is a gas as well. Gases have very high vapor pressures, but liquids, they have lower vapor pressures relative to gases. So B is the right answer for this problem. 130. Which of the following statements is incorrect? The vapor pressure of a solution increases with increase in temperature. That is true. Let's say if you pour water on a table, the water will evaporate faster at a higher temperature than at a colder temperature. If the temperature of the room is cold, it's not going to evaporate as quickly. But if it's warm and if the room is dry, it will evaporate. So the vapor pressure of water increases with increase in temperature. So let me write it like this. As the temperature goes up, the vapor pressure goes up. Now, boiling point is inversely proportional with vapor pressure. That is a true statement. As the boiling point goes up, the vapor pressure goes down. C, the boiling point of a solution increases with elevation. That is incorrect. If you were to go to the top of a mountain, it's very easy to boil water because the air is thin. And so the boiling point of water is actually lower at high elevations. But if you go to sea level, like if you go down at sea level, water boils at 100. But on the top of a mountain, it could be like 60 Celsius or 50 Celsius. So as elevation increases, boiling point decreases. So it's easier to boil water when the atmospheric pressure is low. Now D, vapor pressure decreases with increase in intermolecular forces. That is a true statement. As the intermolecular forces increases, we know that the boiling point goes up. And when the boiling point goes up, the vapor pressure goes down. And so the answer for this problem is C. C is the statement that is incorrect. So let's explain conceptually why the boiling point is higher at sea level compared to the top of a mountain. So let's say this picture represents sea level. And this picture on the right is going to represent the situation on top of a mountain. So let's say you have water. At sea level, the pressure is higher. The atmospheric pressure is like 1 atm. At the top of the mountain, depending on the elevation, it's going to be lower. So let's put a number to it. Let's say it's like 0.4 or 0.5 atm. So at sea level, there's more gas molecules in the air. Twice as much. But in a mountain or on top of a mountain, there's less gas molecules. So we say the air is thin. Now, it's going to take more energy for the water molecules to boil because they have to go against a lot more gas particles in the air. These gas particles, they push against the water molecules. So they act as a barrier, so to speak. So it takes more energy for those water molecules to evaporate or to be vaporized into steam. And so that's why the boiling point is higher. It could be like 100 at sea level. But on the right side, there's less resistance presented by these gas particles. So it's easier for water to evaporate. So it takes much less energy for water to reach its boiling point because it faces less resistance by the atmospheric pressure, by the gases that are above the liquid. So that's why the boiling point at higher elevations is lower, let's say 50, because there's less resistance by the gas molecules in the air. So it's easier for water to evaporate. So I hope that makes sense. And so just keep this in mind. As the elevation goes up, the boiling point goes down. And whenever boiling point decreases, it's easier for a gas to evaporate into, or it's easier for a liquid to evaporate into the gas phase. The next concept that we need to discuss is vapor pressure. Have you ever wondered what vapor pressure is? What is vapor pressure exactly, and how is it different from just pressure? It turns out that vapor pressure is the partial pressure of a liquid above its surface at equilibrium. The key word here is equilibrium. And let me draw 3 boxes that's going to help you to understand the concept. So in both of these boxes, in all 3 of these, there's going to be water. And initially, in the first box, the atmospheric pressure is 0. So there's no gases in the air, just water. So what's going to happen? If there's no gases in the air, what is water going to do? So water has virtually no resistance. It can easily enter into the gas phase. So water is going to begin to evaporate. So I'm going to draw 3 arrows to represent evaporation. Now, as water evaporates, we're going to start getting water molecules in the air. Now, the vapor pressure of water is about 23.76 torr at a temperature of 25 degrees Celsius. So let's assume that the temperature is 25 for this particular scenario. So as water continues to evaporate, the partial pressure of water above the liquid surface is going to increase. So let's say at this point it's about 10 atm. So that's the partial pressure of water. So as water continues to evaporate, some of the water molecules in the gas phase will begin to condense back into the liquid phase. So you have like evaporation and condensation occurring at the same time. But because the partial pressure of water is less than the vapor pressure, the rate of evaporation exceeds condensation. Now, so more water molecules will continue to evaporate because evaporation is greater than condensation at this point. Now, there's going to reach a point where there's going to be a lot of water molecules in the air, such that the partial pressure of water is now 23.76 torr. Once the partial pressure of water equals the vapor pressure, equilibrium has been established. The rate of condensation, that is the rate of gaseous water molecules going into the liquid phase, equals the rate of evaporation. And it is at this point where the vapor pressure is equal to the partial pressure of water. Evaporation is equal to condensation. And so that is the idea behind vapor pressure. Vapor pressure is the partial pressure of water when the rate of evaporation equals the rate of condensation, or basically when you have equilibrium between evaporation and condensation. So that's the vapor pressure. So even though partial pressure can be anything, the partial pressure of water could be 5, 8, 12, 16, 24, 21.2. The vapor pressure is a specific number. It is a specific partial pressure at which point the rate of condensation equals the rate of evaporation. 131. Which choice below correctly ranks the following molecules in order of increase in boiling point? Ammonia is going to have the highest boiling point because it has hydrogen bonds. In a periodic table, you have nitrogen. Below that, there exists phosphorus, and then arsenic is below phosphorus. So the one with the highest should be NH3. Now the remaining two do not have hydrogen bonds. So now we need to look at molar mass. Arsenic is heavier or has a higher molar mass than pH3. So we should expect that arsenic should have a higher boiling point than phosphorus. So the correct answer for this problem is answer choice C. pH3 has the lowest boiling point and NH3 has the highest. So the first thing you should look at is for the presence of hydrogen bonds. After that, for the remaining elements that do not have hydrogen bonds, look at size. Arsenic is bigger than phosphorus, so it's going to have a higher boiling point. (132) Which choice below correctly ranks the following molecules in order of increase in vapor pressure? So let's rank it in order of increase in boiling point, and then we're going to reverse it for increase in vapor pressure. So water has hydrogen bonds, so it's going to have the highest boiling point. So below oxygen in the periodic table, there is sulfur, and then below that is selenium. So because selenium has a higher atomic mass than sulfur, so H2SC is going to have a higher boiling point. So out of the three, H2S has the lowest boiling point. Because H2S has the lowest boiling point, it's going to have the highest vapor pressure. So this is how you rank it for boiling point in increase in order. And for vapor pressure, we need to change the order. So H2S is going to have the highest vapor pressure. H2SE is going to be in the middle. And H2O is going to have the lowest vapor pressure. Water is a liquid. And H2SE and H2S are gases. So the correct answer for this problem is Answer choice D. 133. Which of the following terms represents the tendency of a liquid to form droplets due to the presence of unbalanced forces? Is it A, B, C, or D? The correct answer is D. It's surface tension. So let's say if you have a surface, and we're going to pour two liquids on a surface, hexane, which has the formula C6H12, and water. Now, because hexane is nonpolar, it only has carbon-hydrogen bonds, it doesn't have a lot of surface tension, and so therefore, if you pour it on a surface, it's going to flatten out. It's not going to form a bead. But if you pour water on a surface, a very small amount of water, it's going to form a bead. It's going to have like a spherical shape. The reason for that is the cohesive forces that are found in water is very strong relative to the adhesive forces between water and the surface. So that's why water forms this bead. It has a lot of surface tension. The water molecules on the surface of this bead, which is on its blue line, they have unbalanced forces. The water molecules on the surface are attracted to the water molecules on the interior due to the cohesive forces between them. And so the water molecules on the surface are pulled towards the center. They have a net inward force, and that's why it forms this spherical shape. So surface tension is related to these unbalanced forces that cause molecules to form that bead-like shape. And so the water molecules, they're going to try to minimize their surface area. And the only way to do that is to form this spherical shape. So that's the main idea behind surface tension. Cohesive forces is the forces between two similar molecules. So the force between two water molecules would be considered a cohesive force. The force between, let's say, a water molecule and, let's say, the surface of a glass, that would be considered an adhesive force. So let's say this is a wooden table, or let's say it's a polished wooden table. The interaction between water and the surface of this wooden table, that is an adhesive force. The interaction between water molecules inside this bead would be considered cohesive. When the cohesive forces exceed the adhesive forces, water usually forms this bead-like shape. Now, in the case of hexane, the adhesive forces exceed the cohesive forces, and so hexane is more attracted to the surface as opposed to itself, and so it flattens out. So it really depends on which of these forces are greater. Now let's talk about polarizability. Polarizability is the ability of an atom to distort its electron cloud, such that it can create instantaneous dipoles or temporary induced dipoles. So let's consider two molecules, iodine and fluorine. Iodine is very heavy. It has a molar mass of approximately 254, and for fluorine it's about 38. So iodine has a lot more electrons than fluorine. Therefore, because it has so many electrons which are constantly moving, it's very easy for one side of the atom to have more electrons than the other, in which case you'll have a temporary dipole. One side will be slightly negative, the other side will be slightly positive. So imagine, let's say this is the iodine atom. If in any given moment, you may have like 51% of electrons on the left side and 49% of electrons on the right side. So the right side will be slightly positive, and that would form a temporary dipole, a dipole that lasts for a very short time. And the ability of a molecule to do that, that's polarizability. So because iodine is more polarizable than fluorine, iodine has more London dispersion forces and van der Waals forces. Those forces is a result of the formation of temporary induced dipole moments, which is associated with polarizability. So iodine, because it's heavier, it has more electrons, it's more polarizable, it has more London dispersion forces, more van der Waals forces, and that's why it has a higher boiling point than fluorine. Iodine exists as a solid at room temperature, whereas fluorine is a gas. 134. The vapor pressure of an unknown solvent is found to be 8.76 torr at 298 Kelvin and 42.1 torr at 356 Kelvin. Calculate the heat of vaporization of the solvent. The equation that we need is the natural log of P2 over P1, which equals the heat of vaporization divided by R multiplied by 1 over T1 minus 1 over T2. So we're going to rearrange the equation to find the heat of vaporization. So we need to multiply both sides by R and divide both sides by this term. So if you rearrange it, the heat of vaporization should equal R ln P2 divided by P1, all divided by 1 over T1 minus 1 over T2. Now R is the energy constant, not 0.08206, but you want to use 8.3145. And then we're going to multiply that by the natural log of the second pressure divided by the first one. The second pressure, we're going to define it as 42.1. The first one is going to be 8.76. So 42.1 divided by 8.76. And then we're going to divide that by 1 over T1 is 298 Kelvin and T2 is 356 Kelvin. And make sure you put this in parentheses when you type it in your calculator. So if you type it in correctly, you should get 23,874. Now, R has the units joules per mole per Kelvin. And we have Kelvin in the bottom, so the units Kelvin will cancel. So this number is in joules per mole. And to convert it to kilojoules per mole, we need to divide it by 1,000. And so we're going to get 23.87 kilojoules per mole. So the answer for this problem is A. 135. Which of the following statements is incorrect? Is it A, B, C, or D? So let's look at each one. A. The conductivity of metals increases with temperature. Well, that is false. B is a true statement. The conductivity of metals decreases with temperature. As the temperature goes up, the electroconductivity of metals will decrease. Metals are more conductive at colder temperatures. In fact, if you cool a metal close to absolute zero, it can become a superconductor. C. The conductivity of semiconductors increases with temperature. That is a true statement. Semiconductors, or metalloids like silicon or germanium, their conductivity is fairly low, but as you raise the temperature, the conductivity of these metalloids will increase. And D is also a true statement. The conductivity of semiconductors increases with increased dopant impurities. So let's say if you have a silicon crystal, and let's say if you added a few aluminum atoms to it or a few phosphorus atoms, the conductivity of the impure silicon crystal will go up. So anytime you add like another atom with like 3 or 5 valence electrons to a semiconductor, even just adding a small amount, the conductivity will increase. In fact, that's how solar cells are made. 35.1 grams of sodium sulfate is dissolved in 250 milliliters of water. Calculate the molality of the solution if the density of water is 1 gram per milliliter. So, since the density is 1 gram per milliliter, and if we multiply it by 250 milliliters, we can get the mass of water, which is going to be 250 grams. Now, if we want to, we can convert that to kilograms by dividing by 1,000 grams. Molality is defined as the moles of solute divided by the kilograms of solvent. And right now, we have 0.25 kilograms of solvent, which is H2O. So the next thing we need to do is convert the grams of solute into moles and divide it by the kilograms of solvent. And that's going to give us the molality. So first we need to write the formula for sodium sulfate. Sodium has a +1 charge, and sulfate has a 2- charge. So the formula is going to be Na2SO4. So starting with 35.1 grams of Na2SO4, we can now convert it to moles. But we got to find the molar mass. So we need to add up all of the atoms that are found in sodium sulfate. So sodium has a molar mass of 23, and for sulfur it's like 32.06, and for oxygen it's about 16. So the molar mass is 142.06 grams. So now that we have the moles, we can divide it by the kilograms of solvent. And this should give us the molality. So 35.1 divided by 142.06, and then take that result, which is 0.247, divided by 0.25. And the molality is 0.988. So B is the right answer. (137) Which of the following statements are correct? Number 1, vapor pressure is dependent on surface area. Is that true or false? This is a false statement. The vapor pressure of water at 25 degrees Celsius is 23.76 torr. So at that temperature, it doesn't matter if you have a small puddle of water or a very large puddle of water. For both samples of water, small or large, the vapor pressure of water at that temperature will still be the same. It's going to be 23.76. So vapor pressure does not depend on surface area, but it depends on temperature. Number 2, vapor pressure is defined as the partial pressure of a solution at which the rate of evaporation equals the rate of condensation. That is a true statement. We talked about that earlier in this video. And once evaporation equals the rate of condensation, the partial pressure of water at that time is defined as the vapor pressure. You just simply have to know this definition. Number 3, the normal boiling point is the temperature at which the vapor pressure of the solution equals the atmospheric pressure. That too is a true statement. Let's make a table. At 25 degrees Celsius, the vapor pressure is about 23.76 torr. As you increase the temperature, the vapor pressure goes up. So let's say if you heat it up to like 50, the vapor pressure of water is now 92.5 torr. If you increase it to like, let's say 80 degrees Celsius, the vapor pressure is now 355 torr. If you increase it to 100 degrees Celsius, the vapor pressure will be equal to 760 torr. And 760 torr is equal to 1 atmospheric pressure, or 1 atm. And 100 degrees Celsius is the boiling point. So whenever the vapor pressure equals the atmospheric pressure, The temperature at which the vapor pressure equals the atmospheric pressure, that temperature is the normal boiling point. And when you hear the word normal boiling point versus boiling point, the normal boiling point always occurs at a pressure of 1 atm. If you just hear the word boiling point, the pressure may be different than 1 atm, but if you hear the word normal boiling point, the pressure has to be 1 atm. So number 3 is a true statement. Number 4, the boiling point of a solution increases with elevation. That's false. If you go on top of a mountain, the air is thin and it's easier to boil water. So as elevation increases, boiling point decreases. So the correct answer for this problem is number 2 and 3, which is B. So answer choice B is the right answer. 138. Calculate the molality of a 0.355 molar solution of Ki having a density of 1.1 grams per milliliter. So, how can we use molarity and density and convert that into molality? How would you do it? So first, we need to break down the word molarity. Molarity is moles over liters. So a 0.355 molar solution means that there are 0.355 moles of Ki if we have a 1 liter solution. So we're going to use these two values, 0.355 moles of Ki and a 1 liter solution. So that would be, if we use those numbers, the molarity would be 0.355. So if we have a 1 liter solution, that means that we have 1,000 milliliters of solution. And if we multiply that by the density, which is 1.1 grams per milliliter, the units milliliters will cancel, and that means that if we have a 1 liter solution, we therefore have 1,100 grams of solution. Now, to find molality, we need to get the kilograms of solvent. We already have the moles of solute, which is 0.355. So that's half the battle right there. But somehow we have to get the kilograms of solvent. So let's convert moles of solute into grams. So let's start with the 0.355 moles of Ki. The molar mass of potassium is 39.1, and for iodine, it's 126.9. So the molar mass for Ki, it's about 166 grams per 1 mole. So therefore, we have 58.93 grams of Ki, which is the solute. Now you need to understand the relationship between the terms solute, solvent, and solution. The solute, which is Ki, plus the solvent, which is water, adds up to the solution, which is the combination of both. So, if we have 58.9 grams of solute, and if we have 1,100 grams of solution, how many grams of solvent do we have? So 1,100 minus 58.9 means that we have 1,041.1 grams of solvent. So now we could find the molality. So the molality is going to be the 0.355 moles of solute divided by the kilograms of solvent. So if we have 1,041 grams of solvent, to convert that to kilograms, we could just divide by 1,000. So that means that we have 1.041 kilograms of solvent. So the molality of the solution is therefore 0.341. So A is the right answer for this problem. So that's how you can use molarity and density to calculate the molality of the solution. 139. Calculate the molarity of a 0.422 molal sodium bromide solution having a density of 1.07 grams per milliliter. So, in order to find molarity, we need to find the moles of solute and the liters of solution. So let's consider the molality, which is 0.422. What this means is that there are 0.422 moles of sodium bromide in 1 kilogram of solvent, which the solvent is going to be water. If it's not specified, we're going to assume it's water. So we already have the moles. Now we need to find the liters of solution. So 1 kilogram of water means that we have 1,000 grams of water. Now, if we could find the grams of solute, we can add that to the grams of solvent to get the grams of solution. So let's start with the 0.422 moles of NaBr, and let's go ahead and convert that into grams. So Na has a molar mass of 23, and bromine, it's 79.9. So the molar mass of NaBr is 102.9 grams per mole. So if you multiply these two numbers, you're going to get 43.42 grams of NaBr. So since the solute plus the solvent equals the solution, if we add the 43.42 grams of solute plus the 1,000 grams of solvent, this means that we have 1,043.42 grams of solution. So now, using the density, we can now find the liters of solution. So let's start with 1,043.42 grams of solution. We're going to multiply it by 1 milliliter per 1.07 grams. So notice that the unit grams cancel. So now we just got to convert milliliters into liters. And there are 1,000 milliliters per 1 liter. So 1,043.42 divided by 1.07, and then take that result and divide it by 1,000. So the volume is 0.9752 liters. So now we can calculate the molarity, which is the moles, 0.422 moles, divided by the liters, 0.9752. And so you should get 0.433 m. So A is the right answer. 140. Determine the freezing point of a solution made by dissolving 70.1 grams of calcium chloride with 200 grams of water. The Kf for water is 1.86 Celsius per molality. So the freezing point equation is delta T is equal to negative Kf times the molality times the Van Hoff factor. So let's find the molality first. Let's start with 70.1 grams of the solute, and let's convert it to moles. So we need to find the molar mass of calcium chloride. For calcium, it's about 40.08, and for chlorine, it's 35.45, but we have to multiply that number by 2. So the molar mass of CaCl2 is 110.98 grams. So the units grams cancel. Now that we have moles of solute, to get the molality, we need to divide by the kilograms of solvent. And currently we have 200 grams of water, and water is a solvent. So to convert grams to kilograms, divide by 1,000. 200 divided by 1,000 is 0.2. So we have 0.2 kilograms of solvent. So 70.1 divided by 110.98, that's about 0.6316. Take that result divided by 0.2. So the molality that you should have at this point is about 3.158. So now we can use the freezing point depression equation. Delta T is really the change in temperature between the freezing point of the solution and the freezing point of the pure solvent. So it's going to be T solution minus T solvent is equal to negative Kf, which is 1.86, times the molality, which is 3.158, and then multiplied by the Van Hoff factor. Now, how many ions are in calcium chloride? Calcium chloride will dissolve into 3 ions. You're going to get a calcium plus 2 ion. You get one of those, and you're going to get 2 chloride ions. So if you add these numbers up, 1 formula unit of calcium chloride will generate 3 ions, so the Van Hoff factor is 3. So let's put a 3 here. Now we're looking for the temperature of the solution. The temperature of the solvent, in this case the freezing point of water, is 0. So we don't have to worry about that number. So negative 1.86 times 3.158 times 3, that's going to be negative 17.62. So since 0 is nothing, the freezing point of the solution is now negative 17.6. So D is the right answer. 141. Which of the following is not a colligative property? A colligative property is one that is dependent on the moles of solute. So boiling point is a colligative property. Imagine if you have a container filled with water, not completely filled. And let's draw another one as well. On the left we have the pure solvent H2O. The boiling point of pure water is about 100 degrees Celsius. However, if you were to add salt to it, the boiling point will go up. It might increase to about 100.2 or 102 degrees Celsius. This process is called boiling point elevation. The freezing point or melting point of water is 0 degrees Celsius. If you were to add salt to it, the freezing point will go down, and this process is called freezing point depression. Now, the magnitude of the change in temperature is dependent on how many moles of solute particles that you add to it. So if you add like a lot of salt, the boiling point can go up to like 105, 106, 110, and the freezing point could drop to like negative 10 or negative 20. So the more salt that you add, the greater the change in the boiling point between the solution and the solvent. So therefore, boiling point and freezing point are colligative properties because they depend on the moles of solute that are dissolved in a solution. So since we're looking for the one that's not a colligative property, we could eliminate A. So as the moles go up, the boiling point of the solution will increase. And we know that boiling point is inversely related to vapor pressure. So as you add salt to water, the boiling point may go up, but the vapor pressure goes down. So D is eliminated. And molality is dependent on moles of solute. Molality is equal to moles of the kilograms, or moles of solute divided by kilograms of solvent. So molality is a colligative property. The only one that's not a colligative property is temperature. The temperature is not dependent on the moles of solute. So B is the answer that we're looking for. Going back to boiling point, the change in boiling point between the solution and the solvent is equal to Kb times m times I. So as you can see, boiling point elevation is dependent on molality. And molality, as we mentioned, is dependent on moles. So that's why boiling point elevation and freezing point depression are colligative properties. Now, vapor pressure is also a colligative property. The vapor pressure of the solution is equal to the mole fraction of the solvent times the partial pressure of the solvent. And the mole fraction of the solvent is equal to the moles of the solvent, in this case it might be like H2O, divided by the moles of the solute plus the moles of the solvent times the partial pressure of the solvent. So notice that the vapor pressure of the solution depends on the moles of solute. So vapor pressure is also a colligative property. There's an equation that directly relates the moles of solute particles to the vapor pressure. And so just keep that in mind. Boiling point elevation, freezing point depression, vapor pressure, those are all colligative properties, including molality and molarity. Now, there are some other things I do want to mention. Osmotic pressure, which is represented by pi in this equation, is a colligative property. As you can see, molarity is part of the equation, and molarity depends on the moles of solute per liter of solution. So osmotic pressure is another colligative property that you need to be aware of. So there's really four main colligative properties: boiling point elevation, freezing point depression, osmotic pressure, and vapor pressure. Those are the main four. Now, going back to temperature, for something to be a colligative property, not only does it depend on the moles of solute, but it does not depend on the identity of the solute. Because some of you might be wondering, well, let's say if you dissolve an ionic compound in water. Some ionic compounds are exothermic and some are endothermic, and the temperature can change. And if you add, let's say, a lot of an exothermic substance, let's say like sodium hydroxide. If you dissolve sodium hydroxide in water, it is very exothermic. And the more you add to it, the more heat will be released and the temperature will increase. So if you're reasoning that way, you have to realize that temperature is still not a colligative property, because the temperature of that solution is really dependent on the identity of the substance or the solute. Sodium hydroxide may be very exothermic, but sodium chloride, if you dissolve it in water, is not very exothermic. And so you might not even notice a temperature change if you put salt in water. So because the temperature of the solution will be dependent on which solute you dissolve in it, it's not considered a colligative property. It has to be dependent on the moles of solute particles and not dependent on the identity of the solute. So that's another reason why we could say temperature is not a colligative property. 5.12 grams of ethanol is dissolved in 40.1 grams of benzene. The freezing point of benzene is 5.5 degrees Celsius. Calculate the freezing point of the solution. And the Kf for benzene is 5.12 Celsius per molal. So the first thing we need to do is find the molality of the solution. So which one is the solute and which one is the solvent? The solvent is the 40 grams of benzene because, for one thing, we have a greater quantity of benzene, and also we were given the Kf for benzene, so that has to be the solvent. So ethanol is the solute. So let's start with 5.12 grams of ethanol, and let's convert it to moles. So we need to find the molar mass. So carbon is about 12.01. We're going to multiply that by 2. And there are 6 hydrogens, each with a molar mass of 1.008. And plus we need to add 16 for oxygen. So the molar mass for ethanol, you should get 46.068 grams. Now the next thing we need to do to get molality is we need to divide by the kilograms of solvent. So we have 40.1 grams of solvent. To convert it to kilograms, we have to divide by 1,000. So 40.1 divided by 1,000, that's going to be 0.0401 kilograms. So 5.12 divided by 46.068, that's 0.111. And take that number divided by 0.0401, you should get a molality of 2.772. So now we can use the equation delta T is equal to negative Kf times m times I. So the temperature of the solution minus the temperature of the solvent, that's delta T combined, which is 5.5, that's the freezing point of benzene, is equal to negative Kf, or negative 5.12, times the molality of 2.772, and ethanol doesn't dissociate into ions. It's a molecular compound. At least under neutral conditions, it doesn't really ionize. So the Van Hoff factor, we can assume it's 1. We're going to treat it as a non-electrolyte. So if we multiply 5.12 by 2.772, we're going to get negative 14.19. And so now we're going to add 5.5 to both sides, to negative 14.19 plus 5.5. You should get negative 8.69 degrees Celsius. So that's going to be the new freezing point of the solution. So the freezing point of pure benzene was 5.5 degrees Celsius, and once we add ethanol, the freezing point decreased to negative 8.69. So A is the right answer. 143. Which of the following combinations are immiscible? Is it A, B, C, or D? Like dissolves like. I'm sure you've heard of that expression. So we need to know which answer choice either contains 2 polar compounds or 2 nonpolar compounds. So we know water is polar. It has hydrogen bonds. Anything that have hydrogen bonding is going to be polar. So NH3 has hydrogen bonds, it's polar. Now, whenever you have a molecule that's composed of the same element, it's nonpolar. So iodine and bromine, they're nonpolar. They're made up of one type of element. The electrons are shared equally, and so since they're evenly distributed, it's not going to be polar. Now, whenever you have a hydrocarbon, or a molecule that is made up only of carbon and hydrogen, it's also going to be nonpolar. So we could eliminate answer choice A and C because a polar and a nonpolar compound do not mix. Now, sulfur dioxide, in order to determine if it's polar or not, we need to draw the Lewis structure. And let's count up the valence electrons. Sulfur has 6 valence electrons and oxygen has 6 as well. Both elements are found in group 6A or group 16 of the periodic table. And so you get a total of 18 valence electrons. To find the number of lone pairs on the central atom, subtract 18 by the highest multiple of 8, just under 18. So 8, 16, this would give us 2. So what this tells us is that there are 2 electrons, or 1 lone pair, on the central sulfur atom. Now, sulfur can have an expanded octet. It can have more than 8 electrons. And it turns out that the most stable form of sulfur dioxide looks like this. Oxygen likes to form 2 bonds. If you add up the electrons, you're going to get 18. Now, notice that this molecule has a bent shape. And if you draw the dipole moments, which point towards the more electronegative oxygen atom, notice that they're not exactly antiparallel. They don't cancel. They have to be directly opposite to each other to cancel. So due to the bent shape of this molecule, SO2 is polar. Carbon dioxide, if you add up the valence electrons, carbon has 4 and oxygen has 6 times 2, that's 12 plus 4, which is 16. 16 is a multiple of 8, and therefore, whenever you have a multiple of 8 valence electrons, there are going to be no lone pairs on the central atom, assuming if hydrogen is not in the compound. That technique works if hydrogen is not there. So it turns out this is the Lewis structure for carbon dioxide. Oxygen likes to form 2 bonds. It has 6 valence electrons and needs 2 more to get to 8. Carbon likes to form 4 bonds. It has 4 valence electrons and needs 4 more to get to 8. Now, if you draw the dipole moment for CO2, notice that the arrows are antiparallel. They cancel. And so what that tells us is that carbon dioxide is nonpolar. So SO2 and CO2, they shouldn't mix. Now, looking at carbon tetrachloride, there are 4 chlorine atoms, and chlorine is more electronegative than carbon. So notice that all of the dipole moments, they point in opposite directions. So therefore, they cancel. So these 2 cancel, and those two cancel, which means carbon tetrachloride is nonpolar. So for answer choice B, we have two nonpolar molecules, and like dissolves like, so carbon tetrachloride and Br2 are immiscible. So B is the right answer. So to answer a question like this, you have to be able to tell which compounds are polar and which ones are not. So let's review some basic rules. At least that can help you with like 90% of questions that you may encounter. So polar versus nonpolar compounds, how to quickly identify them. So first, identify the nonpolar ones. If it's composed of carbon and hydrogen only, like CH4, C6H6, C2H2, it's automatically nonpolar. If it's made up of one type of element, like I2, Br2, Cl2, H2, it's nonpolar. And if all of the outer elements are the same, and if there's no lone pairs in the central atom, it's going to be nonpolar, like CBr4, CF4, BF3, boron doesn't have any lone pairs, or like BCl3, PCl5, all of the outer elements are the same. It's going to be nonpolar. If it has hydrogen bonds like water, NH3, HF, it's going to be polar. Now, if it's not symmetrical, if it has like a bent shape, so like SO2, that has a bent shape, it's going to be polar. Let's see, NH3, or like NF3, it doesn't have a bent shape, but it's trigonopyramidal, and it only has like one lone pair, that's polar. So usually if it has like one lone pair, it's polar, but you have to watch out for the compounds that have multiple lone pairs, but if they're evenly distributed. So if you have a structure that has the square planar shape, like xenon tetrafluoride, this one is nonpolar. But let's say if you have a compound with the seesaw shape, like this one, it's going to be polar. Notice that you only have one lone pair, but if you have like two lone pairs that are like directly opposite to each other, it's going to be nonpolar. So this one is nonpolar and this is polar. But if it has like two lone pairs with a bent shape like water, that's polar. 144. Determine the mass percent of a 0.455 molal sodium chloride solution. So if we can find the mass of the solute and the mass of the solution, we can find the mass percent. So a 0.455 molal solution means that we have 0.455 moles of NaCl per 1 kilogram or 1,000 grams of solvent, which we're going to assume is H2O. So we have the grams of solvent. We need to find the grams of solute, and we can add that to get the grams of solution. So let's convert 0.55 moles of sodium chloride into grams. So we need to find the molar mass of NaCl. And Na has an atomic mass of 23, and for Cl is 35.45. So the molar mass of NaCl is 58.45 grams. So if we multiply that number by 0.455, we're going to get 26.59 grams of solute, which means the mass of the solution is the sum of the solvent and the solute, so it's going to be 1,026.59 grams. So now we could find the mass percent. So the mass percent is the mass of the solute, which is 26.59, divided by the mass of the solute and the solvent, which is the mass of the solution, and that's 1026.59, and we need to multiply it by 100%. So 26.59 divided by 1,026.59 times 100, you should get about 2.59%. So A is the answer for this problem. 145. Which of the following statements is incorrect? So let's look at A. The solubility of a gas in a solution decreases with increase in temperature. That is a true statement. let's say if you have a solution, and in the solution there's dissolved gas particles, let's say like carbon dioxide. If you add heat to the solution, what's going to happen? Particularly with the gas particles that are dissolved in the solution. The gas particles will gain enough energy and leave the solution. And so there's going to be less gas particles in the solution, and thus the solubility of the gas will decrease at that high temperature. So anytime temperature goes up, the solubility of a gas goes down. So B, the solubility of most ionic compounds increases in an aqueous solution with increase in temperature. Generally speaking, for most ionic compounds, this is true. Whenever you raise the temperature of the solution, you can dissolve more salt in, let's say, a warm water solution rather than a cold water solution. C, the solubility of a gas in a solution decreases with increase in external pressure. That's false. So let's say if we have a solution and there's some gas particles in it, but let's say the pressure of the gas above the solution is very high. Let's say if we pack it up with like CO2, a lot of carbon dioxide molecules. If there's so many gas particles in the air, they have nowhere else to go but in a solution. And so if you can increase the external pressure of the gas above the solution, more gas molecules will be forced to enter the solution, and so the amount of gas particles in the solution is very high. So therefore the solubility of the gas in that solution goes up. So whenever you increase the external pressure of a gas above the solution, the solubility of the gas in the solution goes up. And then D, molarity is a colligative property. This is a true statement. Molarity is equal to the moles of solute divided by the liters of solution, and molarity doesn't depend on the identity of the solute. It just depends on how much solute you have in a solution. So molarity can be considered a colligative property. So the answer for this problem is C. By the way, the relationship between the pressure of a gas and its solubility is Henry's law. Basically, he states that the pressure of a gas above a solution is proportional to the solubility of that gas in a solution. So as the pressure goes up, the solubility goes up for that gas. 146. The solubility of a gas is 0.0246 m at a pressure of 1.5 atm. Calculate the solubility of the gas if the pressure above the solution is increased to 5.5 atm. So the pressure was increased, and based on Henry's law, the solubility should therefore go up as well. And the equation that we need for this problem is P2 over P1 is equal to S2 over S1. So the second pressure is 5.5. The first one is 1.5. The units atm cancels. And the first solubility, which corresponds to a pressure of 1.5 atm, is 0.0246. So we're looking for S2, the solubility that corresponds to a pressure of 5.5 atm. So if we cross multiply, we're going to get 1.5 S2 is equal to, let's see, 5.5 times 0.0246 is about 0.1353. So now we need to divide both sides by 1.5. So 0.1353 divided by 1.5, you should get 0.0902. So D is the right answer. 147. Calculate the osmotic pressure of a 2.25 molar magnesium chloride solution at 35 degrees Celsius. The equation for osmotic pressure is pi is equal to mRT times the Van Hoff factor. So we already have the molarity is 2.25. The R value is the gas constant 0.08206 liters times atm per mole per Kelvin. So the temperature has to be in Kelvin. So 35 plus 273, that's going to be 308 Kelvin. Now we need to take into account the Van Hoff factor. Magnesium chloride will dissociate into one magnesium ion and two chloride ions. So we're going to get 3 ions in total, so the Van Hoff factor will be about 3. So if we multiply those numbers, 2.25 times 0.08206 times 308 times 3, the osmotic pressure should be 170.6 atm. So we can round that to 171. So A is the right answer. 148. Which of the following solutions will have the highest boiling point? We know that the difference between the boiling point of the solution and the boiling point of the solvent is Kb times m times I. So it's proportional to the product of the molality and the Van Hoff factor. So looking at D, magnesium phosphate is insoluble, so the Van Hoff factor is going to be less than 1. It might be close to 0, so we can eliminate D. Now for A, we have glucose, C6H12O6. It's a non-electrolyte. Even though it can dissolve in water, it doesn't ionize, so the Van Hoff factor is 1. So if we multiply m times I, for A it's going to be 0.60 times 1, so that's about 0.60. For B, sodium sulfate dissolves into 3 ions. We get 2 sodium ions and 1 sulfate ion. So which means that the Van Hoff factor is 3 for B. So if we multiply 0.25 times 3, we would get a molality Van Hoff product of 0.75. So m times I is 0.75. So now let's consider C. Aluminum fluoride will dissolve into 1 aluminum cation and 3 fluoride ions. So we're going to get a total of 4 ions. So it's going to be 0.35 times 4. 0.35 times 4 is about 1.4. And so solution C has the highest m times I product. So C, therefore, is going to be the right answer. We're going to get the highest boiling point. (149) Which of the following solutions will have the highest freezing point? So, freezing point, like boiling point, is dependent on m times I. But we have a negative sign instead of a positive sign. So potassium iodide has 2 ions, so 0.3 times 2, we're going to have an Mi value of 0.6. Magnesium fluoride has 3 ions, 1 Mg ion and 2 fluoride ions, so 0.45 times 3, this is going to be 1.35. Aluminum sulfate has 5 ions. I'm going to write this one out. So Al2SO4 3 will dissociate into 2 aluminum cations and 3 sulfate ions. So we have a total of 5 ions. So 0.35 times 5 is about 1.75. And sodium sulfate, we discussed that one already. It has 3 ions, so 0.55 times 3 is about 1.65. So which one is the answer? Is it A, B, C, or D? It turns out that the correct answer for this problem is A, because the question asked for the highest freezing point. If they wanted the lowest freezing point, it would be C. Keep this in mind. When you add salt to water, the boiling point goes up. It's a boiling point elevation process. But when you add salt to water, the freezing point goes down. And so the one that's going to have the lowest freezing point is the one with the highest m times I ratio, because the freezing point naturally decreases. But if you want the highest freezing point, you want the one with the least amount of solute. And let's illustrate this. So we know the equation is the temperature of the solution minus the temperature of the solvent, or the freezing point of the solvent. Let's say 0 for water. For water, Kf is negative 1.86. And let's say the molality is 2 and the Van Hoff factor is 3. So here we have an MI ratio of 6. If we calculate this, 6 times 1.86, this is going to be negative 11.16. Now, let's say if we have another solution with a lower m times I product. So let's say it's instead of 2 times 3, but 1 times 2. This would be negative 3.72. So the MI product is equal to 2 in this case. So which one has the higher freezing point? Is it negative 11 or negative 3.72? Which number is higher on the number line? On the number line, negative 11 is to the left and negative 3.7 is to the right. So the number line increases as you go to the right. So negative 3.7 has a higher value than negative 11. So this number correlates to the higher freezing point. And notice that it's associated with a lower m times I product. And so that's why we got A as the answer, because it has a lower m times I product, and therefore it's going to have a higher freezing point. So just be careful with the wording of the question. So let's summarize what we've considered. So let's say if you have a low m times I value versus a high m times I value. The one with the highest MI value is going to have the highest boiling point. So the boiling point change will be large. The boiling point is going to increase more. The one with the low MI value, the boiling point is not going to increase as much. So we should get like a small increase. So the one with the highest boiling point is going to be the one with the highest m times I value. Now, for freezing point always decreases. So the one with the low MI value is going to have a high freezing point. The one with a high MI value, the freezing point is going to decrease a lot, so it's going to have a low freezing point. So if you're looking for the lowest freezing point, you need to look for the one that has a high MI value. If you're looking for the compound that's going to give you the highest freezing point, you're looking for the one that gives you the lowest MI value. If you're looking for the highest boiling point, you need to find the highest MI value. The lowest boiling point would be the one with the lowest MI value. So I just want to summarize that so that you can understand it. 150. 197.4 grams of an unknown non-electrolyte solute was dissolved in 432 grams of water. The boiling point of the resulting solution is 101.3 Celsius. Identify the unknown solute. And the Kb for water is 0.512 Celsius per molality. So how can we do this? Anytime you want to identify the unknown solute, a simple way is to find the molar mass. So we need to find the molality, and then we can use that to find the moles, and then the grams over the moles is going to be the molar mass. We already have the grams of solute, and we have the grams of the solvent. So delta T is equal to Kb times m times I. The change in temperature is 101.3 for the solution minus 100 for water. The boiling point of pure water is 100. Kb is 0.512. We're looking for m, and The Van Hoff factor is 1 because it's a non-electrolyte. It isn't ionized. So the change in temperature, 101.3 minus 100, that's 1.3. And we're going to divide that by 0.512. So the molality is equal to 2.539. So what this means is that there's 2.539 moles of solute per kilogram of solvent, which is water. So if we multiply by 0.432 kilograms of water, notice that we have 432 grams of water. To convert it to kilograms, divide by 1,000. This is going to give us the molality. Well, not the molality, but the moles. 2.539 times 0.432. This will give us 1.097 moles of solute. So the units kilograms cancel. So now we could find the molar mass, which is going to be the mass, 197.4 grams of solute, divided by the moles, 1.097. And this is equal to 180 grams per mole. So now what we need to do is identify which compound has a molar mass of 180. So now we need to use the periodic table. Let's start with ethanol. If we added up 2 carbons times 12.01 plus the 6 hydrogens, which has a molar mass of 1.008, plus 16 for O, the molar mass is about 46 for ethanol, so D is out. For sucrose, we have 12 carbons, so 12 times 12, plus 22 hydrogens, plus 11 times 16 for the 11 oxygens. So sucrose has a molar mass of 342, so C is eliminated. Glucose, 6 times 12 plus 6 times 16. This is about 180, so B is the right answer. 151. Calculate the vapor pressure of the solution if 2 moles of methanol is mixed with 3 moles of diethyl ether. Assume the vapor pressure of methanol and diethyl ether are approximately 100 and 470 millimeters of mercury at a certain temperature. So here we have 2 volatile components that make up a mixture. And to find the pressure of the solution, we have to take both vapor pressures into account. We need an equation that basically is a weighted average. The equation for this particular problem is this equation right here. The vapor pressure of the solution is equal to the mole fraction of component A times the partial pressure of component A plus the mole fraction of component B times the partial pressure of component B. So the mole fraction of substance A, let's say it's methanol, it's 2 moles out of a total of 2 plus 3, or 5 moles. So 2 out of 5 is basically 40%. The partial pressure of methanol is 100, plus the mole fraction for component B, which is diethyl ether. We have 3 moles of diethyl ether out of 5. 3 out of 5 is 60%, times the partial pressure of 170. So this equation works like a weighted average. So 2/5 of 100 is about 40, and 3/5 of 470 is 282. So the pressure of the solution is somewhere between 100 and 470. But because we have more of diethyl ether, it should be closer to 470 than it is to 100. So 40 plus 282 is about 322. And so C is the right answer. 152. The partial pressures of CO, H2, and O2 are 74.5, 35.2, and 214 millimeters of mercury, respectively. Calculate the mole fraction of CO. One way to find the mole fraction of CO is to take the moles of carbon monoxide and divide it by the total moles. You can also find the mole fraction by taking the partial pressure of CO2 and divide it by the total pressure. So we're going to do it that way for this problem. So the partial pressure of carbon monoxide is 74.5. To find the total pressure, we need to use Dalton's law of partial pressures, and we need to add up all the individual partial pressures. So the partial pressure of CO plus the partial pressure of hydrogen gas plus the partial pressure of oxygen gas. So this should give us the answer. So 74.5 divided by the three numbers in the denominator is equal to 0.230. So A is the right answer. So what does this number mean, 0.23? If the mole fraction is 0.23, what does that mean? So what that means is that 23% of the particles in this mixture is carbon monoxide. 0.23 is 23% as a decimal. And so if you have a mole fraction of, let's say, 0.65, that relates to 65%. So let's say if we wanted to find the mole fraction of O2, it would be 214 divided by 214 plus 74.5 plus 35.2. The mole fraction of O2 is equal to 0.661. So what that means is that 66.1% of all the particles is composed of oxygen gas. 153. Which of the following represents the condition where solid, liquid, and gas phases coexist? This is the triple point. Now let's talk about the phase diagram. This is the solid phase. Let's extend it further. This is the liquid phase, and this is the gas phase. The triple point is right here. I'm going to put T for triple point. At that point, the solid and liquid and gas phases coexist. The line that separates the solid and liquid phases is known as the melting point line. And the line that separates the liquid and gas phase is the boiling point line. And the line that separates the solid and gas phase is the sublimation line, or sublimation curve. Now let's say if the pressure is 1 atm at this point. Let's draw a horizontal line. So at this point, let's say point A, at the intersection between 1 atm and the melting point line, that is the normal melting point. The normal melting point is the point where the solid and liquid phases coexist, but at a pressure of 1 atm. At point B, this is called the normal boiling point. It's the point on the boiling point curve, or the boiling point line, where the pressure is 1 atm. So whenever you hear the word normal melting point or normal boiling point, the pressure has to be 1 atm. As you go from solid to liquid, that is melting, and that's endothermic. As you go from liquid to solid, that is freezing. As you go from liquid to gas, as vaporization, and as you go from gas to liquid, that is condensation. Solid to gas is sublimation. Gas to solid is deposition. So by adjusting the temperature and the pressure, you can go from one phase to another. So as you increase the temperature, depending on what pressure you have, at high pressure, let me erase some of these lines. So at high pressure, as you increase the temperature, the solid is going to convert into a liquid. It's going to melt into a liquid, and then the liquid will vaporize into a gas. If you were to increase the pressure if you were to increase the temperature under low pressure conditions, the solid will skip the liquid phase and sublime into a gas. So at high pressures, you can go from a solid to a liquid to a gas if you raise the temperature. But at low pressure, you can go directly from a solid to a gas. So compounds that like to sublime directly from a solid to a gas. Two examples are carbon dioxide and iodine. Carbon dioxide is known as dry ice, and the reason why it's called dry ice is because it doesn't liquefy at normal pressures. So at a pressure of 1 atm, if you pour dry ice on a table, it's going to skip the liquid phase. It's going to go from a solid phase into a gas phase directly. However, if you wish to liquefy carbon dioxide, you need to raise the pressure. If you can increase the pressure, carbon dioxide will become a liquid first and then become a gas. But you have to greatly increase the pressure. If not, it's going to sublime, which it usually does under normal conditions. Iodine does the same thing. At normal pressure, at a pressure of 1 atm, it sublimes from a solid to a gas. Water, on the other hand, at 1 atm, it goes from a solid to a liquid to a gas. But water could sublime from an ice to a gas if you were to decrease the pressure well below 1 atm. So as you adjust the pressure, you can control whether if a solid will sublime or if it will melt before vaporizing. So there's some other things we do need to mention regarding the phase diagram, and that is the critical point. The critical point, it's basically somewhere over here. It's at a very high temperature and pressure. At the critical point, something happens. If you go past the critical point, you get into a region called a supercritical fluid. And that phase of matter, a supercritical fluid has, it's not really a gas and it's not really a liquid, but it has properties of both. This critical point has 2 points of interest. If you go down to the x-axis, this is called the critical temperature. And if you go to the left, this point is called the critical pressure. And once you surpass that point, then you have what is known as a supercritical fluid. So just make sure you know that the critical point is all the way at the end of the phase diagram. It's the point at which a supercritical fluid can form. Number 154. Which of the following statements is true concerning the density of water? Is it A, B, C, or D? So first, which one has a greater density, ice or liquid water? We know that ice floats on top of water, so that means that ice is less dense than water. So the density of the liquid is greater than the solid as it relates to water. So we can eliminate answer choice C and D. Now, why is the density of liquid water greater than that for ice? Is it because the melting point line has a positive slope or a negative slope? Well, let's draw the phase diagram for water. It looks something like this. So here's the solid phase, liquid, and gas. As you can see, the melting point curve has a negative slope. As you go to the right, the line goes down. It's going this way, so it has a negative slope. Now, carbon dioxide has a different phase diagram. Carbon dioxide and most other substances, it looks more like this. As you can see, the melting point line, which is the line in blue, it has a positive slope. As you go to the right, the line goes up rather than going down. So the correct answer for this problem is B. The reason why the density of liquid water is greater than the solid is because the melting point line has a negative slope. Now let's understand this. So let's start in the solid phase. On the y-axis we have pressure, and on the x-axis we have temperature. As you increase the pressure, notice what happens to ice. Ice will liquefy into liquid water. Whenever you increase the pressure, the density goes up. So because the liquid phase is above the solid phase, if you go directly up on the y-axis, that means the liquid phase is more dense. And that's what we see for water. But now for CO2, let's say if we start at this point, at the liquid phase, if we increase the pressure by going directly upward, notice that we'll enter the solid phase. That means that the solid phase is more dense than the liquid phase for carbon dioxide. So let's summarize what we're talking about here. So anytime you see a phase diagram, my drawing is terrible today. So anytime you see that, if you have a phase diagram where the melting point line has a negative slope, the density of the liquid is greater than that for the solid. And this is the phase diagram for water. So that's why liquid water is more dense than ice. But anytime the solid liquid melting point line, if it has a positive slope, the reverse is going to be true. The density of the solid is going to be higher than that of the liquid. So that's what you want to take from this particular problem. So this is the phase diagram for CO2. The difference is the slope. Here the slope is negative, and here the slope is positive. M represents slope if you go back to algebra. 155. A 4.78 gram, I meant to put rock, was dropped into a graduated cylinder containing 24.3 milliliters of water. The final volume of the mixture was 25.9. Calculate the density of the rock in kilograms per cubic meter. So the density of the rock can be calculated using this equation. Density is mass divided by volume. Now the mass of the rock is 4.78 grams. And the volume of the rock is the difference in the water displacement. The volume in the graduated cylinder rose from 24.3 to 25.9. So if you take the difference of those two numbers, you should get 1.6. So 4.78 divided by 1.6 is about 2.99 grams per milliliter. So now we need to change the units from grams per milliliter into kilograms per cubic meter. Now it's important to know that 1 cubic centimeter is equal to 1 milliliter. So let's convert. Let's start with 2.99 grams per milliliter. So let's multiply by 1 milliliter per cubic centimeter. And next, let's convert centimeters into meters. So there are 100 centimeters per meter. And let's raise it to the third power because we have centimeters cubed. So right now, milliliters cancel and centimeters will cancel as well. So we have cubic meters. We just need to convert grams into kilograms. And we know that there are 1,000 grams per 1 kilogram. So grams cancel. So now we could type this in the calculator. So it's going to be 2.99 times 100 raised to the third power, which is like 100 times 100 times 100, 3 times, and then divided by 1,000. So the answer that you should get is 2990 kilograms per cubic meter. So that's how you can change the units of density from one unit to another. So anytime you're dealing with square units or units cubed, just make sure to raise that conversion factor to the same power as what you see here. So D is the right answer for this problem. 156. John, Sally, and Susan performed different experiments to measure the density of aluminum, which has a value of 2.7 grams per milliliter. Which student's data is accurate but not precise? Is it John, Sally, or Susan? Accuracy is how close you are to the true value. Precision is how close your data is to one another. So, John's data is accurate. Let me just put A for accurate. The reason why it's accurate is because it's close to the accepted value of 2.7. Sally's data is not accurate because it's not close to it. Susan's data is accurate. It's close to the true value of 2.7. Now, John's data is not precise because the numbers are not very close to one another, so I'm going to put NP for not precise. Sally's data is precise. If you look at each of her values, they're very close to one another. 3.102, 3.101. Those numbers agree with one another, so her data is precise. Susan's data is precise as well. So John's data is accurate but not precise. Sally's data is precise but not accurate. Susan's data is both accurate and precise. But since we're looking for the student who is accurate and not precise, this is going to be John. So A is the right answer. 157. Which of the following statements is incorrect? Let's look at D first. The equivalence point occurs when equal molar amounts of acid and base have been mixed in a solution. That is true. C. The endpoint of a titration is determined by the color change of an indicator. That is true. If you have phenolphthalein, if it goes from clear to pink, you know that you've reached the endpoint of the titration. If you look at A, an aqueous solution of KOH will turn litmus paper blue. That is true. Litmus paper turns blue in the presence of a base, and it turns red in the presence of an acid, and KOH is a base. Anytime you see hydroxide with a metal, it's a base. So B is the statement that is false. An aqueous solution of HCl containing phenolphthalein will appear pink. Phenolphthalein is colorless in an acidic solution, but in a basic environment, it turns pink. So B is the statement that is incorrect. 158. What is the pressure of the gas inside the open-ended mercury manometer if the atmospheric pressure is 740? Now, the height difference of the mercury column is 25 millimeters of mercury. Now, millimeters of mercury and torr are the same thing. We know that 1 atm is equal to 760 torr, which is also equal to 760 millimeters of mercury. So when you see 25 millimeters of mercury, that's the same as 25 torr. However, that 25 corresponds to the height difference between these two different levels. So that's 25 millimeters of mercury, which we can say 25 torr. So in a problem like this, all you need to do is either add or subtract 25 to this number. So the answer is not going to be A and it's not going to be D. It's either B or C. So you need to find out which one is stronger, the gas or the atmospheric pressure. Now, the outside pressure, it applies a force against the surface of this liquid. So that's the outside pressure. The gas also exerts a force on this liquid. Who is stronger? Is it the gas or the outside air? Notice that the outside air pushes the boundary of the mercury further than the gas. So because it pushed it further, the outside air is stronger, which means the gas is weaker. So therefore, we have to subtract and not add. The pressure of the gas should be lower than 740 because it's weaker. So to calculate the pressure of the gas, it's going to be 740 torr minus 25 torr, which is equal to 715 torr. So C is the right answer for this problem. 159. Which of the elements shown below can have the following first four ionization energies? Is it A, B, C, or D? So notice that the jump occurs during the fourth ionization energy. As you go from the first to the second, the increase was about maybe 1200, 12 to 1300. And then as you go from the second to the third ionization energy, the increase was a little bit over 900. And as you go from the third to the fourth, the increase was about almost 8 to 9,000. So as we can see, the jump occurred during the fourth ionization energy. Now what this tells us is that the first three ionization energies is associated with valence electrons. The fourth ionization energy, because it's so high, it's associated with the removal of a core electron. So whatever this substance is, because the first three ionization energies are relatively low, this element has 3 valence electrons. Now with that information, we can ID the right element. Magnesium is found in group 2A of the periodic table, so it has 2 valence electrons. Potassium is found in group 1A, so it has 1 valence electron. Silicon has 4, but aluminum has 3, and therefore aluminum is the element that fits this description. So B is the right answer. 160. An unknown compound was added to an Erlenmeyer flask containing a solution of potassium chloride. A white precipitate formed. Which of the following is the unknown compound? So we need to know which one would yield a precipitation reaction. So let's say if we pair up KCl with the first one, barium hydroxide. Let's go ahead and predict the products of this reaction. The K will pair up with the OH, and Ba is going to pair up with Cl. Now, K has a +1 charge, and hydroxide has a -1 charge. So because they have the same charge, we can write them together, KOH. And for barium, it has a +2 charge. Chloride has a -1 charge. So we can pair it up like this. And so it's going to be Ba1Cl2. Now, alkali metals like lithium, sodium, potassium, they're always soluble. So potassium hydroxide is soluble. So let's write aqueous. Now, chloride is generally soluble except with elements like silver, mercury, and lead. So barium chloride is soluble. So it's not going to be A. A will not generate a precipitation reaction, but B will, because we have silver. So if we were to write the reaction between KCl and AgNO3, the products would be KNO3. K has a +1 charge, nitrate has a -1 charge, so they combine in a 1-to-1 ratio. And Ag also has a plus charge, Cl has a minus charge, so we get AgCl. Nitrates are always soluble, so this is going to be aqueous, but silver chloride, that's a solid, and so this is going to be the white precipitate that's formed. Now all of the other compounds, like aluminum sulfate, if you pair that up with KCl, you would get K2SO4, which is soluble, and AlCl3, which is soluble as well. And the other compound too, ammonium bromide, if you pair that up with KCl, you'll just get ammonium chloride and KBr. KBr is soluble, it has potassium, and ammonium is also soluble as well. So to answer this question, you need to know your solubility rules. The only precipitate that is formed is silver chloride, so B is the right answer.